Hello everyone, and welcome to what will be our largest space tour ever on this channel. Don't worry at all if you are not familiar with astronomy. It is all going to be easy to understand with simple examples and explanations that you can easily picture in your head. But for now, in preparation for the long discovery journey that awaits us, please adopt a comfortable position. There is no problem at all if you drift and fall asleep. You can always return later. You have timestamps to navigate between the planets if you want, on your screen, in the description, and in the comment pinned under this video, together with links to audio streaming sites and Patreon. But without waiting more, let's get started. The first leg of our trip begins close to the Sun, near the smallest and fastest planet of the system, Mercury. Mercury is only about twice bigger than the Earth-Moon, and there are actually satellites that are bigger than it, like Ganymede, a moon of Jupiter that we will visit later, or Titan, a moon of Saturn. But Mercury is considered a planet because it follows its own orbit around the Sun. It is not the satellite of another planet. Its mass is also bigger than any of these satellites because Mercury is denser. Its density is similar to Earth, and it is believed that Mercury is mainly made of metal, 70% of it dominated by iron, and the rest, about 30%, would be silicate material, what we generally call rock. As we're going to see, conditions at the surface of Mercury are strongly influenced by the proximity of the Sun. But how close to the Sun is it exactly? In average, the distance is about 58 million kilometers, or 35 million miles. For comparison, the Sun has a diameter of 1.4 million kilometers, so it's actually not that close, proportionally. If the Sun was the size of a basketball, then Mercury would be a small grain of sand, but several steps away from the basketball. Still, this raises a question. Mercury is comparatively very small, and due to its mass, which is enormous in comparison, the Sun is a huge gravity well. So why does Mercury keep its distance with the star instead of being pulled to it and swallowed? This brings the question of speeds and orbits. Mercury travels in space around the Sun at high speed. Its velocity is 48 kilometers per second, about 30 miles per second. For comparison, Earth travels at 30 kilometers per second. A general rule is that the farther planets are from the Sun, the slower they are on their orbit. The farthest one, Neptune, travels at only 5.4 kilometers per second, almost 10 times less than Mercury. And this is not a coincidence, because an orbit results from an equilibrium. There are two main variables to consider in a star system like ours when it comes to orbits. There is the gravitational pull of the huge mass that is at the center, which pulls the planets. And there is their velocity, which tends to push them away. It is a centrifugal force. Without the mass of the star at the center pulling them, planets would just escape. Their speed would surpass escape velocity, that is to say, the speed above which they can break free from the gravitational pull of another body. Their orbits form thanks to this equilibrium. There are bodies that sometimes escape the systems where they appeared and travel between stars, sometimes even planets. We know there are lone planets, which most probably formed in a star system and were expelled from it. Because even though orbits can last for hundreds of millions of years, billions even, they can be altered by other bodies sometimes, that for example make a planet or a satellite accelerate and break free. The equilibrium also does not mean that the orbit is a perfect circle, or that the speed is constant. Most orbits are actually elliptical. They look more or less oval. And that's particularly the case with Mercury. When the planet comes closer to the Sun, gravitation tends to make it accelerate, which means that it is pushed away. Its higher speed allows it to go farther from the Sun, but not far enough and fast enough to break free from it. So after traveling following a curve that makes it move away, it is pulled back, it reaccelerates, and so on. The cycle repeats itself. In the case of Mercury, it repeats itself in 88 of our days. So the Mercurian year, one revolution around the Sun, is 4 times shorter than on Earth. Now, when we say that planets like Mercury revolve around the Sun, it works and it is a statement that can be considered true. But it is not 100% accurate. What the planets and everything in the system revolve around is not the star itself, but the center of mass. The Sun accounts for more than 99% of this mass, 99.8% to be precise. So obviously it determines very strongly the center of mass. But the real center of mass in the system is not the center of the Sun. Each planet also has a little gravitational pull and drags the center of mass towards it. Of these planetary influences, the most important one in the solar system is by far Jupiter, because it is the most massive planet. It is more massive than all the other planets combined. Now, as it happens, the center of mass is generally inside the Sun, because planets are scattered around it, so their respective pools tend to cancel each other. But sometimes the center of mass can be outside of the Sun. If we imagine an extreme case, for example, when all planets are on the same side of the Sun, and they all pull more or less in the same direction, which is something that can happen. If all planets were to be aligned on the same side, the center of mass could be at a distance of 2 suns' radius from the Sun, 1 diameter. It is not much, but it leads to another geeky question. how often, if ever, are the 8 planets of the solar system aligned on the same side of the Sun? Actually, extremely rarely, and technically they cannot be perfectly aligned because their orbits are not exactly on the same plane. They are slightly oriented, tilted. So at no point could we draw a straight line that would go through the centers of each planet because of the differences in planes. But if we simplify and just ask for the planets to look aligned, watching the solar system from above, you're going to see it probably never happened and is unlikely to happen before the solar system disappears. Why? Because an alignment of just the 3 innermost planets of the system, Mercury, Venus, and Earth, happens only once every 40 years. The chance to have Mars, the 4th planet, on the same arc at this precise moment is very small, and the alignment of the 4 first planets can only happen once every several thousand years. And as you add more planets, Jupiter, Saturn, Uranus, Neptune, slower and slower, with larger and larger orbits, the probability that they are all in the same arc at the same time decreases very fast, or, in other terms, the number of passes you have to wait for this alignment to happen increases exponentially. I found a paper by a mathematician who calculated that the alignment of the 8 planets could only happen once every 400 billion years. But the solar system is thought to be only 4.5 billion years, almost 100 times less. And the universe would be less than 14 billion years old, following the Big Bang theory. So it is unlikely that the alignment of the 8 planets that can happen every 400 billion years ever took place in the first 4.5 billion years of the solar system. Maybe the odds are around 1%. And the odds are also that it will not happen before the Sun dies and the system disappears with it. But still, the point was to tell you that the center of mass moved a bit over time, and that this is the real pivot around which planets revolve. Now it is time to take a look at Mercury itself. Like other rocky planets, it has a solid crust and a dissociated structure inside, meaning that elements are organized in layers with a mantle and a core. And as you approach the center of the planet, pressure and temperature increase. I told you earlier that Mercury was 70% metal. It contains proportionally a lot more iron than any other planet in the solar system. And this is a bit of a mystery, because why would a particular planet accumulate a lot more iron than others in its formation process? Rocky matter in the solar system had a certain ratio of silicate and metal that can also be found in rocky planets like Earth or Mars. So why does Mercury differ in its composition? The first theory to explain this, the most widely accepted at this point, is that Mercury was bigger than it is now in the past, several billion years ago. At the time, its mass would have been more than twice its current mass, with a metal-silicate ratio similar to other rocky planets. but the solar system was still in its early stages, and there would have been a collision with a planetesimal, that is to say, a fairly large object formed by the accretion of rocks and dust that crossed Mercury's trajectory. Based on models, this planetesimal would have been several thousand kilometers across and about 1/6 of Mercury's mass. The collision between the two would have been cataclysmic and would have ejected in space, stripped away, much of the original crust and mantle of the planet, that is to say, its rocky components. So Mercury would be so rich in metal not because it attracted some more than other planets, but because it used to be a bigger planet that lost much of its rock and kept its metal. But this is just a hypothesis, and there are others. The second one has the same starting point. Mercury was more than twice more massive in the early stages of the system than it is today. But the loss of its rocky material would not have come from a collision, but rather from solar activity. The proto-sun, which was still forming, would have been larger than today. Gravitation made it contract to its current size over millions of years. So the sun would have been larger at the time, and as a result, temperatures near Mercury would have been around several thousand degrees. This would have vaporized the rock at Mercury's surface, forming an atmosphere of rock vapor, and this atmosphere would have been lost, carried away by the solar wind, that is to say, the stream of particles that the sun produces. So, a different explanation for the loss of Mercury's rock that would explain why it contains so much metal proportionally. A third hypothesis proposes that Mercury formed as a metal-rich planet from the start, because also of its proximity to the Sun. The huge cloud of gas that would have become the Sun would have caused drag on the particles from which Mercury was forming, was accreting. This would have made lighter particles go away, swallowed by the Sun, instead of being gathered by Mercury, whereas heavier metallic particles would have remained available, and as a result, Mercury would have ended with more metal than rock in its structure. In any case, this happened several billion years ago, and today Mercury presents a surface that is similar in appearance to that of the Moon, with large plains and a lot of craters, which always indicates that a body is geologically inactive. The surface material is not renewed by volcanism or plate tectonics like on Earth, but instead it stays still, and only impacts from asteroids can modify its appearance. Due to the proximity of the Sun, it makes sense to anticipate high temperatures at the surface, and indeed, this is the case, but only on the parts that are directly exposed to the Sun. Mercury can also be an intensely cooled place. Near the equator and during daytime, on the side of the planet exposed to sunlight, temperature rises up to 700 kelvins, that is about 800 degrees Fahrenheit, and more than 400 degrees Celsius, about twice the temperature in a cooking oven. But the same regions, at night, when they are plunged in the dark, fall to 100 kelvins only. That is minus 280 Fahrenheit or minus 173 Celsius. That is to say, cold enough to freeze water instantly. I'll tell you later about the conditions on Mars. They are harsh, but they are almost welcoming in comparison with that. And to make it worse, a day or a night lasts a very long time on Mercury. The planet revolves fast around the Sun. I told you before, 88 days. But it rotates, it spins slowly on its axis, and in a way that is locked to the Sun. Every time the planet completes 2 revolutions, 2 orbits, that is to say 2 Mercurian years, it rotates 3 times on its axis. For comparison, when the Earth completes 2 orbits, 2 of our years, it rotates more than 700 times on its axis, 2 times 365. But Mercury only 3 times. It is very slow at rotating. Another way of saying it is that one single rotation of Mercury happens in 58 of our days. But it also means that any point on the equator of Mercury can remain exposed for a very long time to the Sun, or for an equally long time stay in the dark, 176 days, 2 Mercurian years. The solar day, the time for the Sun to rise, stay in the sky and set, is actually longer than a year, due to this combination of rapid orbital velocity and slow spinning. 1 year on Earth is a touch more than 365 solar days, but on Mercury, 1 year is half a day. There are also regions of the planet around the poles that are constantly in the dark, or almost in the dark, and where the temperature never rises much. Probes that were sent in the past decades have shown that there was ice, probably water ice, that stays frozen around the poles of Mercury. This shows that despite its proximity to the Sun, the planet is not just a burning hot desert of plains and craters. The hottest planet of the solar system is actually not Mercury, but Venus. If you find Mercury hostile, wait for Venus because it is worse. So let's go on with our journey to our second destination, and also the second planet from the Sun in the solar system. At first sight, Venus and Earth could look like twin planets. Almost the same size, Earth is just a touch bigger. They are not that far apart, and actually there may have been a point in the distant past when Venus looked more like Earth than today. But nowadays the conditions at their surfaces could not be more different. We saw before that Mercury was at 58 million kilometers from the Sun. This is just an average because its orbit is elliptical. Venus is at 109 million kilometers, almost twice as far. The orbit of Venus is comprised between the Sun and the Earth orbit, and this means that seen from Earth, Venus is never very far from the Sun, and when it is not hidden by the Sun's light, it is not hard to see. After the Sun and the Moon, it is the most visible, the brightest object in the sky. And it is visible not just because of the relatively short distance on an astronomical scale, but because of a layer of very reflective clouds in its upper atmosphere. Mercury, the Moon, or Mars barely have an atmosphere compared with Earth. But on the contrary, Venus has the thickest, densest atmosphere of all rocky bodies in the solar system. The clouds that block sight and make the planet look white seen from space are composed primarily of sulfuric acid. But this is just a taste of what lies beneath. The atmosphere is so dense that at Venus' surface, pressure is more than 90 times what it is on Earth. For comparison, it is equivalent, the pressure, to being about 3,000 feet, 900 meters, underwater. That's a pressure human bodies cannot stand, obviously. Now there are submarines that reach this depth and more, so it is not impossible to imagine a man-made vehicle resisting to the pressure on Venus. But the other problem would be heat. The mean temperature at the surface is estimated at more than 700 kelvins, that is 460 degrees Celsius or 870 degrees Fahrenheit. Actually hotter than the surface of Mercury when it is exposed directly to the Sun. Why is Venus so hot? Also because of the atmosphere. We'll come back to the reasons why Venus ended up with such a dense atmosphere, but if we look at what it is now, it is primarily made of carbon dioxide, 96% of it, plus 3 to 4% of nitrogen, and traces of other elements. We know it rather well because Venus was one of the first targets of space exploration. The Soviet Union had an ambitious program to explore this planet in the 1960s, and they sent several probes. These probes didn't survive long in the atmosphere, given the conditions, but long enough to send a lot of valuable information. And since then, more and more information about Venus has been collected, including with a NASA probe called the Magellan Orbiter. This probe was able to map the surface with radars, since it is hidden in visible light. The carbon dioxide at the surface is in a state that we don't normally encounter on Earth. It is called a supercritical fluid. This means it is not just gas, because it is very pressurized, also very hot, but not to the point of being solid. It has passed the critical point of pressure and temperature, where it could be a gas, but there is not enough pressure to make it solid, so it exists in an intermediary state beyond the gaseous and liquid phases. It is this state of matter that is called supercritical fluid. It is believed to be rather common in the atmosphere of gas and ice giants, Jupiter, Saturn, Uranus, Neptune, and also on Venus. On Earth, it doesn't normally occur naturally because of the different set of conditions, except maybe for water at the exit of some hydrothermal vents. Hydrothermal vents are like natural chimneys that eject very hot water, heated by the temperature from the Earth's mantle. But they eject this water deep underwater. So when it comes out of the vent, this water is very hot, several hundred degrees. So at surface conditions it would be steam. But it cannot be steam because there is too much pressure for that. We are deep underwater. It cannot be just liquid either. It is too hot for that. And at the same time there is not enough pressure to make it solid, to turn it into ice. So it is in a supercritical state. Not for long, because it is ejected in water that is much colder, so it cools down quickly and becomes just liquid. It is hard to imagine the texture of a supercritical fluid. We are not used to it at all. But in any case, you don't want to experience it, because if you plunged your hand into a supercritical fluid, it would be at the same time burned and crushed. This gives you an idea of the kind of environment at the surface of Venus. And Venus' atmosphere is also responsible for the heat. It is so dense that it doesn't let any heat escape. It is a massive greenhouse effect, but extreme, the strongest we know of in the solar system. Venus did not form with such a thick atmosphere. Typically, the gases that compose the atmosphere on a rocky planet can come from asteroid impacts. They are liberated and stay because of gravitation, or they can come from degassing from the planet's crust and mantle. That is to say, when gas is released at the surface, typically what happens with volcanoes. This atmosphere stays in place around the planet when the planet is massive enough to retain it due to gravitation, and when it is not carried away, ejected into space by collisions or by the solar wind. A magnetic field, like Earth, also helps retain it. Venus does not have one, so gravitation explains how the atmosphere stays with the planet. Earth and Venus have similar masses. I told you Earth is just a touch more massive. So they also have quite similar gravitational pulls. Given this set of conditions, why did Venus ended with this crushing atmosphere and Earth did not? These are just hypotheses, but studies have suggested that several billions of years ago, Venus could have had an atmosphere rather similar to the early atmosphere of Earth. In these conditions, there could have been substantial quantities of liquid water on the surface, and why not? Life could have appeared in these oceans if they existed. But what would have doomed Venus would have been its proximity to the Sun. The distance from the Sun to Venus is 70% of the distance from the Sun to Earth. This means more energy received from the Sun. And as in the first 100 million years of the solar system, the Sun gained in luminosity, this water on Venus could have entirely evaporated. This would have accumulated greenhouse gases in the atmosphere. Water as gas, as vapor, has a greenhouse effect, and once past a critical point of greenhouse effect, the heating of the planet would have snowballed into a loop. The accumulation of heat at the surface liberated even more greenhouse gases, thickened the atmosphere, and made it even hotter, and so on. At this point, it is hard to imagine life at the surface of Venus. But if there is some, and this is purely speculative, we have no solid evidence of life on Venus at this point. It could be not at the surface, but higher in the atmosphere, in the upper cloud layers of Venus, about 30 miles, 50 kilometers up from the surface. Because there, temperature and pressure are lower, and actually not that far from terrestrial standards. But this environment is also very acidic, so the forms of life in that environment, if they exist, would have to be able to thrive floating in a type of environment that has no equivalent on Earth. Actually, these clouds are so dense that things could float on them. Venus was one of the first sources of inspiration for terraforming, or at least the installation of human cities on other planets. We will expand on that when I tell you about Mars and terraforming. Another effect of the atmosphere that completely surrounds the planet is that the temperature is about the same everywhere. There are no large differences between the equator and the poles, like on other planets. But there are still differences in temperatures because of differences in altitude. Venus has a geography with plains, they cover 80% of it, and they have a volcanic origin. There are also apparently active volcanoes on Venus, and this sulfuric acid we talked about in the clouds of the upper layers of the atmosphere would come from them. There are highlands, impact craters too, no small craters, because it takes a big asteroid to cross this atmosphere and impact the surface. Many meteorites, like the ones that sometimes hit the Earth's surface, would be destroyed and vaporized long before it happens on Venus. But there are larger impact craters left by bigger asteroids. The images we have from the surface are not actually photographies. They are radar maps that have been colored in false color. But they still give an idea of what the surface looks like. A surface probably similar to what the Earth would look like, with no water, no life of any kind, and constantly plunged in darkness because the sunlight cannot reach the surface. There would be many more things to say about Venus, but we have so much to discover around the solar system. So for now, we're going to return to Earth because its orbit is on our way to the next destination, Mars. To entertain you during the trip, I will tell you about our destination, the Red Planet, and the challenges to overcome to travel to Mars, land, stay, and come back. From the energy necessary and the distance to radiation or cohabitation of a small group of astronauts for a several-month-long journey. We will also talk about terraforming as a concept and how it could be applied to Mars, and many other things. Earth is already getting smaller, and we have crossed the orbit of the Moon. But there are still millions of miles to cross before we reach Mars. In past space cruises, we had to travel faster than light to reach exoplanets and even other galaxies. Such speeds defy the laws of physics as we know them, and there is good reason to estimate that they cannot physically be achieved. But tonight, traveling at a few percentage points of light speed will be enough to complete the round trip in about 1 hour. Such a speed has never been reached by man, but it is theoretically possible at least. So, what is the distance between Earth and Mars? There is not a single answer to this question, because the distance is constantly changing. Since you tuned in to this story, the distance has changed by thousands of miles as the two planets follow their orbits around the Sun at high speed. Sometimes they are on either side of the Sun, and when this happens, Mars is invisible from Earth. When the two planets are on opposite sides of the Sun, the distance is maximal and it reaches 400 million kilometers. This would be like 10,000 times the circumference of Earth. But there are also times when Mars is much closer. When Earth and Mars are aligned on the same side of the Sun. In this case, the distance drops to about 55 million kilometers, almost 8 times less. This is less than 40 million miles. About every 26 months, Mars reaches this close approach, this is how it is called, to Earth. And this is the right moment to take advantage of, to send missions to Mars. But the distance when a close approach happens is not always exactly the same, because it is not that simple. The two orbits of Earth and Mars are not exactly on the same plane. They are slightly tilted with respect to each other, and the exact shapes of these orbits change constantly because they are influenced by the position of other bodies, especially Jupiter, which has a significant influence on the orbit of Mars. At the scale of the solar system, these changes in orbits are very small, but they are absolutely relevant to space travel because they imply differences of hundreds of thousands of miles. The precise calculation of where planets will be is nothing new. It was developed along the 20th century and became crucial when probes started to be sent to space. But you can imagine the complexity of the observations and calculations that have to be made to take into account velocities and the influence of all bodies involved. So there's a lot of modelizing and mathematics going on to make accurate estimates, because a probe cannot miss its destination, which is constantly moving by millions of miles. And this is what would happen without good knowledge of orbits, speeds, and all the factors that impact them. So with all these elements at play, not all close approaches between Mars and Earth are exactly the same. In 2003, Mars made its closest approach to Earth in 60,000 years, and it won't be that close again until 2287. In the meantime, we will have to cross a bit more distance when close encounters happen. But as I said, there is one about every 26 months, every 2 years. The last one was in 2020. The next one will happen in 2022. And there is already a next NASA mission planned. If not in 2022, then when the next close approach presents itself, a mission known as Mars Sample Return, a campaign to bring samples of Mars soil and rocks back to Earth. Given that probes or spaceships need to come back, these missions need to be planned over several years. It is not possible to just arrive, land, take samples during a few weeks, and come back immediately. Because during the time spent on the planet, the distance with Earth has increased again by millions and millions of miles. Now, the distance and time in space are not the only elements that matter. Energy consumption to go, land, and come back is maybe even more important. And the shortest trip is not necessarily the most realistic or achievable. Storing energy, fuel, is complicated. It occupies space. It has to be sent to space. And as soon as spaceflight began, astronomers and engineers started studying the most efficient path into space when it comes to energy consumption. An economical way of traveling between planets is to jump from one orbit to another, following an elliptical orbit. This kind of transfer is called Oman transfer orbit. This is the orbit followed, for example, by the InSight probe sent by NASA a few years ago. It implies approximately 9-month travel time from Earth to Mars, then a stay of about 16 to 17 months on Mars, waiting for the next transfer window, and another 9-month trip to return to Earth. That is to say, 3 years in total for the round trip. A method that can help consume less energy when approaching the target, the planet, is called ballistic capture. What is it? When spacecrafts use Oman transfer orbit, it typically requires the spacecraft to burn fuel in order to slow down at the distant planet. Because when the ship approaches it, it travels faster in space than its destination. It has to catch up with it. The fuel necessary to slow down has to be transported all the way from Earth, which adds to the cost and complexity of the craft. But with the method of ballistic capture, the spacecraft is just placed in advance on the orbit of its destination planet before the planet arrives. When the target arrives, the craft is captured by the planet's gravity, and it can put itself in orbit around it with small thrusters for adjustments, but without a big expense of energy. Now, another possible method to slow down spacecrafts when they reach their target is a maneuver called aerobraking. Aerobraking consists in flying the craft through the atmosphere, so it has to be a body with an atmosphere, at the low point of the orbit. The frictions, the drag, slows it down, and the advantage is that this method uses the environment. It doesn't consume more energy than the minimum necessary to position the craft on the right orbit. So all this gives you an idea of the variety of mission plans, of possible paths that have been imagined and tested. We are now halfway to our destination, so before we talk about landing and the environment we will find on Mars, let's take a look at the formation of the planet and what it is made of. As you may know, the dominant theory about the formation of planets in the solar system is that it all started with a large accretion disk, a disk of gases and dust that was kept together and put in motion by gravitation. Most of the mass of matter concentrated in the center to form the Sun, but not all of it. The periphery of the new star was still filled with matter, with dust in orbit around it. And through collisions over millions and millions of years, this dust snowballed into bigger and bigger rocks and boulders. After millions of revolutions around the Sun, bigger rocks and protoplanets progressively cleaned up their orbits of dust and smaller bodies by absorbing them or turning them into their satellites. Like for Earth, this process is believed to have been completed about 4.5 billion years ago for Mars. At this point, rocky planets in the solar system had eliminated most of the smaller rocks and boulders on their orbit, and they had taken a ball shape. This globe shape happens because of gravity. Above a certain size, bodies become round, whereas smaller objects like asteroids or comets can keep other shapes. They are not large enough and massive enough to form a ball of matter. It is hard to figure out the history of Mars from Earth. On our planet, we can study the geological timeline by analyzing the layers of rocks and minerals. On Mars, nothing like that has been made yet. A few samples of soil could be analyzed by probes, but nothing comparable. But it doesn't mean hypotheses cannot be made. The age of the surface of a planet can be estimated by counting the number of visible craters. A higher number and density of craters points to older terrain. But Mars also has experienced intense volcanism along its history, and volcanism resets the surface terrain. It also has glaciers, winds, possibly running water in the past, so craters may have been erased. With these limited means of estimating the age of the surface, the oldest part is believed to be in the southern hemisphere. The surface there would be about 3.8 billion years old. In the northern hemisphere, the landscapes are dominated by large plains that would have appeared later, after the last waves of bombardment by asteroids. It is believed that after its formation, for about 400 million years, that would be 4.5 to 4.1 billion years ago, Mars had a dense atmosphere, which formed as a result of asteroid and comets impact and gases escaping from the mantle of the planet. This early atmosphere would have been much denser than ours on Earth, implying higher pressure, and under these conditions, the water vapor in the atmosphere could have condensed into an ocean, possibly even a global ocean, but one that existed at high temperature, a little bit like in a pressure cooker. Slowly, over millions of years, this large body of water started to cool down, and this could have opened the first window for the possible emergence of life around 4.4 to 4.3 billion years ago. But this is purely speculative and based on modelizing. There is no direct proof of it. In any case, this early atmosphere would have lacked stability, because as the planet kept cooling down, it would have escaped into space or become incorporated into the surface. After liquid water and high pressure, the atmosphere would have become thinner and thinner, and the planet increasingly cooled as a result, turning water into ice. The following 400 million years, from 4.1 to 3.7 billion years ago, saw new drastic changes. Bombardment by asteroids could have kept happening like on Earth, and the southern hemisphere, the surface in the southern hemisphere, would date from this period. Like on Earth, Mars probably has a liquid core made of primarily metal. Metals tend to converge to the center of planets due to their higher mass. The core is covered by a mantle and a much thinner solid crust. In average, this crust today would be around 50 kilometers thick, to be compared with 40 kilometers on Earth. Once again, this is an estimate that looks possible, reasonable, but contrary to Earth, it could not be proven directly and by multiple methods. But at the time, 4 billion years ago, this crust was much thinner, and the planet had a period of intense volcanic activity. Great volcanoes appeared. After our landing, we will pay a visit to one of them, Olympus Mons, and fracturing of the surface made a large rift valley system appear. As a result of this volcanic activity that poured gases and ashes into the atmosphere, the planet would have stopped cooling down, because the thicker blanket of gases trapped more solar heat, a greenhouse effect. At this point, clouds probably developed, and with them, precipitations running to the ground. This could explain the valleys that were possibly dug by running water billions of years ago, by erosion. And at the time there could have been also lakes forming in basins and craters. Maybe also an ocean covering the north of the planet. A clue that points to such a scenario with the existence of an ocean, or at least running water, is the analysis of rocks on the surface by rovers. They indicate the presence of clay minerals that typically form by prolonged exposure to groundwater. During this second period, another window for the possible emergence of life, the second one, theoretically opened. There was liquid water, an atmosphere, and also maybe a magnetic field around the planet like on Earth. The inside would have been in motion like on Earth, creating a magnetic dynamo that would have shielded the planet from radiation. In theory, this would make several of the conditions that allowed the appearance of life on Earth possibly present on Mars at the time. But again, these conditions didn't last more than a few dozen million years. Mars is a smaller planet than Earth, and it cooled down faster. As a result of it, the magnetic dynamo would have shut down, and the magnetic field would have disappeared. But more preoccupying for the possibility of life at the surface is the fact that atmospheric conditions continued to change. With its smaller mass than Earth, and without a magnetic field, Mars kept losing its atmosphere that dissipated into space millions of years after millions of years. What remained of the atmosphere started to cool down again, and with the accumulation of gases like sulfur poured by volcanoes, rains would have become increasingly acidic along a period of 800 million years, until about 3.6 billion years ago. Once again, this hypothesis is supported by the analysis of soils that were apparently altered by acidic groundwater. As the temperature went down, much of the water would have frozen, possibly under the surface. Bombardments by asteroids that had become less and less frequent over hundreds of millions of years almost came to a halt, like on Earth at the same time and in the rest of the solar system. Maybe punctually there were still asteroid impacts that melted huge quantities of subsurface ice and caused catastrophic floods that could only be short-lived because the water was reabsorbed into the ground and frozen again. After 1.5 billion years of catastrophic reverses in its appearance and atmosphere, Mars would have then entered a period of relative stability that continues to this day. Stability in the sense that there were no more large-scale geological changes or climatic changes. The surface of Mars was now dry, not much stayed of its previous atmospheres, and the new atmosphere has become so thin that there is very little pressure at the surface, so few that water vaporizes instantly at the surface. There can no longer be a liquid water. Over 3 billion years, there was still erosion with powerful winds. Occasionally, volcanoes appeared and modified the surface, like they do on Earth. But there doesn't seem to be plate tectonics like on Earth, and the face of Mars may not have changed radically for a very long time now. Seen from space, it has this red color that comes from the oxidation of iron. It is rust that gives Mars its name of red planet. The poles remain covered in ice, and the size of these ice continents at the poles probably varies over very long periods, depending on the distance from Mars to the Sun. I will tell you more about the conditions at the surface, but it is now time to land because we have reached our destination. We made this journey quickly, but for astronauts it will take months. Astronauts have already spent extended periods of time in space, including more than the time necessary to reach Mars. But it was in space stations that stayed on a low orbit around Earth. The psychological burden of knowing you are traveling further and further away from your planet in a potentially dangerous adventure in an environment where only technology can keep you alive, this cannot be looked over. This probably recreates the experience of the explorers who left Europe by sea in the 15th and 16th centuries, with their crews at the mercy of unpredictable oceans for months. There were situations of mutinies or despair. Now, this human factor can certainly be overcome by selecting highly trained astronauts and making sure their group dynamic works for the mission. But the psychological and social dimension of such a journey, it brings challenges that cannot be fully eliminated. And then there are biological, physical difficulties. Human bodies have not evolved for life in space, and especially in a zero-gravity environment. It is not just the loss of bone or muscle when we don't need to compensate for gravity for an extended period of time. There are other aspects that affect metabolism and the way our bodies heal. For example, it would be more difficult to treat a fracture without gravity. And this is also something astronauts would need to pay attention to. They could not really afford to hurt themselves. But the biggest medical issue in space is certainly radiation. On Earth, we are shielded from radiation by our magnetic field and the atmosphere. The radiations we talk about here are streams of tiny particles, bits of atoms, or of energy that exist in space or come from the Sun. The Sun ejects them constantly in every direction, and they travel through the solar system. This is a big problem for extended stays in space, because it is hard to fully shield against them, including inside spaceships or stations. One day spent in the International Space Station, for example, is equivalent to roughly 10 sessions of chest X-rays. If it is for a day or two, there are no measurable consequences. But when it is for months or years, the damage to the DNA, to eyes, to the immune system can become concerning. It is more than enough to significantly raise risks of cancer, and the ISS is far from being the worst place in space. It is on a low orbit and still within the Earth's magnetic field. So traveling further in space will imply higher doses of radiation. An even more insidious effect of radiation exposure is that it may affect cognitive function over time, making astronauts maybe less able to respond to unforeseen circumstances or stressful situations. So, what can be done to minimize the problem of radiation? There are vests under development made of materials that are efficient at blocking free particles like protons. For example, vests made of polyethylene. Polyethylene is easy to make, it's a plastic. We use it all the time. This is the material of bottled water. There are radiation sensing instruments that could alert astronauts when they go through a place where radiation is more intense, and they could move to a part of the craft where they are better shielded. Metals that make the hulls of spacecrafts are not good at stopping radiation, but other materials are. Apart from polyethylene, hydrogen works well, and it would be possible to integrate hydrogen-rich materials into the spacecraft's structure, or maybe just line the walls with water tanks. Now, these options also raise issues of weight, because all this has to be sent into space. Another solution being explored by scientists, and it sounds a lot like science fiction, is to give the craft its own electromagnetic field, generated by a device on board the craft. It is probably for the long term, and it creates other problems like the energy necessary to make it work constantly. But that would be an ideal long-term solution to the problems of radiation for space travel. Because until such a solution is found, long-haul space travel with astronauts will be hard and a direct threat to their health. One day in space, outside the magnetic field of Earth, is equivalent to about 700 days on Earth when it comes to the dose of radiation received. It's almost like 2 years in a single day. In other terms, in 1 month in space, outside the Earth's magnetic field, astronauts receive almost the equivalent to a lifetime of radiation on Earth, if they are not protected. At this point, the issue of shielding against radiation is one of the biggest stakes for scientists who work on future manned missions to Mars or beyond. But we have now reached the proximity of Mars, and the first leg of our trip is done. Sometimes there are storms of dust on the planet that can reach global dimensions and completely hide the ground. This is one of the difficulties of the harsh environment we will find at the surface. But not today. Through the very thin atmosphere of the planet, we can directly see the ground and its variety of plains, craters mainly in the southern hemisphere, mountains, rifts, all in various shades of red to brown, except the white caps of ice at the poles. These caps are primarily water ice, but not only. They also contain frozen carbon dioxide. Like Earth, Mars has seasons, because the planet rotates on an axis that is not perfectly perpendicular to its orbit, so it does not always present the same side to the Sun. When it is summer for one hemisphere, for one pole, that is to say, the pole receives direct sunlight, it is winter for the other one that stays in the dark for months. Without an atmosphere that regulates temperatures like on our planet, the dark pole becomes extremely cold for months, so much that carbon dioxide in the atmosphere freezes and falls to the ground. This covers the dark pole with a layer of carbon dioxide ice. But then, when the summer arrives, sunlight sublimes carbon dioxide. That is to say, it turns it instantly from solid to gas. Carbon dioxide liberated as gas brings dust with it in the atmosphere, and clouds form, clouds that look like cirrus clouds on Earth. Until the next change of season, when carbon dioxide freezes again and falls back to the ground. We will keep exploring the surface, but now let's land. We will do it like probably the first human missions will, landing in a rocket that will be able to take off at the end of the mission, return to the spacecraft left in orbit around the planet and start the trip back to Earth. A dozen small crafts have already landed successfully on Mars since the 1970s. There was Mars 3, sent by the Soviet space program, and Viking 1 and 2 by NASA. Then there was a long period when funding issues and other priorities put missions to Mars on hold. They resumed 20 years later, in the 1990s, with the appearance of rovers like Sojourner, Opportunity, Curiosity, and more recently Perseverance, which landed in February 2021. Between these missions that have collected samples, sent images from the ground, and the cartography made by probes in orbit, our knowledge of Mars has increased, has improved dramatically in the past 40 or 50 years. And clearly between these successful missions and the various long-term projects for manned missions from public and private agents that exist at the moment, Mars is a hot topic in the world of astronautics. A human mission is unlikely to take place this decade, but the next, why not? And this raises the questions of knowing whether it is worth it or how much it would cost. Because apart from the risks of failure and the huge complexity, an obvious limiting factor is the cost. It is estimated to roughly $500 billion. This is a lot, or not that much, depending on how you look at it. If you compare it to the world's economy, $500 billion is not that much. The world's GDP is 87 trillions. So $500 billion would be 0.6% of 1 year of the world's economy. In other terms, it is equivalent to 2 days of economic activity on Earth. As a species, the perspective to try and go to another planet for the first time ever, for the equivalent to 2 days of work, it doesn't seem that much. And it can also be argued that this spending is also an investment for a part. This is the kind of projects that need research in materials, processes, fuels, equipments of all sorts that could have other beneficial uses. But still, this amount is well above the budget of any space agency or private investor. And it would certainly not be profitable financially. There are resources that could be exploited on Mars by a human community living there, like water, metals, and maybe many other materials to be discovered. But there is probably no treasure to find. It would be for the sake of knowledge, for science, for the challenge itself, or the perspective to one day establish a permanent human presence on Mars. It has been argued that this last point made sense as a species for humankind. A presence on different planets strongly reduces the risk of extinction, if we wish to consider this a goal. Because apart from that, there are plenty of places on Earth that are currently unpopulated by man, and that would be much easier and cheaper to colonize, like the poles and Arctic regions, deserts, or even the bottom of the seas. Each are inhospitable, but they are still way more welcoming than Mars for us. Even in the terrible cold and lack of vegetation of the Antarctic, for example, where the only human presence is scientific basis, at least there is air to breathe. There is pressure, so you can go out without a pressurized suit, and the temperature is actually almost pleasant if you compare it with Mars. The atmosphere is too thin to retain heat at night, and it is farther away from the Sun than Earth, so the average temperature is minus 60 degrees Celsius, which is minus 80 degrees Fahrenheit. At best, the temperature near the equator during the day can rise up to 20 degrees Celsius, 70 Fahrenheit. It doesn't sound too bad, but in the same location, the temperature at night will drop to minus 73 Celsius, minus 100 degrees Fahrenheit. There is no place on Earth where the temperature varies by 100 degrees in a single day. Add to this the absence of air, the atmosphere is 100 times less dense, and it is 95% carbon dioxide, so there is nothing to breathe for us. The problem of radiation, the dust storms that can rage for weeks. This is actually very harsh, and any human community would have a precarious situation, living only thanks to their equipment. They would probably need to find shelter underground, or at least under anti-radiation domes, and they would desperately need to find water from which they could extract oxygen and irrigation for food production. They would also need to produce energy, probably with solar panels, and this is also a risk if the sun is hidden by dust for an extended period of time. They would have to pressurize the place where they live. These represent many elements of risk, and they could not afford to fail on any of them. Now, for the same amount of funding, it would be so much easier to create an entire underground or underwater city on Earth that could exist and function completely cut from the rest of the world. It doesn't sound useful, and no one is going to invest in this, but if the argument in favor of establishing bases on Mars is to gain living space or compartment humanity to protect it from extinction, it doesn't really work that well, considering that it could be done on Earth. But still, the challenge is fascinating, I think, and I hope a human mission to Mars will one day leave Earth and succeed. One of the interesting questions it could answer would be the presence of traces of life on the planet, even if it is long extinct or asleep. If life appeared at some point on another planet of the solar system, then it would strongly suggest that the conditions that allow the existence of life are not that extraordinary. That would be a powerful argument in favor of the existence of life in multiple locations, multiple places in our galaxy. But a base and a few scientists look absolutely possible, however difficult it is, in a not-so-distant future. Now it is not forbidden to dream, and longer term, the concept that has circulated since the 20th century is the idea of transforming Mars or other planets to make them more similar to Earth and habitable by man and Earth-like life. As you know, this is called terraforming. What is terraforming, and is it just a dream or something that could happen for real? The concept appeared in science fiction in the 1940s. It is not that recent. The first notable scientific article about it was written by an astronomer, Carl Sagan, in 1961. And in this article he proposed a theoretical way of transforming the planet Venus to make it habitable. At the time, it was known that Venus had a very dense atmosphere that created a powerful greenhouse effect, and it kept temperatures at the surface at levels that were unbearable, hundreds of degrees. The composition of the atmosphere was roughly known. It had water, nitrogen, and carbon dioxide. So he proposed the idea of seeding this atmosphere with algae. It is so dense that algae would have stayed in suspension. They wouldn't have fallen to the ground and be incinerated. Algae would have converted the components of the atmosphere into organic compounds by feeding on them, especially carbon dioxide. This would have progressively removed carbon dioxide from the atmosphere and reduced this greenhouse effect until temperatures dropped to more comfortable levels. And the carbon would have remained captive in a blanket of matter that would have fallen to the surface. The oxygen would have risen to make the air breathable. That was clever, but later discoveries showed that it couldn't work because the clouds of Venus are very rich in sulfuric acid that would have destroyed algae. And another problem, even more insurmountable, was that the atmosphere was just too dense. Algae would maybe break carbon dioxide into carbon and oxygen, but oxygen would have stayed high, whereas pure carbon would have fallen down to the surface, be incinerated, and through combustion would have returned to the atmosphere as a gas. Sagan also proposed a terraforming project for Mars in the 1970s, and because it is certainly the planet most similar to Earth in the solar system, the concept of terraforming Mars has stayed around for decades. As we saw earlier, it is not impossible that Mars had an Earth-like environment in its history long ago, with a thicker atmosphere and abundant water, possibly liquid water. If the mechanisms that made this atmosphere change happened, they could maybe be reversed. I told you before about the likely reasons that made Mars lose most of its atmosphere. There is no magnetic field, so solar wind tends to erode the atmosphere by carrying it away. Then there is the lower gravity than Earth. Mars has 60% less gravitational pull at its surface. Something that weighs 100 pounds on Earth weighs 38 pounds on Mars. So people walking on the surface could not make big jumps like astronauts on the moon, but they would definitely feel lighter than on our planet. It also means that the atmosphere is less bound to the planet than in the case of other more massive planets. And finally, the last reason for the loss of this atmosphere is that when there is carbon dioxide in an atmosphere and water is present, it tends to react with rocks at the surface to form carbonates, which are solid salts. So this tends to draw atmosphere off and bind it to the surface. This happens on Earth, but due to volcanic activity that ejects new gases into the atmosphere, there is a kind of balance, and the Earth's atmosphere doesn't get eroded by its absorption into the surface. So between these various effects, Mars' atmosphere was probably, in the past, carried away into space and absorbed by the planet itself. These problems are due to the mass of Mars, the lack of enough volcanic activity, and the absence of a planetary magnetic field. These problems cannot go away easily. This is what Mars is. And for these reasons it looks complicated to give it an Earth-like atmosphere. Because even assuming it could be done, technically and financially, this atmosphere would be unstable and would need constant maintenance, constant readjustments to stay in place. It would have to be replaced artificially, as it tends to get thinner without intervention. There are other technical problems. In order to be habitable, this atmosphere would have to be heated. But Mars receives less light than Earth from the Sun because of the distance. The light level is about 60% of Earth only. So if an atmosphere with the same composition and density as Earth was created, with the same greenhouse effect that retains heat, it would still be insufficient to raise the temperature above 0 degrees Celsius, and water would stay frozen instead of becoming liquid. And then, even if all of this could be overcome, the soils are toxic for us. They contain a lot of chlorine, too much to make them proper for agriculture. They would also have to be chemically modified. All of these problems, and there are others, actually have solutions that are theoretically possible and often within our technological reach. But in practice, it clearly looks undoable for the moment at the scale of an entire planet. We just don't have enough energy and the possibility to send the huge equipment necessary to Mars. But let's imagine we tried. What could be the methods employed to terraform Mars? The starting point would have to be to generate a greenhouse effect that is mostly absent at the moment by injecting gases into the atmosphere. These gases would trap solar heat near the surface and help start a process of global heating that could one day make water at the poles and underground melt. They would also increase pressure and make it more bearable for humans. At the moment, the pressure is just 1% of Earth pressure. So a pressurized suit is absolutely necessary. But if this pressure reached just 25 or 30% of Earth, it would already be possible to go out without a suit. Just an oxygen mask would be sufficient. There are compounds with a significant greenhouse effect, like ammonia and hydrocarbons, that are abundant in the solar system and could be imported to Mars. We know where to find them, for example, on the moons of Jupiter. But these compounds are relatively light, and it could be hard especially at the start, to make them stay around the planet. Another option would be to release gases with very powerful greenhouse effects into the atmosphere, like fluorine compounds. This includes the famous CFCs that became known for attacking the ozone layer on Earth. But they also are very powerful greenhouse gases. In fact, they are thousands of times more powerful than carbon dioxide. Fluorine is present in Mars crust in higher quantity than on Earth, as far as we know. So an idea could be to manufacture these compounds from the materials present in the soil and release them into the atmosphere. Or, alternatively, send rockets with payloads of compressed CFCs. When it comes to warming the planet, a proposed solution would be to use orbital mirrors to redirect more sunlight to the surface. They could also be targeted at the poles and their layer of solid carbon dioxide to try and sublimate it and help kickstart a greenhouse effect. Another necessity would be to oxygenate this atmosphere if it gets dense and hot enough. Science fiction often uses the idea of seeding the planet with algae or vegetation in general. This could help, but this is not such a good solution because the net production of oxygen by terrestrial plants is quite small, even on Earth. Plants reabsorb oxygen at night. And in fact, on Earth, more than 2/3 of oxygen is generated by the oceans. Liquid water would be probably necessary to fill the atmosphere with oxygen, and vegetal life that can initially resist extreme conditions of low pressure and cold would have to be introduced. Or an alternative solution would be to create oxygen from water in industrial plants. As you know, oxygen is the main component of water with hydrogen. And finally, if all of this can be sorted out, there will always be the problem of Mars' inability to retain its atmosphere. So as a solution, the idea of creating an artificial magnetic field was proposed, which in theory could be achieved with superconducting rings built around the planet in which electric current would constantly circulate. At the scale of a planet, this is of course very theoretical. So as you see, the terraforming of Mars is not for tomorrow, or even the day after tomorrow. But at the end of the day, technical solutions are not completely out of reach. It could become a viable project in the future if mankind had considerable sources of cheap energy at its disposal, way more than today, but with equipment that could harvest the sun's energy or generate it through fusion. It is not completely unthinkable in several generations. Before we leave Mars, I told you we would visit a volcano. Mars may be smaller than Earth, but it is home to one of the largest and tallest mountains known in the solar system, Olympus Mons. Olympus Mons is an enormous shield volcano. That is to say, a volcano that has grown a very wide base made of the lava it has ejected along its history. Olympus Mons has a surface as big as Italy or Great Britain, and its peak reaches 26 kilometers high, or 16 miles, That's more than twice Mount Everest. It is believed that such a large volcano could appear because of the lack of plate tectonics on Mars. On Earth, a lot of the energy and pressure under the crust is released in rifts between plates, and volcanoes are not eternal. They are parts of plates that move and at some point may disappear in the very, very long term. But when this mechanism doesn't exist, a volcano can stay in place and keep releasing lava for hundreds of millions of years. This is probably why and how Olympus Mons could reach such a size. And this is interesting because if lava keeps nearing the surface on Mars, and assuming there are pockets of water trapped underground, then in some particular locations there may be liquid water under the surface, water heated by geothermy. There are so many other interesting things to say about Mars. It also has satellites, and we are at an exciting moment historically when it comes to space exploration. After the initial exploits of going to the moon and sending probes to the various corners of the solar system in the 1960s, space exploration had slowed down in the following decades. But there is a resurgence happening at the moment with different actors. There is NASA, private companies, China, the ESA, Russia, Japan. Many of the missions and projects planned are collaborative. Maybe not with China, but in general they are. It still may seem painfully slow when you follow space news on a daily basis. These projects take years, but on a historical scale, it seems we are returning to the kind of excitement there used to be in the 1950s and the 1960s, and I'm happy about it. As you know, Jupiter is the largest planet in the solar system, and it is visible to the naked eye on many nights. The first planets from the Sun in our system are rocky: Mercury, Venus, Earth, and Mars. Beyond the orbit of Mars begins the realm of gas and ice giants, planets that do not have a well-defined hard surface, but are giant balls of gas, denser and denser as you approach their core. And it is believed that underneath all these layers of increasingly hot gases, they have a solid core where metal dominates. These include Jupiter, Saturn, Uranus, and Neptune. But rocky bodies can still be found beyond Mars, and there are many of them. Some float in a region called the asteroid belt between the orbits of Mars and Jupiter, including fairly large ones like Ceres or Vesta, that are not large enough to be classified as planets, but they follow their own orbit around the Sun. And beyond Neptune, there is also an even larger asteroid belt, the Kuiper belt, that includes Pluto or Eris. And in between these two asteroid belts, in the region of the gas and ice giants, there are many, many rocky and solid bodies of all sizes that have been captured and turned into satellites by these gas giants. Jupiter has dozens of satellites. Some are called moons because they are larger, and due to their size, they tend to adopt a ball spherical shape. Others are smaller asteroids, sometimes a few miles across or less, all the way down to small rocks and dust. Saturn has so many small objects in its orbit, and they are so brilliant that they form visible rings. Jupiter also has rings, but they are less large and less dense, which is why they are more discreet. Along our cruise, we will land on several of the larger satellites, including the 4 main ones that are called the Galilean moons of Jupiter, because they were observed for the first time with a rudimentary telescope by Italian astronomer Galileo in the 17th century. But first, let's go to Jupiter. In our last cruise to Mars, I told you about the distance and how an itinerary could be decided based on orbits and the distance from Earth to Mars. Because the distances between planets are constantly changing depending on their own movement along their orbits. Sometimes they can be aligned on the same side of the Sun, in which case they are closer, or they can be on either side of the Sun, and in that case the distance is much more. The same applies to travel from Earth to Jupiter. When the two planets are at their closest point, the distance is 365 million miles, almost 600 million kilometers. At its farthest, it is almost twice as much. Now, to get a sense of distances inside the solar system, let's bear in mind that Earth is actually much closer to the Sun than it is to Jupiter. The distance between Earth and the Sun is about 93 million miles. And to express astronomical distances in a simpler way, an unit, the astronomical unit, was defined. One astronomical unit is equivalent to the distance between our planet and the Sun. So, by definition, Earth is one astronomical unit away from the star, and Jupiter is 5 times farther, precisely 5.2 astronomical units, meaning that the planet and its moons receive less solar energy, and also that light from the Sun reaches them later than Earth. The sunlight needs only 8 minutes to reach Earth, but it needs 43 minutes to reach Jupiter. Being farther from our star, Jupiter also has a much longer orbit than Earth, and it is slower on its orbit. Actually, the farther planets are from the Sun, the slower they tend to be on their orbit. This is an effect of gravitation. The fastest planet in the solar system is also the closest to the Sun, Mercury, and it travels in space at almost 50 kilometers per second. That's equivalent to more than 100,000 miles per hour. Earth travels at close to 30 kilometers per second. Jupiter is significantly slower, only 13 kilometers per second. And so, between the longer distance to close one revolution around the Sun, plus the slower speed, Jupiter needs a lot more time to complete a full revolution and orbital journey around the Sun. It needs about 12 of our years. The one characteristic that makes Jupiter stand out in the solar system is obviously its large size. It is still a very small body compared with the Sun, less than 1,000th of the Sun mass, but it is much bigger than any other planet, and even bigger than all the other planets of the solar system combined. Its mass is 2.5 times the mass of all the other planets together. We will pay more attention to Jupiter later, including its composition and formation history. But for now, we are approaching its periphery, and it is time to take a look at its bigger moons. As I told you, there are 4 of them: Io, Europa, Ganymede, and Callisto. They are all very different from one another, and we're going to make a stop on each one. These 4 moons are called Galilean moons, as we said earlier, because they were first observed 4 centuries ago by Galileo Galilei. At the time, they were the first objects found to orbit a planet other than the Earth, and their discovery was a big deal because it challenged views on the nature and the shape of the cosmos. I will also give you a link in the description to my story about cosmology and the evolution of descriptions of the universe over time. Jupiter was always well known since the dawn of human times, because it is visible in the night sky. After the Sun and Venus, it is the 3rd brightest object. But its satellites are way too small to be visible to the naked eye. So only the use of a rudimentary telescope made the observation possible. We will see their history, their orbits, and how these orbits are in resonance with each other. But for now, let's approach the first one, Io. Io is the closest to Jupiter of the 4, the innermost, and the 3rd largest of Galilean moons. It is slightly larger than our moon, and it is a very dense body, the densest of any moon in the solar system. It also stands out for its volcanic activity, which is extreme. There are more than 400 active volcanoes at its surface, and some of them produce plumes of sulfur that climb as high as 300 miles, that's about 500 kilometers. This makes the surface of Io constantly ravaged by eruptions and clouds of gas released by the volcanoes. To us, it may look almost like a representation of hell. So why is Io so geologically active? Because of the presence of Jupiter and other moons, but especially the mass of Jupiter. It causes a phenomenon called tidal heating. What is it? You know that rocky planets and moons in the solar system are very hot inside. Their crust at the surface solidified because it became cooler over time, and with this cooling process over millions and millions of years, the crust tends to become thicker. But there is still intense heat inside that remains trapped as a consequence of mainly two phenomena. First, there is the creation of these bodies when a lot of smaller asteroids and dust collided to form them. These collisions generated a lot of energy, a lot of heat, that dissipates very slowly because it is accumulated inside, under the crust. And then there is a second and more important phenomenon that happens inside planets: radioactive decay. Unstable large atoms like uranium and a few others fission. They suddenly reorganize their particles into smaller atoms, and in the process they liberate energy and free particles that do not get stuck into the new atoms. This fission of unstable atoms tends to make them disappear over time, but it takes hundreds of million years for some of them, and there are less and less, but they still maintain a residual presence. Their decay, this radioactive decay, because it liberates radiation, is a natural phenomenon, and it keeps heating rocky planets from within, or satellites. This radioactive decay also happens inside the Moon, our Moon, and there is most probably the same mechanism inside Io. But in the case of this body, a much bigger contributor to its internal heating is the mass of Jupiter nearby and the gravitation forces that result from it. As Jupiter is very massive, the side of Io that is closer to the planet has a slightly larger gravitational pull than the opposite side. And due to the presence of other moons around Jupiter that influence its orbit, the orbit of Io is not perfectly circular. It is elliptical. Depending on its position, the Moon can be closer or farther from Jupiter. This means that as the Moon is in motion, it is subject to different intensities of gravitational pull, and this force causes distortion of Io's shape, as if you had an orange in your hand and you would squeeze it, press it in different parts. It is not going to destroy it, but it is going to flex its interior. This happens to Io, and at the scale of a rocky body like this one, it means constant friction inside the planet, which generates heat. And this is tidal heating, the gravitational pull of a large body that is strong enough to distort its satellite, as the satellite follows an elliptical orbit and moves from being closer to being farther constantly. More than any moon in the solar system, this hits the inside of Io due to friction, and this is what drives its intense volcanic activity. There is a lot of energy waiting to be released, and the constant flexing of the Moon makes its surface prone to moving and breaking. Apart from volcanoes, more than 100 mountains have been identified that have been uplifted by compression of the crust. Io may be way smaller than Earth, it is about the size of the Moon, but because of that, it has mountains higher than Mount Everest. And in between these spectacular mountains, there are rocky plains, and here again, volcanism influences the Moon. Because lava is constantly released, Io has a relatively young surface that gets renewed with new material coming from the inside of the Moon. On telescopes and cameras, Io appears in shades of yellow, white, black, red, even green, that correspond to different types of sulfur. All the surfaces on moons and planets tend to have visible craters, the remains of asteroid impacts, but Io doesn't, because the surface flows of lava that can sometimes be several hundred miles long, they constantly renew its surface and erase traces of impact. There is a very tenuous atmosphere on the Moon, first because it is not massive enough to retain a thick atmosphere, and second because Jupiter is close, as we said, and tends to steal gases from Io due to its gravitational pull. It is estimated that the atmosphere loses a ton of matter per second due to this. This is not that much on such a scale, and the faint atmosphere gets renewed by gases released by the volcanoes, mainly sulfur dioxide. As soon as they are released by the volcanoes, these gases tend to freeze due to the intense cold. The inside may be very hot, but Io is much further from the Sun than we are. There is no atmosphere to retain heat, and when the Moon passes in the shadow of Jupiter, it does not receive any solar energy at all. But when Io is exposed to the Sun, a superficial layer of this sulfur dioxide sublimates, which means that it returns instantly to gaseous state, and this is what maintains a bit of atmosphere. There would be much more to say about Io, but let's change setting and move to a second moon, one that also has exciting features, Europa. Europa presents a few cracks and streaks on its surface, but it has the smoothest surface of any known solid body in the solar system. There are very few craters or mountains. It is the smallest of the 4 Galilean moons, and it is slightly smaller than the Earth moon. Why the smooth surface, and what is Europa made of? Its density suggests that overall its composition is similar to terrestrial planets of the solar system. Primarily, it is made of silicate rocks, that is to say, large quantities of silicon and oxygen, and it is likely that its core is rich in metal, especially iron. But the smooth surface and other observations strongly suggest that the outer layer of the Moon is made of water. This layer would be about 60 miles thick, 100 kilometers, and so the surface of Europa would be essentially frozen water ice. And the question is, if temperatures are higher under this layer of ice, there could be an ocean of liquid water underneath. But first, what is the dynamic of this solid surface? Because it features a lot of darker streaks of lines that are visible from space. The most likely explanation is that there were, and there continues to be, eruptions of ice between plates. The ice under could be warmer and erupt, causing the crust to spread open and expose warmer layers beneath. In a sense, this is a phenomenon that reminds of oceanic ridges on Earth between plates, even though in this case the environment and material involved are completely different. So, this is compatible with the existence of a subsurface ocean. If the ice under the crust is warmer, there may be a point where the temperature is high enough for water to become liquid. What would heat this ocean? High temperature from the inner layers of the moon, and here again, like for Io, this phenomenon of tidal heating that we just discussed. It may contribute to warm up water. Surface temperatures are extremely cold. At the equator, we are talking about minus 160 degrees Celsius. That's minus 260 degrees Fahrenheit. Again, because there is barely any atmosphere, and Europa receives less sunlight than Earth. At the poles, the temperature plunges to minus 220 degrees Celsius. And it also passes in the shadow of Jupiter regularly for several of our hours. Europa takes 3.5 days to complete a revolution around Jupiter. So for several hours in a row, it is plunged in complete darkness and no longer receives direct sunlight. At this moment, the surface temperature at the poles must drop to levels that are not that far from the absolute zero. So in any case, the ice crust is thick, at least several miles or several kilometers. But there is an ongoing debate about how thick it is. And this is important because if it is thin, relatively thin, there could be exchanges between the liquid ocean and the surface from time to time. When these streaks form, or maybe when an asteroid hits the moon and breaks the crust. Whereas if the ice crust is dozens of kilometers thick, the hypothetical liquid ocean and the surface would be totally separated. But in any case, the existence of liquid water is likely on Europa, and that could possibly be a lot of water if the water layer is about 100 kilometers thick, which is the dominant theory at the moment, and even if half of it is solid ice, that would make more liquid water than on Earth. This is absolutely huge. So if there exists a place with water and heat coming from the inner layers of the moon, then this raises the possibility of the existence of life on Europa. And this is why this moon has had a high profile among the moons of Jupiter in the past decades, since various discoveries were made. Discoveries about Europa itself, its composition, and discoveries on Earth, in the abyss. We know that life is possible in complete darkness, with food chains that start with bacteria able to resist very high pressure and temperature. Bacteria that can feed on chemicals released by the Earth's crust. And then bigger and more complex organisms that feed on these bacteria. So maybe a similar phenomenon exists thousands of kilometers under the extremely cold ice crust of Europa, in the darkness and high pressure of its subsurface ocean. This is just about theoretical conditions for life that could be present on the moon. There was never any proof that it exists, but there are long-term projects for missions that could go to Europa to search for evidence of life. Now, even though life exists somewhere on Europa, it doesn't mean its surface would be welcoming to human beings at all. Apart from the cold, radiation is very intense due to the lack of atmosphere and the lack of magnetic field like the one we have on Earth. And Jupiter, which is close, emits heavy radiation. So any manned mission would have to leave behind very heavy anti-radiation walls or buried deep down in ice under the surface to find protection against this radiation. Europa is the smallest of the 4 Galilean moons, as I said. Now let's go to the largest and the third one outward from Jupiter, which also has yet again a completely different environment, Ganymede. I told you that Europa needed 3.5 days to orbit Jupiter. Ganymede needs 7 days. And actually there is an interesting interaction between these 3 satellites, Io, Europa, and Ganymede, and the planet Jupiter. The 3 satellites are in orbital resonance. Their orbital periods are synchronized. Europa needs exactly twice as much time as Io to orbit Jupiter, and Ganymede twice as much time as Europa. So that is exactly 4 times as much time as Io. They are in an orbital resonance of 1, 2, 4. What is this concept of orbital resonance, and why does it happen like this? As you know, all planets in the solar system orbit around the Sun, which has by far the biggest mass of any object in the system. Actually, the Sun represents more than 99% of the matter in the entire system. But the Sun is not the only body that influences orbits. Even though they are smaller, planets also have an influence over each other. That depends on their masses and the distances between them. So it is true to say that the Sun determines orbits, because it is by far the biggest factor. But if we go a bit further into detail, it is not 100% accurate. Other bodies, every body, also has a small influence on every other one. A large planet can distort the orbit of a smaller body and eventually modify it so much, revolution after revolution, that this object may be placed on another orbit or even expelled from the solar system. This probably happened many times along the history of the solar system, and there is a phenomenon that can greatly increase the influence between 2 bodies in space. It is when they exert regular, periodic influence on each other. For a comparison, think about when you are pushing a child on a swing. The swing has its own frequency, but even without touching the ground, the child can amplify the movement by pushing with his body, because this pushing acts in a periodic repetition, and it has a cumulative effect on the motion. On a bigger scale, this is what can happen between planets, or the moons orbiting a planet. And this is this phenomenon which is called orbital resonance. Very often this mutual influence is unstable. The 2 bodies exchange momentum, and it shifts their orbits progressively to the point that the resonance disappears. But under some circumstances, sometimes, a resonant system like this can become stable because it is self-correcting. The exchange of momentum between bodies keeps them in a stable resonance. It is the case, for example, between Neptune and Pluto. The two are in a resonance of 2, 3. It means that when Neptune does precisely 3 revolutions around the Sun, Pluto does exactly 2. And the same kind of resonance formed between Io, Europa, and Ganymede in a ratio of 1 to 4. When Ganymede does 1 revolution around Jupiter, Europa does 2, and Io does 4. Another effect of momentum and gravitation that applies to Ganymede is that the Moon is also tidally locked to Jupiter. This means that it always presents the same face to the planet. Most moons have this characteristic. They don't rotate on themselves. It's the same with our Moon. We always see the same face, looking at it from the Earth. But now let's take a look at Ganymede itself. What Ganymede stands out for the most is that it is the largest moon in the solar system. Its diameter is only 40% the diameter of Earth, but it is bigger than the planet Mercury. It is not as massive as Mercury, though, because Ganymede is made of lighter material, lighter elements. Mercury contains a lot of metal, whereas it is estimated that Ganymede has a core of metal and rock, but is also half made of water, in different states, different types of ice. I'll come back to this. And maybe between them there could be liquid water. So as for Europa, there is speculation about the possibility of life in the oceans of Ganymede, but it looks less likely or harder to prove for several reasons. First, because the outer layer of ice is much thicker than on Europa, so reaching the liquid part looks very hard, close to impossible at the moment. And also it is uncertain whether the bottom of this subsurface ocean reaches the rocky mantle underneath. It is believed that there is another layer of ice, but not the same type that we are familiar with. On Earth, we essentially know ordinary water ice, frozen water, which forms at certain conditions of pressure and temperature. Typically when the temperature drops below 0 degrees Celsius and at sea level pressure on Earth. But if the pressure is higher, you need a lower temperature for water to freeze. Now you know that ice is a crystalline form. It means that water requires a highly ordered microscopic structure. Billions and billions of molecules become perfectly ordered, following a pattern. It almost never happens on Earth because of the conditions of temperature and pressure we have on our planet. But there are different possible crystalline forms, different patterns that water may adopt. And these different crystalline structures could be explored and studied in laboratories, showing that different types of ice may exist. Ordinary water ice is called Ice 1, and many other possibilities of structure have been identified, Ice 2, 3, 4, 5, and so on. It is believed that the inner layer of ice on Ganymede is Ice 3, which forms when liquid water is exposed to a temperature of -20 to -30 degrees Celsius, plus a pressure of 200 to 300 times the sea level pressure we have on Earth. On our planet, these conditions can only exist in a laboratory, because naturally, where there is enough pressure, at the bottom of oceans, the temperature is higher than that. And where the temperature is low enough, because -20 to -30 degrees Celsius is perfectly reachable in the winter in many parts of the world. But in that case there is not enough pressure because it is at the surface. So these conditions are not naturally met in our environment, but it seems they are in the depth of Ganymede's oceans. So at its surface, Ganymede is mainly made of water ice, but there are other elements that probably arrived as a result of impacts with smaller bodies. 1/3 of the surface is dark and covered in clays and organic compounds that are believed to be traces of impactors that collided with the Moon. Contrary to Europa and Io, the surface is quite ancient in average, because there is not much activity that renews it. But there are still grooves and ridges that are not completely explained at this point, given the structure of the Moon, but that could have appeared, maybe, hundreds of millions of years ago, when its surface was more active than it is now. Ganymede may have less chance of harboring life than Europa, but when it comes to human presence and exploration, it may be a bit more welcoming. There is less radiation because of the longer distance to Jupiter, and also thanks to a degree of protection from a magnetic field that seems to be generated, like on Earth, by the dynamo effect of a rotating metallic core at the center of the Moon. The level of radiation is still deadly, and the temperature and pressure very hostile, but with adapted protections it is not impossible to think of a human base one day on Ganymede. Out of the different moons of Jupiter, Ganymede presents a less difficult set of conditions than Io and Europa. But there is even better. Callisto. We still have a fourth Galilean moon to look at. Callisto is the fourth of them by distance to Jupiter, and thanks to this, it has the lowest radiation levels, but there are other interesting features that distinguish it. I told you that the surfaces of Io and Europa were fairly young in astronomical times, that is to say, still millions of years. But in contrast, Callisto has the oldest solid surface in the entire solar system. It seems that since its formation, there was never any kind of subsurfaces processes, like volcanism or plate tectonics, that could have rejuvenated the surface. So it never changes at all, except for impacts. Callisto has the most cratered surface in the solar system. It is completely covered in impact craters that have appeared over probably several billion years. So why is Callisto so inactive geologically? It is believed that this is due to its formation history. Callisto would have formed very slowly from the accretion of smaller rocks, but not fast enough to reach a high temperature inside. And as a result, the Moon is not fully differentiated internally. What it means is that bodies of a certain size, planets or large moons, tend to have a structure in layers internally. the heavier elements converge to the center, to the core, and various elements above it form layers that are clearly distinct in terms of chemical composition and conditions of temperature and pressure. It is the case of rocky planets like ours and the 3 first moons we just visited. This process of differentiation is never at 100%. For example, there can be movements in the mantle of a planet that can make small quantities of metals go up and reach the surface. But still, large bodies acquire an organized structure overall, one that is differentiated. But this process was very incomplete on Callisto, and it makes it the largest body in the solar system that is not fully differentiated. Elements inside are mixed up, and there are several layers made of rock and ice mixed together. Here again, the various conditions mean that the structure of ice differs depending on how deep it is inside the moon. The crust is made of ice 1, the ordinary one on Earth, but inside it is believed there is also ice 5, 6 and 7 with different crystalline structures. And under tens of miles of icy crust, probably yet again another ocean of liquid water that has been isolated from space for billions of years, since nothing ever happens on the surface of Callisto except occasional impacts that do not reach beyond the icy crust. After the Earth, Moon and Mars, Callisto is a possible target for manned missions one day. Clearly not in the 2020s or 30s. It is way farther than Mars, and there is no specific project now. But if one day men set foot on one of the moons of Jupiter, it is likely to be Callisto first. The low radiation level and the geologic stability are advantages, and Callisto could be a good base as a station for further exploration of the solar system and remote exploration of Europa in the search for traces of life, for example. Until now, we have spoken about the 4 main moons of Jupiter, but there are many more of smaller sizes that were discovered long after. You remember that Galileo observed these 4 moons in 1610. It took almost 3 centuries then, to the end of the 19th century, to start discovering more and smaller moons of Jupiter. Today, at this point, 79 moons in total have been found and named. They are called moons when they are large enough, and there are also moonlets and dozens of smaller satellites. Together with the planet, they form a system called the Jovian system. We'll take a look at some of these smaller bodies and also at the rings of Jupiter. But before, let's talk about the planet itself. As you know, Jupiter is by far the largest and the most massive planet of the system. It has 2.5 times the mass of all other planets combined. It is also probably the oldest planet of the system, the first to form, according to current models of planetary formation. These are all theories based on our knowledge of the history of the solar system and physics, not absolute certainties. But the dominant models, right now, suggest that Jupiter formed quite far from the Sun, beyond the limit called the snow line, This is the distance to an early star where it is sufficiently cold for volatile compounds like water to condense into solids. The origins of Jupiter would have started with a large, solid core, one of rock and metal, that would still exist today at the center of the planet, and around which huge quantities of gas like hydrogen and helium would have aggregated, kept together by gravitation. After a few million years, which is short at this scale, the various other planets of the solar system were not formed yet, and the system was essentially a gigantic disk of gas and dust, with a newborn star in its center. So rather quickly, Jupiter gained enough mass to absorb or satellize everything on its orbit to clean it up, and reach a mass that was already 50 times the Earth's mass. Nowadays, after absorbing more gases and rocky bodies, Jupiter is more than 300 times as massive as Earth. But because it is less dense, being primarily made of gas, it has 1300 times the volume of Earth. Now, the fact that it is a gas planet doesn't mean that it is like a cloud that could be crossed easily. The more you move towards the center, towards the core, the denser and hotter the planet becomes. Due to the mass, temperatures and pressure inside Jupiter reach levels that are way higher than at the center of Earth. And the gravitational forces that keep the planet together are very powerful. Jupiter has a composition dominated by hydrogen. It is about 3/4 of its mass and 90% of its volume, and it is so much matter that the interior is strongly compressed. This compression generates heat, and actually Jupiter emits more heat by itself than it receives from the Sun. But however massive Jupiter is, it is not enough to ignite the same reactions of fusion between atoms of hydrogen that happen inside the Sun, which is why it didn't turn into a star. We know that there are systems where more than one star forms, even though this is not the most frequent case. If Jupiter had gained more mass, it could have turned into a second star after the Sun, but the planet stayed well short of that. It is estimated that it would need to be 75 times more massive to ignite fusion. So because it is a gas planet, there is no solid surface to land on. The planet begins as a cloud of low density and becomes increasingly dense. If we were to enter this big ball after gaseous hydrogen, we would reach a layer of liquid hydrogen turned into liquid by the rising pressure, followed by another layer of so-called metallic hydrogen, another phase of hydrogen. It doesn't mean it turns to metal in the usual sense of the term, but that under such conditions, hydrogen behaves like an electrical conductor, which is why it is called metallic hydrogen. Jupiter and also Saturn would contain a lot of this metallic hydrogen form due to their large masses that compress hydrogen. Now visually, when we look at Jupiter, we also see several bands or belts of color, different colors, that are segregated all around the planet. And there is also a giant spot. These bands move at different speeds. They are made of clouds of ammonia that float in the upper layers of the atmosphere, and their movements cause strong turbulences. In its upper layers, Jupiter has powerful winds. The various bands have different circulation patterns, they move at different speeds, and their interactions create turbulence and even storms. This is what the Great Red Spot is believed to be. It is a vortex, a storm, that probably did not always exist, but became a stable feature of Jupiter's atmosphere. Jupiter being very big for a planet, the red spot is bigger than Earth, and it rotates counterclockwise, in the opposite direction to the bands of clouds. The phase of fast growth is long over for Jupiter. There is no longer much matter to aggregate, like in the early stages of the solar system. But the planet keeps attracting bodies, like comets, that are captured by its gravitational pull and fall on it. Jupiter would receive about 200 times more asteroids and comet impacts than Earth. For a long time, it was believed that Jupiter played an important role here in shielding rocky planets, including ours, from asteroid impacts, because it would have acted as a gravity well located at the limit of the inner solar system, being the first and biggest of giant planets. So Jupiter would have been like a vacuum cleaner of the system. But this view is now more disputed, because also due to its mass, Jupiter could attract more asteroids and comets to draw them from the Kuiper belt, the larger belt of asteroids that exists beyond Neptune. So this debate is still open, and it is unsure at this point whether Jupiter is such a shield for Earth. But in any case, due to its mass and age, Jupiter has the largest number of large satellites of any planet in our system, and it also has rings. These rings are not obvious like the rings of Saturn, and actually they were discovered only recently, in 1979, when a space probe, Voyager 1, explored the Jovian system. These rings are not as large comparatively as Saturn's, and they are way less bright, which is why they were not seen before. Saturn's rings contain a lot of ice that reflects light, whereas Jupiter's rings are primarily made of dust. And in between, or around these rings, there are more moons, dozens of moons. I told you earlier that Jupiter had 79 in total, so let's explore a few of them. Other Jovian moons than the four largest ones started to be discovered in 1892, and they are much smaller, so they were harder to identify from Earth. Initially they were given numbers, Jupiter 5, 6, 7, and so on. Jupiter 5 is also called Amalthea, and it is the fifth biggest moon, and the last one discovered by direct visual observation. The following ones were found by photographic or digital imaging, that is to say they were seen on photographs of space using extended exposure time, which allows to capture objects that could not have been noticed otherwise. Like other smaller moons, Amalthea interacts with Jupiter's rings. These rings contain dust ejected from the surface of these moons. Amalthea is also not large enough to acquire a spherical shape, so it looks irregular. Its maximal length is about 160 miles or 250 kilometers. Put near Earth, it would look about the size of Massachusetts or Belgium. It is believed that this moon formed far from Jupiter because its structure is light and it contains water ice. In the early stages of Jupiter's formation, the planet emitted a lot of heat, and based on the distance to Jupiter, it is very close, this moon would have entirely melted. So the theory is that Amalthea formed farther in the solar system and was captured as a satellite afterwards. Visually, the moon looks very red, which may be due to sulfur it would have collected from Io, which is also close, but this is uncertain. Amalthea orbits at only 180,000 kilometers from Jupiter, which is only a bit more than the diameter of the planet. It looks really close. So if we were to land on this moon and look at Jupiter, the planet would look huge. Imagine something 8 times bigger than the moon when we watch it in the night sky. But there is even closer than Amalthea. Jupiter 16, also known as Metis, is the innermost known moon of Jupiter. It orbits at only 130,000 kilometers, which is less than Jupiter's diameter. And it is the fastest moving moon of all. It orbits at 30 kilometers or almost 20 miles per second. This moon is far too small to be spherical. Its maximal length is 60 kilometers by a width of 40, so it looks like a big asteroid. And Metis is just in the middle of one of the rings, and this is not a coincidence. It is dust from this moon that generates the ring. When there are impacts with rocks, material can easily be ejected from Metis because of the low gravity. And there are 2 more moons like Amalthea and Metis, Adrastea and Thebe, that also have irregular shapes. And then there are 70 more smaller moons that orbit much farther from Jupiter. It is believed that these bodies had their own orbit around the Sun, like asteroids from the asteroid belt, and they were progressively captured by Jupiter. They float in space away from the rings and are only a few miles across sometimes. Some of them follow a prograde orbit, that is to say, they orbit in the same direction as Jupiter's rotation, and others are retrograde, which is the opposite. These ones travel the opposite way of Jupiter's rotation. It is well possible that more will be discovered. At this point, more than 20 of these small, irregular satellites have not been named. They were just given a number. And discoveries continue. As recently as 2020, more candidates were found on orbits that are far from the planet, and the population of moonlets could be in the hundreds. It depends where the limit size is fixed. First of all, what distance do we need to travel to go to Saturn? As I told you when we visited other planets before, the answer is always, it depends. It depends where Earth and Saturn are on their respective orbits. If they are opposed on either side of the Sun, this distance is going to be bigger than if they are aligned on the same side of the Sun. When they are at their closest distance, so on the same side of the Sun, the distance between them is about 1.2 billion kilometers. That's 750 million miles, or about 7 astronomical units. An astronomical unit is the distance from Earth to the Sun, and it is a convenient unit to compare distances in the solar system. So that gives you an idea of how far Saturn is from the Sun in comparison with our planet. By definition, we are 1 astronomical unit away from the Sun, but Saturn is almost 10 times farther, at 9.5 astronomical units, give or take, because orbits are not perfect circles. They are slightly elliptical, oval-shaped, so the distance to the Sun varies a little over time, depending on which position the planets occupy on their orbit. In other terms, our planet, seen from Saturn, would look really close to the Sun. And this is why when Saturn is on the other side of the star, opposite to us, the distance increases, but not dramatically. It increases to 11 astronomical units, instead of 7 at its shortest. If we were to travel at light speed, it would take us around 1 hour to get to Saturn. Luckily, we are traveling by the mind, so this is going to be even shorter than that. And on our way, we will cross the orbits of Mars and then Jupiter before arrival. So, as we are now leaving the Earth's orbit and beginning to accelerate, let's talk a little bit about what we will find when we reach Saturn. As you probably know, Saturn is called a gas giant, and it is the second largest planet of the solar system after Jupiter, another gas giant. Gas planets do not have a solid surface, like rocky planets. They are made of layers of gas, increasingly dense, and it is believed that at their centers there is a solid, rocky or metallic core, around which the gas accumulated during their formation process. Gas planets are kept together by gravitation. The large mass around the center of these planets pulls the gas and keeps the planet as one single body. It is believed that gas planets have to be of a certain size. They cannot be small like the size of Earth or Mars, because it takes a certain mass for them to stay in one piece. But an hypothesis is that gas and rocky planets may have similar origins. They start with a solid body, a core that appears in the formation process of a star system, in orbit around a star. These planetoids grow by absorbing smaller objects in and around their orbits over millions and millions of years. And they can also grow, sometimes, by absorbing asteroids that travel across the star system. This is how Earth and other rocky planets, Mars, Venus, Mercury, are thought to have formed. But on the orbits of Jupiter and Saturn, that are significantly farther from the Sun than these rocky planets, there could have been on top of that a lot of hydrogen, and to a lesser extent helium, that had not been absorbed by the Sun. This is the matter they would have attracted. And these floating gases, collected by the two planets that completely cleaned up their orbit, would have become the various layers of these gas giants. I am using the conditional here because even though there is a broad consensus about the main lines of the formation history of the solar system, there are also variations between models, and these models, these theories, are inherently hard to prove. It is not as if we could recreate the experience. For example, if you look at the solar system in isolation, it seems to suggest that rocky planets would tend to be located near the star. It is the case for the 4 rocky planets of the solar system: Mercury, Venus, Earth, and Mars. And further away, you would find gas giants like Jupiter and Saturn, and even farther, ice giants like Uranus and Neptune. But the observation of other star systems and the growing number of exoplanets discovered, this also indicates that other placements of planets are possible. For example, gas giants that are located near their stars. These planets are called hot Jupiters because they are close to a star. Maybe they formed away from their star and they changed orbit later, so it does not necessarily disprove the theory that gas giants appear far from stars. But this is to illustrate that debates about the formation history of star systems and the appearance of the different kinds of planets are still open. We will elaborate much more on Saturn itself, but for now we have considerably reduced the distance with the planet, and it is becoming bigger and bigger. We have passed the orbit of Jupiter, which was about halfway in our journey. The size of Saturn, and its even larger rings, is becoming very imposing. The planet is actually almost as large as Jupiter, even though it is not as massive, and by a margin. It has 3 times less matter, 3 times less mass than Jupiter, meaning that it is less dense, and we will see later why it can be almost as big with less than a third of Jupiter's mass. But before we reach the planet itself and its rings, let's spend some time exploring its moons that are not less interesting. The moons of Saturn could be a topic by itself, because they may not be as famous as its rings. But Saturn has more moons with confirmed orbits than any other planet in the solar system. In total, 146 moons. But this number raises the question of what we define as a moon. Technically, each block or even each particle in the rings of Saturn is a satellite of the planet, and there are billions and billions of these particles in the rings. These are way too small and not independent enough to be called moons. The moons I am referring to are not part of the rings. They are distinct bodies, and they have been accounted for among the 146 moons I mentioned only when they could be repeatedly observed and their orbit identified. If we lowered the bar of what a moon is and accepted smaller bodies, there could be hundreds more. But tonight we're going to pay a visit to some of the biggest. Titan, which is the largest moon of Saturn and a very big moon, the second biggest in the solar system. Rhea, the second biggest. Iapetus, the third, and also Enceladus. Each of them have different things to reveal. So let's begin by taking a look at Titan, the largest and most famous of these moons of Saturn. It is actually so big for a moon that only one is larger in the solar system, Ganymede, a moon of Jupiter. For comparison, the diameter of Titan is 40% of the diameter of Earth. So Titan is significantly smaller than our planet, but it is about 50% wider than our moon. For reference, our moon is number 5 by diameter in the solar system. Number 1 and 2 are Ganymede and Titan, as I said, and number 3 and 4 are two other moons of Jupiter, Callisto and Io. Number 6, just after Earth's moon, is yet another Jovian moon. Jovian means of Jupiter, Europa. Another element of comparison is that if Titan was not a satellite of Saturn, but had its own independent orbit around the Sun, it would be considered as another rocky planet, because it is larger than Mercury. Larger, but not as massive. Titan only has 40% of the mass of Mercury. Mercury is mostly made of iron and dense rock, whereas a large portion of Titan is made of ice that is way less dense than these materials. Despite the distance with Earth, Titan was discovered relatively early, by the mid-17th century, by a Dutch astronomer, Christian Huygens. It is quite far in comparison with the moons of Jupiter that had been discovered a few decades earlier by Galileo, about twice as far. But Titan is big for a moon and relatively shiny, with an uniform yellowish atmosphere. This helped Huygens detect and study it. A bit like the planet Venus, Titan reflects sunlight and is far enough from Saturn to be distinguished from it with relatively rudimentary telescopes. But then, for 350 years, our knowledge of Titan remained very basic, because like for Venus, its surface was impossible to see, hidden under a thick and opaque atmosphere. A lot of what is known about this moon's surface and atmosphere was discovered in the past few decades by probes, and in particular in 2004, when a probe, Cassini, approached it. It is rather uncommon for a moon to have a thick atmosphere. It can only happen when moons are large enough for their gravitation to retain this atmosphere. But we have seen that Titan was the second biggest moon of the solar system. And also, over hundreds of millions or even billions of years, they have to retain this atmosphere, because an atmosphere can be lost due to a collision with another body, or by passing too close to a planet that could steal it, or it can be carried away by solar wind, which is the flow of particles and radiations that comes out of the Sun. So the conditions are drastic, and probably for this reason, only two moons with a significant atmosphere are known in the system. There is Titan, and the other one is Triton, a moon of Neptune. The two moons are relatively big, and they are far from the planet they orbit, and also far from the Sun. Different conditions that probably explain why they have been able to retain their atmosphere. Now, other moons generally have a very faint atmosphere. It is not dense enough to be comparable to the kind of atmospheric conditions we are familiar with on Earth. Titan is really different because its atmosphere is very heavy and dense. So dense actually that surface pressure is higher than the one we have on Earth. It is estimated to be close to 1.5 atmosphere. That is to say, a slightly higher, 50% higher level than the one we are accustomed to at sea level on Earth. Something that would be perfectly bearable to human beings. The sensation of pressure would be like swimming a few feet underwater. Now, the atmospheric pressure may be livable, but the other conditions are not. The composition of the atmosphere is mainly nitrogen, at 97% of it, plus methane and traces of hydrogen. Our own atmosphere is 70% nitrogen, but we also have 20% of oxygen that we can breathe. There is no gas oxygen on Titan's surface, and so we couldn't breathe without a suit. Another major problem for human beings would be the temperature. Titan is almost 10 times as far from the Sun as Earth, and this means it only receives about 1% of the sunlight we receive. So, not much sunlight, and on top of that, 90% of it is absorbed by the thick atmosphere. Only the remaining 10% reaches the surface. Now, because the atmosphere is thick, there is also a greenhouse effect like on Earth, and this helps retain a bit of heat. But all in all, the temperature is still very cold, about 94 Kelvin, or negative 179 degrees Celsius, a temperature at which water would freeze instantly, but it would be even colder without this greenhouse effect. And yet another problem that man would have at the surface would be the constant darkness. With 1% of sunlight and a thick atmosphere hiding the sun, you are plunged almost in constant night. But let's say we have a suit with heating, an oxygen mask and lighting. What would we see at the surface of Titan? An extraordinary landscape, actually. At the same time, completely alien, chemically, but somewhat familiar by its geography. Titan is thought to have standing bodies of liquid on its surface, including rivers, lakes, and seas. Except these bodies don't contain water, because it would freeze, but liquid hydrocarbons, like methane or ethane. Titan is believed to be the only place in the solar system, except Earth, to have such liquid bodies, with a cycle of evaporation, clouds, and rain, like on Earth, except it is not water, but hydrocarbons. Apart from this cycle of precipitations, mountains and volcanoes have been observed, but not Earth-like volcanoes. these are cryovolcanoes. A cryovolcano erupts volatile materials and gases, such as ammonia, water, or hydrocarbons, all these materials that astronomers call ices. It is not just water ice. It is believed that these materials ejected by cryovolcanoes come from reservoirs under the surface, a bit like lava on Earth, but these are much colder materials and they are not rock. It has also been observed that the surface of Titan looked relatively young, because it doesn't have many impact craters. For a part, this may be thanks to its atmosphere. Like ours, a dense atmosphere eliminates small asteroids by destroying them. But it is also because there is a geological activity on Titan. It seems new material is expelled from the inside of the Moon, supposedly by these cryovolcanoes, in large enough quantities to replace surface material slowly, on a scale of several million years. But this eliminates traces of impact and refreshes the surface. One last question about Titan that was raised when this set of conditions and composition became better known is about the possibility of organic life on this moon. At the surface, this sounds very unlikely due to the temperature. But like for other moons of the solar system, like Europa, the moon of Jupiter, there could be subsurface oceans under the thick ice sheet. And in these oceans, maybe, the bricks for simple organisms, prebiotic conditions, could be present. There is no proof at all today that Titan harbors any kind of life. And if it does, it would have to be life that relies on other energy sources than sunlight, like the life forms on Earth that depend on hydrothermal vents near the ocean floors. They depend on them for the energy and nutrients that they need. But this is theoretically possible. In a weird way, Titan is considered the body in the solar system that looks the most like Earth geographically. But obviously the materials and the climate are very different, and the surface of the Moon is constantly plunged in the dark. At this distance, even if the Sun could be seen through the atmosphere from the surface, it would only be a very distant and faint light in the sky, not the big shiny ball we are accustomed to. Now let's take a look at the second biggest moon of Saturn, Rhea. Rhea is much closer to our idea of a moon. It is made of rock and ice. It barely has any atmosphere, only a very tenuous layer of gas. And it is significantly smaller than our moon. It was discovered 20 years after Titan by an Italian astronomer, Cassini. Hence the name of this mission to explore the moons of Saturn, Cassini-Huygens. These were the early discoverers of Saturn's moons. Rhea may not be as remarkable or as original as Titan, but it holds one record. It is the smallest body in the solar system which has been precisely measured to experience hydrostatic equilibrium. What does it mean? Planets are round, and moons too, down to a certain size, whereas smaller bodies can be irregular. but there is no example of a body the size of Earth, for example, that would be elongated or irregular. This happens because above a certain mass and density, objects in space adopt this spherical shape. But why is that? Because of hydrostatic equilibrium, which is a concept from fluid mechanics. And it is simple to understand. The material inside planets or moons, under their solid crust, is viscous, fluid. It consists of very hot material, rock and metal generally. What makes this material stay together, is gravitation. As you know, the reciprocal attraction of all this matter keeps it as one single object. And gravitation pushes on the material that is at the center of the body. The outward layers of matter above have a weight that compresses the center of the ball. If this gravitational force was left unchecked, the body should collapse on itself. The mass would stay the same, obviously, but it would become smaller and smaller because the matter would be more and more compact. It doesn't happen because there is an opposite force, the one that pushes materials to expand. This, in physics terms, is called the pressure gradient force. So gravitation and the pressure gradient are opposite forces in that case. And the volume of a body stabilizes at the point where the two forces cancel each other. Large objects in space tend to become spherical because of the equilibrium of these forces. The spherical shape is the one that spreads forces evenly around the center. But this happens only on large-scale objects that are not entirely solid. A small or medium-sized asteroid is not affected by this, because it is not viscous, and it is not big enough for gravitation forces to compress it and for its core to melt. But planets and some moons are subject to this equilibrium, and this is why they are round. The pressure gradient force and the equilibrium it forms with gravitation are also important for the Earth's atmosphere. If there was no resistance to gravitation, the entire atmosphere could be pulled to the ground and could not be dozens of miles thick as it is. And if there was no gravitation, the Earth's atmosphere would expand around the planet and diffuse into outer space. It would get lost. Our atmosphere is as it is and stays in place because there is this hydrostatic equilibrium at play. And sometimes it can work in ways that are a bit counterintuitive. You remember earlier I told you that Saturn was almost as big, as voluminous as Jupiter, and yet it only had a third of its mass. How is that possible? This happens because the mass and the size of a body are not systematically moving in the same direction. It would sound logical that if you take a planet and give it more material, the planet is going to turn bigger. But in fact, no, it doesn't work like this. The planet will become more massive if you give it more matter. It will contain more matter. But this is also going to affect its hydrostatic equilibrium. and it could actually diminish its size instead of increasing it, due to the increase in the gravitational force. So Rhea is remarkable in that sense because it is the smallest known body in the solar system that is subject to this hydrostatic equilibrium, and as a result, it gained its round shape. If it had just been a touch less massive, Rhea would have had an irregular shape. Now let's take a look at another moon, also discovered by Cassini, Iapetus. Iapetus is named after a titan of Greek mythology, like various moons of Saturn. And this moon is close to Rhea by size, and its composition is also estimated to be close, ice, and to a lesser extent rock. At first sight, Iapetus may look spherical, but it is not. It is just below the hydrostatic equilibrium line. And this gives it unique features in the solar system. The poles are squashed, and at the equator there is a very long and high ridge, a mountain chain, giving Iapetus the appearance of a walnut. This mountain chain is impressive, especially considering the size of this moon. The mountains are up to 20 kilometers high. For comparison, that is more than twice Mount Everest. On a moon that is much smaller than Earth, Iapetus would have about the surface area of Australia, for comparison. It is unclear how this ridge would form. And there are several hypotheses about it. It could have been created by the collapse of a ring system, or by icy material from inside the moon that would have been ejected. Or maybe it is a remnant of its formation, because based on observed impact craters, the ridge looks very ancient, almost as old as the moon itself. Another mystery about Iapetus is its coloration. One hemisphere is dark and the other very bright. The difference is really obvious, and the reasons for this have puzzled astronomers since the moon was observed from closer. Here again, there are theories. One of them, which sounds possible, is that Iapetus receives infalling material on one of its sides from another smaller moon of Jupiter, Phoebe, and this would be the explanation for the marked difference in color. Before we go on our journey, let's have a look at one last moon with yet another unique feature, Enceladus. Enceladus is small, not large enough to be spherical, and it has an ellipsoid shape. That is to say, the shape of a sphere compressed on both sides. If you put a ball in a press and press to flatten it, you get an ellipsoid. Its small size made it harder to see from Earth, and it was discovered only in 1789 by a German astronomer, Herschel, more than a century after Titan and Rhea. But Enceladus is one of the most reflective bodies of the solar system. It reflects light because its surface is covered in ice. Ice that stays fresh and clean, because on a large part of its surface, this ice is renewed by frequent cryo-eruptions coming out of these cryovolcanoes that we mentioned earlier. Enceladus is thought to have subsurface liquid oceans, and it is yet another moon that is thought to possibly have a set of conditions favorable to biological life. Again, not surface life like on Earth, but life in the depths of dark oceans under the icy crust. How do we know or estimate what these distant moons are made of, by the way? Some of them have been approached by probes, but we never went there or take samples after all. These estimates are obtained by different methods. A first one is to cross the size and the mass of celestial bodies. The size can be observed, and the mass can be deduced from their influence on other bodies due to gravitation. These calculations are complex and they involve multiple bodies and unknowns, but astronomers and mathematicians have worked on these celestial mechanics issues for literally centuries. If you have an estimate of the size and the mass, this may give you a first idea of what a body can be made of. For example, if it is very massive, very heavy for its size, this points to heavy materials like metal, whereas if it is light, it could be ices or lighter rocks. Then there is a second set of information that comes from spectroscopy. What is it exactly? Different elements have different signatures. They emit on different electromagnetic wavelengths. And we can measure these wavelengths. So, analyzed with instruments that can measure and interpret where they are on the electromagnetic spectrum, distant bodies can reveal a lot of information about what they are made of. Here again, this is no golden bullet because the signals are faint, especially for distant bodies. The signals get mixed, so they need to be analyzed to build hypotheses. But this is another valuable source of information. And yet another method is to recoup all this with what we know of the chemical composition in their environment and the formation models. We know, for example, that heavier elements tend to migrate towards the core of a planet, whereas lighter elements will stay closer to the surface. We know that a certain set of conditions, of pressure, of temperature, puts elements in a given state, solid, liquid, gas, or other states. I'll say a word about metallic hydrogen when we dive under the surface of Saturn. So, with these sources of data, and the interpretation that we can do with them from the various disciplines that astronomy touches on, physics, chemistry, mathematics, optics, spectroscopy, we can build solid hypotheses about what planets and moons are made of, and how they are structured internally, even without having physically traveled there. Still, these are only theories and not certainties. Maybe there will be changes in the future. There were some in the past. But at this point, they are the best informed guesses we can make based on available information. As we continue to approach Saturn, it is now time to talk about its rings. The 4 moons we quickly looked at are farther away from the planet. But as you know, because you have seen pictures of Saturn, the rings start quite far from the planet too. they are gigantic. And actually they are even bigger than pictures suggest, because what we see on photos or artist views is just the most visible, the densest or shiniest part of the rings. In reality, they extend on tens of thousands of miles, more than the planet's radius. These rings are also incredibly thin relative to their size. Their thickness varies from 1,000 yards, which is less than a kilometer at most, to only 30 feet, 10 meters locally. This is not even the proportions of a sheet of paper. The rings are incredibly thin. But we see them so well, or at least the rings that are relatively close to the planet, because they are also very shiny. They are made almost exclusively of water ice, with a bit of dust, but barely, less than 0.1%. The main rings are made of billions and billions of particles and small objects. The largest ones are only a few meters or yards across. And they are all little satellites that turn around the planet together. This ice is clean enough to reflect sunlight. And this is why we see the rings so well. Another fact that could sound counterintuitive is how little water or little matter the rings contain. The total mass of the rings has been estimated, and it is less than the Antarctic ice sheet on Earth. So, for comparison, we have to imagine that the ice sheet of the South Pole from Earth would be spread on a surface, an area that is 80 times larger than the total surface of Earth. That's how thin and delicate these rings are. But why are they so big, and how and when did they appear? Historically, the dominant hypothesis was that the rings dated from the formation of the planet or close, and so that they were very old, billions of years old. This hypothesis was not based on very solid measurements or models, and it was increasingly challenged, especially a few years ago when the Cassini spaceship explored the rings. They were revealed to be much less massive than thought. And it was also confirmed that they regularly lost some of their matter, that fell down to Saturn. This means that this type of rings comes with an expiration date. They will get depleted eventually. A problem for the old rings theory is how shiny they are. Over time, they should have collected cosmic dust, particles that would have darkened them. But as I said, they are made of 99.9% pure water ice. So, from these observations, it appeared that the rings could be much younger, maybe, only 10 to 100 million years, which would be a small portion of Saturn's existence. And based on current observed depletion rates, the rings may disappear in 300 million years. The age of the rings is something, but it doesn't tell us how they would have formed. And here there are two main theories. An old one is that the rings are left over from the original nebular material from which Saturn and the whole solar system formed. All these particles would have turned into satellites of Saturn early in its formation process, and so the planet would always, or almost always, have had these rings. As we said before, this theory is now rather old-fashioned, because it fails to explain why the rings would be pure ice, and it doesn't take depletion of the rings into account, because this was not known when this theory appeared. The second theory, which under different variants is now dominant, is that the matter the rings are made of comes from an old moon of Saturn. The orbit of this moon would have decayed, that is to say, the moon tended to fall toward its planet instead of maintaining the same distance to it. And once it was close enough, the attraction from Saturn's big mass, the tidal forces as they are called, would have ripped apart this moon. It would have been shattered over time into all these small pieces that stayed in orbit and formed the rings. A variation of this theory is that it were not tidal forces but a collision between this moon and a comet or a large asteroid that shattered it. This would check with the relatively small quantity of matter in the rings. You remember they contain less material than the Earth's southern ice sheet. But this theory doesn't fit really well the composition of the rings, almost pure ice, because there is no example of a pure ice moon anywhere in the solar system. There are floating blocks of water ice, yes, and water is abundant on many moons. But the moons with the most water, like Enceladus that we visited before, still have about 20% of rock. So, if that happened, if a moon was ripped apart near Saturn, why did its ice stay in orbit and its rock disappeared? Hence another variant of the same origin theory for the rings. It would not be an entire small moon, but just the ice mantle of a larger moon, maybe a moon the size of Titan. Such a moon would have decayed, its orbit would have decayed during the formation period of Saturn, and its mantle of ice would have been stripped and stayed in orbit, whereas the rest of the moon would have fallen into Saturn and have been absorbed by it. But these are all theories with their own merits, and nothing is sure. For example, the brightness of the rings, their purity, is cited as proof that the rings are young and not hundreds of millions of years old. But maybe the darker material could have stayed in certain areas of the rings. They are not uniform. There are divisions between them and zones that appear more or less bright. Maybe clumps form within the rings with impurities, and then they would be disrupted by impacts which would automatically clean up the rings. We don't know for sure. But at this point, the best hypothesis for the presence of all this matter in orbit around the planet remains a shattered moon, entirely or partially. What we really don't know is when and how this happened. You saw pictures of the rings, so you also know that they have like stripes, subdivisions, lines that are more or less bright, and in between them sometimes entirely dark spaces. different subdivisions have been established based on their appearance and the distance to Saturn. A common one starts from ring D, the closest to Saturn, which is quite faint and was confirmed only in 1979 by a probe Pioneer 11. Then there are rings C, B, A, with divisions between them, and after that it turns a bit confusing if you keep moving away from the planet, because the ring after A is called F, and after that E. These different divisions have different physical characteristics, like their thickness and the density of particles that makes them more or less bright. But let's keep approaching. We are now right in front of the imposing mass of Saturn. I told you at the beginning it looked almost as big as Jupiter, even though it has less than a third of Jupiter's mass. And this has to do with this equilibrium of mass and size that we discussed before. Being more massive, Jupiter is more compressed, so it is also significantly denser than Saturn. In terms of chemical composition and structure, if we leave aside this difference of density, the two planets look alike. They both are gas giants, thought to have a metallic and rocky core, around which enormous layers of gas have accumulated and stay stuck together by gravitation. Now we say gas because its main components are hydrogen and helium, and in that the planet reflects the composition of the nebular cloud from which the solar system formed. It was thought to be mainly hydrogen, followed by helium, the two simplest elements, and the rest, the other elements, were present in very small quantities proportionally. But don't imagine that Saturn is just like a cloud. It is way denser than that. Around the core, it is believed there is a layer of metallic hydrogen. That is to say, hydrogen that is so compressed that it goes beyond liquid. It is in a state called metallic because it can conduct electricity. I told you about it already in the space cruise to Jupiter and its moons, or when we detailed the table of elements. Above the layer of metallic hydrogen, there is liquid hydrogen and liquid helium, and only above that begins a truly gaseous outer layer. So there are parts of Saturn that are denser than anything on Earth, and in total, the planet has 95 times the mass of Earth. For comparison, Jupiter has more than 300 times the mass of Earth. But if you take an average, with these outer layers of gas that are little dense, Saturn has an average density that is lower than water, about 30% less dense than water. So, still in average, it could be called a relatively light planet. It is not pure hydrogen and helium, too. As we said, the core is thought to be metallic and rocky, and there are traces of other elements. This is where the yellowish hue of the planet comes from. In its upper atmosphere, there are crystals of ammonia that give it its color in natural light. Apart from that, the planet has less features than Jupiter. Its surface is rather uniform, with just a bit more yellow around the equator. And it doesn't show on pictures, but its shape is not really that of a sphere. This is due to its rotation and its relatively low density. The rotation creates a centrifugal force, and this flattens the planet a little bit. It becomes an ellipsoid, like Enceladus, the moon we visited before. Except, contrary to Enceladus, Saturn is not a body with a solid surface. It is a rotational ellipsoid. It takes this ellipsoid shape due to its rotation. If the rotation stopped, which is not going to happen, but let's say it would, theoretically, then the centrifugal force would dissipate and the planet would become a sphere due to this hydrostatic equilibrium that we talked about before, that would no longer be altered by the rotation. Like for other gas planets, if we approach Saturn and start diving into it, there is no precise surface, just an increasing density of gas around us, that after hundreds of miles of travel towards the core of the planet becomes so dense that it turns into liquid, then metallic, and after that there is a molten core of heavy material, metal, probably predominantly iron, and rock, silicates. Being that much farther from the Sun than Earth, it takes more time to Saturn to complete a revolution, the Saturnian year, almost 30 of our years. During this long revolution, the aspect of Saturn seen from Earth changes a little. We see it under different angles, at times from above the rings, and the rest of the time from under the rings. This is so because all orbits of planets around the Sun are on the same plane, but this plane is not perfectly uniform for each of them, each of these orbits. The orbit of Saturn is slightly elliptical, and compared with the orbital plane of Earth, it is slightly inclined by a bit more than 2 degrees. So, if we take the orbital plane of Earth as a reference, Saturn crosses it twice in 30 years, when it passes above and then below. And this is why the planet is seen half of the time, and for several consecutive years, from above, and then from below, slightly. Its surface may look peaceful and quiet in comparison with Jupiter, which has stripes of color, moving, and a red spot which is thought to be a gigantic storm. But this is misleading. In its upper atmosphere, Saturn has some of the most violent winds of the solar system, at 500 meters per second for the fastest ones observed. These are only second to the winds of Neptune when it comes to speed. Again, for comparison, the speed of sound in our atmosphere is 360 meters per second. And here, at 500 meters per second, these winds are supersonic. At its southern pole, Saturn also has an unique feature, a warm polar vortex, that is to say a region of rotating gas, in that case a big one because it is the size of Earth, around which blow the fastest winds observed on the planet. Heat, supposedly coming from inside Saturn, is ejected from that vortex. The average heat in the atmosphere of Saturn has been measured at minus 185 degrees Celsius, but the temperature measured in that vortex would be about 60 degrees warmer, at minus 122 degrees Celsius. It is still freezing cold there, but less so, and these temperature differences probably explain and influence the violent winds around the vortex. How far are Uranus and Neptune from us on Earth? You remember from our previous space stories that there is an unit that is useful to figure out distances in space, the astronomical unit. It was defined, roughly, as the equivalent of the distance from the Sun to the Earth, which is about 150 million kilometers, 93 million miles. Light takes about 8 minutes to travel this distance, and the astronomical unit is convenient to compare distances between the orbits of planets. So, the Sun to Earth distance is 1 astronomical unit, the Sun to Mars 1.5 units, Jupiter, which is the 5th planet from the Sun, is at a bit more than 5 astronomical units. Saturn, the 6th planet, is almost twice as far as Jupiter, 9.5 astronomical units. But to reach Uranus, we need to double that distance again, about 19 astronomical units. 19 is like a middle point, because the orbit is not a perfect circle, it is slightly elliptical. At its closest, the distance is a bit more than 18 astronomical units, and at its farthest, a bit more than 20. But a good order of magnitude to bear in mind is that Uranus is 19 times farther from the Sun than Earth, and Neptune is 30 times farther. At this distance, light and heat from the Sun take more time to reach them, and there is much less. They don't have a solid, rocky surface, as you know, so we cannot really say that they have a cold surface. But the upper layers of these planets are extraordinarily cold. We will see how cold when we approach them. The first close images we got from Uranus are not very old. They were taken by a probe, Voyager 2, in 1986, and they revealed a planet that looks almost featureless, without the kind of cloud bands and storms that are observed on other giant gas planets. Neptune looks more animated, but both planets have conditions in their upper layers that are some of the most extreme in the solar system. So first, let's talk about what they are made of and why they are called ice giants. Until the 1940s, astronomers distinguished two main types of planets in the solar system: the rocky ones, with a solid surface, like Mercury, Venus, Earth and Mars, and gas planets, which are bigger and do not have a clearly defined surface, because they are made of gas in various layers denser and denser as you move towards the center. And their core is believed to be made of rock and metal, around which gas has accumulated and stays kept together by gravitation. There were 4 gas planets: Jupiter, Saturn, Uranus and Neptune. It was assumed that their composition was more or less similar, mainly hydrogen and helium, the 2 most abundant elements in the solar system, and most probably in the universe in general. They are the simplest, the smallest types of atoms. There are heavier elements, dozens of them, including some that are also relatively abundant, like oxygen, iron, and carbon. But it is believed that these elements are mostly younger than hydrogen. Like other heavier atoms, they would tend to form in stars when they approach the end of their lives. You know that the fuel of stars is hydrogen. Inside them, hydrogen is exposed to such extreme conditions that fusion happens. Atom cores combine to form heavier atoms, mainly helium, for most of a star's life. But when the end of a star nears, because it has consumed a large part of its hydrogen reserves, which takes hundreds of millions of years, billions of years in the case of a star like the Sun, the star starts consuming helium, and heavier and heavier elements are formed. It is believed that this is how these heavy elements appear, all the way to big atoms with dozens of particles, like gold or uranium. And then, when a star dies, it becomes gigantic, it explodes in a supernova, which would disperse these elements, and they would become available to form new systems. Our system is much younger than the estimated age of the universe. I told you about all that in the video about cosmology. I put the link in the description. So if these theories about the universe, stars, and the formation of star systems are accurate, it is not surprising that these heavier atoms are actually present in our solar system, either alone or combined with others in compounds like ammonia, carbon dioxide, sulfur dioxide, or water. But still, most of the solar system, if we take into account the Sun itself and all the planets, is still mostly hydrogen and to a lesser extent helium. And as it happens, these are also the main components of gas planets like Jupiter and Saturn. They probably have rocks and metals in their core, and they have other compounds in small quantities in their various layers. But this isn't much in proportion. So, until about the 1940s, it was assumed that Uranus and Neptune, because they were giant planets with no defined surfaces like Jupiter and Saturn, had a similar composition. To put figures on this, it is estimated that Jupiter and Saturn are more than 90% hydrogen and helium. But it appeared through spectroscopy and estimates of their mass relative to their size, and later measurements sent by probes, that no, Uranus and Neptune were quite different in their composition. only about 20% of hydrogen and helium by mass, and a lot of compounds like water, hydrocarbons, and ammonia. These different compounds are called ices in astrophysics and planetary science, because when they are independent from a larger body like a planet and at a sufficient distance from a star, they are generally found frozen as solids. On Earth, when we hear the term ice, we think about water ice, whereas in astronomy, ice refers to a broad range of compounds that includes water and various more. These compounds have in common that they freeze above or near 100 kelvins at Earth's surface pressure. They include water, which freezes at 273 Kelvin, which is 0 degrees Celsius. The Kelvin scale is similar to the Celsius scale, except it begins at 0, the lowest possible temperature, whereas the Celsius scale begins at minus 273. So water freezes at 273 Kelvin and 0 degrees Celsius. Ammonia freezes at 195 Kelvin, that's minus 78 degrees Celsius, or methane freezes at 91 Kelvin, minus 182 Celsius. These elements make the majority in mass of Uranus and Neptune. And this is the scientific reason why they are called ice giants. But it can be a bit misleading, because when we hear ice giant, we may think about a planet with a hard surface, which they are not, or one with blocks of ice floating in its atmosphere, which they don't have either. The term ice refers to the compounds they are made of, not the state they are in, because, as we will see, these compounds are no longer solid. They might have been when the planets formed, but they no longer are. The term was needed to differentiate these planets from gas giants, like Jupiter, because their composition and formation history were quite different, and the term ice giant sounded appropriate, which is why it was adopted over the past 40 years. Now, a good question is why some planets are rocky, others are made of hydrogen and helium, and others of ammonia, water, and methane. And why is there an apparent order in the solar system with 4 rocky planets near the center of the system, then 2 gas giants made of hydrogen that happen to be the 2 biggest planets, Jupiter and Saturn, and after them 2 ice giants that are in between rocky planets and gas giants in terms of size and mass. To try answering this, we need to talk about the theories of planet formation. One thing that makes the formation of planets harder to research is that we only have one system at our disposal, ours, and there are not that many planets in it. Only 8 bodies are considered massive enough to be classified as planets, plus a few smaller bodies like Ceres or Pluto, dwarf planets, but that's not many. The starting point of a star system is something relatively uncontroversial among astrophysicists at this point. It is still theoretical, but it is backed by a lot of observations from the chemical composition of planets to their orbits, the laws of gravitation, and even, since 2018, the direct and confirmed observation of a star system in formation around a newly formed star called HL Tauri, 450 light-years away from us. It is far, but not that much at the scale of the galaxy. It is believed that a star system begins to form when enough matter, gas and dust, coming from a nebula concentrates in a smaller space. A nebula is an immense cloud of matter floating in space. There are several in our galaxy. And the main force behind the formation of a star system is gravitation. In this region of space, this matter in suspension tends to take the shape of a large disk that rotates on itself. For this rotation to begin, an initial impulsion is needed. It is believed that supernovas, the final explosions of stars, could provide it, because they send a shock wave in space. As this disk rotates, matter tends to concentrate in the center faster and faster because the mass at the center increases, absorbing more and more matter. And when the mass becomes critical, big enough for pressure at its center to ignite fusion, it becomes a star. Typically, this new star goes through a short period of growth, during which it absorbs most of the disk. In the case of the solar system, more than 99% of it. We know that there are systems with several stars, 2 or even 3, of different sizes, so there is not a single possible accretion model, accretion process, but it seems the single star model, like our system, is the most frequent one. In any case, this doesn't let much matter available, but still enough to form several planets that concentrate the rest of the protoplanetary disk, what the star hasn't swallowed. This protoplanetary or accretion disk is the basis of planetary formation models. But then there are theories that explain differently the specifics of planets' formation, and ice giants are a bit of a problem here, because their existence appeared as a challenge to existing theories when their composition was discovered. The formation of rocky planets like Earth and also gas giants like Jupiter, this is not very controversial. They are widely understood to have formed through millions of years of collisions of smaller rocky bodies within the protoplanetary disk, until one larger planet remains on its orbit, having cleaned up the orbit of all other bodies. But why do some of these planets become gas giants instead of terrestrial planets? It would be because they would have formed bigger solid cores, around 10 times the Earth's mass, and so with a more powerful gravitational pull, they would have also acquired, by accretion, an envelope of gas. Based on the observation that in the solar system, rocky planets are closer to the star, and gas giants farther from it, it is supposed that the distance from the star also helps retain gas. So, for a long time, it was believed that gas giants had to form relatively far from the star, from the center of a system. whereas rocky planets could be more central. Actually, they could theoretically be distributed in a large part of the protoplanetary disk, but they would tend to become satellites, moons, of gas giants if they were close to their orbits. But in the past 2 or 3 decades, this theory, this assumption, has been questioned by many observations made outside our system, with plenty of exoplanets and other star systems. It appeared that there could be large gas planets, exoplanets, orbiting close to their star, and with a very short orbital period. That is to say, they orbit quickly around the star, as little as a few days, to compare with an entire year for Earth or 12 years for Jupiter. When these gas giants that are close to their star were discovered, they were called hot Jupiter, hot because they are close to the star. And clearly their existence raised a challenge to existing theories about gas giants. These are the easiest exoplanets to discover, because they are big and they are close to their stars, which makes them stand out. They are much easier to spot, and there are plenty of hot Jupiters. So the theories were revisited. The prevalent view about hot Jupiters at this point is that they probably form far from their star, and then they migrate closer to it. The migration could be progressive due to an imbalance in the system until they find a stable orbit close to the star, or it could happen due to a collision that suddenly modifies their trajectory in space. An alternate hypothesis is that they form in situ, close to the star, maybe due to a particularly big solid core that has a lot of gravitational pull. The truth is that this remains an open question at this point. But returning to ice giants, the problem they raise is that these models that work well with terrestrial planets or giants like Jupiter have a very hard time explaining the formation of these big planets so far from the star. Why is that? Accretion of a rocky core requires collisions, plenty of them, and the formation of a protoplanet that progressively cleans up its orbit by absorbing everything on it. So at the start, the protoplanets are fairly small, and a theoretical problem here is that given their distance from the star, a protoplanet forming on the orbits of Uranus or Neptune should have been expelled when they were smaller from the solar system. Based on the laws of gravitation, it is logical that a planet like Jupiter or Saturn stays within the system. They are at 5 and 9.5 astronomical units from the star. But the further you are from the Sun, the less you are bound to the system by gravitation. The force decreases with distance, and at 20 astronomical units like Uranus, or even more, 30 like Neptune, with the accelerating effects of Jupiter and Saturn, the protoplanets would have surpassed the escape velocity. That is to say, they would have traveled fast enough in space to overcome the Sun's pull, and they would have left the solar system. Or they should have been pulled and absorbed by Jupiter and Saturn, or turned into comets, before fully forming. But obviously it didn't happen, because they are here. But a planet forming by collision at 20 astronomical units or more from the Sun and staying there on a stable orbit is something that formation models have a hard time explaining. And to make things even more complicated, it seems that Uranus and Neptune are no exceptions. Plenty of exoplanets that have been discovered in other systems are candidates to be ice giants. So, what could have happened? A first possibility is that they would have migrated after their formation, like possibly hot Jupiters do. They would have started to form somewhere between the orbits of Jupiter and Saturn, 5 to 10 astronomical units from the Sun, and then changed orbit at a time when their sizes and speed were sufficient to keep them bound to the solar system. It is not precisely explained how. There are different theories about this outward migration. It could be, for example, due to close encounters with Jupiter or Saturn that would have expelled them to another orbit. Or another possibility is that they formed differently near their current orbit, but in that case it couldn't be through collisions. An alternative that could work, theoretically, would be that they formed due to instability in parts of the protoplanetary disk. There could have existed regions of slightly higher density in the disk that could lead to the formation of clumps of matter that eventually collapsed due to gravitation to form a planet. Models suggest that a disk with a bit of instability could yield protoplanets between 10 and 30 astronomical units from the star, and both ice giants of the solar system are within this range. So, at this point, the formation of Uranus and Neptune is explainable. The thing we don't know is what mechanism, what process happened, because these processes may have been very different. But we are now at 19 astronomical units from the Sun, approaching Uranus. Even though it is way smaller than Jupiter and Saturn, it was observed from Earth centuries ago, maybe as early as the antiquity. But for a long time it was mistaken for a star or a comet, until the late 18th century, when several astronomers realized that due to its movement it couldn't be a star and had to be a planet beyond Saturn. Uranus is about 19 times farther from the Sun than Earth, as we said, and it is also slower on its orbit, so it takes much more time to complete a revolution, 84 years. Actually, since it was identified as a planet in 1781, it has made less than 3 complete orbits. I also told you earlier that it received much less sunlight than us, due to the distance. The intensity of sunlight varies inversely with the square of distance. In other words, it decreases faster and faster as you move away from the Sun. And so at 19 or 20 astronomical units, depending on where the planet is on its elliptical orbit, it receives 400 times less light than Earth. In other words, Uranus travels in space in the dark, and if we looked at the Sun from it, the Sun would be a small point in the distance, not the big and bright light we see from Earth during daytime. Uranus has several moons 27 have been identified, and we will explore the biggest of them, Titania. But first, let's start traveling inside the planet, from its atmosphere to its core. What we call atmosphere here is just the envelope of gas, because there is no well-defined solid surface. So the atmosphere has been defined as the region that was accessible to remote sensing, up to 100 bar of pressure. That is still hundreds of kilometers or miles within the planet. We saw earlier that the pictures taken by Voyager 2 or telescopes with a lower definition suggest a peaceful, quiet, featureless planet that looks pale blue-green. This is due to the composition of the atmosphere that absorbs red light, but this may be misleading. The planet's atmosphere is very active, and for short periods of time, it happened for 2 months in 2004, for example, large clouds can appear in the atmosphere and spectacular storms can take place. Record-breaking winds have been observed at more than 500 miles per hour, that's more than 800 kilometers per hour. And even though the climate is not very well known, it seems it is subject to big variations. Since the 1990s, and thanks to imaging with higher definition and under different types of light, a lot of clouds and atmospheric phenomena have been discovered. In this atmosphere there is mainly hydrogen and helium. You remember they account for an estimated 20% of the planet's mass, and these elements are thought to be absent from the denser parts of the planet. The third element, that would account for a bit more than 2% of the atmosphere, would be methane, and this aquamarine color of the planet in visible light is probably due to methane. This atmosphere is intensely cold. The temperatures vary depending on the altitude, but in the coldest parts of the troposphere, that is to say the lowest and densest part of the atmosphere, they are near 50 Kelvin, below minus 200 degrees Celsius or below 350 degrees Fahrenheit. I made a story about the Earth atmosphere that explained the variations in temperature, up and down, due to the composition and density of the layers of gas. The atmosphere on Uranus is much lesser known, but it is well established that in the troposphere there are different layers of clouds. Where the pressure is lower, they seem to be made of ammonia, hydrogen and sulfur, whereas where the pressure is higher, they could be water clouds. And these different levels of the troposphere would have a highly complex structure, constantly moving, with strong winds and seasonal variations. Below the troposphere, density and temperature increase. Progressively, hydrogen and helium are less and less present, and we come closer to a kind of mantle made of these ices that give their names to this type of planet. Again, these are not actually solid ices. They probably were before the planet formed, but they are called ices because they are compounds that would be solid if they floated in space, like on a comet, or if they were at the surface of a rocky planet. This mantle represents the bulk of the planet's mass. In total, Uranus' mass is 14.5 times that of Earth. The gas envelope occupies a lot of space because it is not very dense, whereas this mantle is much denser. It represents more than 13 times the Earth's mass and about 90% of the whole planet. Given the conditions, the main components, which are thought to be water and ammonia, are believed to be in a state of dense and hot fluid. This fluid is sometimes called a water-ammonia ocean. By the way, you know what water is, but what is ammonia exactly? When hydrogen forms molecules with oxygen, you get water, as you know. Ammonia is a molecule that hydrogen forms with nitrogen. It is quite abundant in the solar system. There is some on Earth, but it can be found in much higher quantities on Mars, Jupiter, Saturn, and of course Uranus and Neptune, where it is an important component. On Earth, it is found only in trace quantities in nature, and often associated in salts with other elements like chloride or sulfur. But it plays a very important role in the cycle of life on our planet. It is a common waste of the feeding cycle of aquatic organisms, and it contributes to the nutritional needs of terrestrial organisms. Plants need it to grow, and it serves as a precursor to almost half of the world's food. Typically, fertilizers contain some. Now, returning to space, the mixture of water and ammonia has the particularity of freezing at a very low temperature. The melting point is as low as 173 Kelvin, which is minus 100 degrees Celsius, 100 degrees less than water alone. So in space, this water-ammonia mixture could act as an antifreeze and allow the existence of liquid internal oceans at temperatures far lower than it would be possible with water alone. But this is not a concern for Uranus, because where there is this water-ammonia mixture on the planet, the temperature is estimated to be much higher than that. Where the mantle begins, the temperature would be around 47 degrees Celsius, and the pressure 100 bar. That is to say, 100 times the atmospheric pressure at sea level on Earth. And then, traveling deeper into the mantle, temperature and pressure increase, up to extremes at the center of the planet that are estimated to 8 million bars and a temperature of about 5,000 degrees. A hypothesis is that within the mantle, methane, which is also present, could be broken up under the constraints. Methane is hydrogen with carbon, and so pure carbon atoms, could condense into crystals of diamond that would rain through the mantle, almost like stones sinking in a lake, except it is not a lake of water, but of water and ammonia, with very high temperature and pressures that are superior to the deepest abyss on Earth. These rainfalls of diamonds may not be limited to Uranus. Theoretically, they could also happen inside Jupiter, Saturn, or Neptune. Another hypothesis is that at the basis of the mantle, where the core begins, there could be an ocean of liquid carbon. In this state, it is called metallic carbon because it conducts electricity. And yet another curiosity would be the presence of water at such high temperature and pressure that it becomes something called superionic water or superionic ice. This is the same thing. What does it mean? The conditions are so extreme, and they actually cannot exist in nature on Earth, that the water molecules break apart and oxygen crystallizes. That is to say, it adopts a highly organized and repetitive structure, like a lattice. In between this lattice, hydrogen can float freely. The existence of this state, this phase of water, was only theoretical until it could be synthesized very recently, in 2019. In a laboratory, water was squeezed between two pieces of diamond and maintained at a very high pressure, and then blasted by a pulse of laser. In this experiment, the pressure was 1,000,000 times atmospheric pressure. It defies imagination, but as we saw earlier, pressure inside Uranus could reach up to 8 million atmospheres, so it is theoretically possible in natural conditions on this planet. And the water was heated almost instantly with the laser to several thousand degrees, recreating the conditions that are believed to exist within the mantle of Uranus and Neptune too. As expected, oxygen and hydrogen in water molecules broke apart and oxygen crystallized. This phase of water is also called Ice 18. In a previous story about the moons of Jupiter, I told you about the different types of ice, of water, that are thought to exist depending on the conditions. Ice 18 is one more, and it is likely to exist in a stable state somewhere in the depth of ice giants, even though we are nowhere near the capacity of going there to take samples and check. After the mantle, the last part of the internal structure is the core, around which ices and gases aggregated during the formation process, or possibly where heavier elements migrated. We don't exactly know, as we saw when I told you about the formation history of the planet. This core is thought to be relatively small, around half the mass of Earth, and it would be made of rocks, of silicate, that is to say silicon and oxygen, and also metals. Now that we have quickly seen the inside, let's take a look at the periphery of the planet, because there are more things to see there. First, there are rings. They are not very visible and generally not represented on views of the planet, but 13 of them are known. The majority of them are very narrow, only a few kilometers or a few miles wide, and they are made of very dark particles that vary in size from microscopic to 1 or 2 feet. It is believed that these rings are younger than the planet. It could have been one or several moons that were shattered by impacts and left their matter all around the planet in orbit. Because there is a respectable number of moons around Uranus, we know 27 of them. So let's take a look at the largest one, Titania, which is also the 8th largest moon in the solar system. It is believed to have formed like the other moons of Uranus from a small accretion disk that surrounded the protoplanet in the early stages of the solar system. In its composition, Titania is very similar to several moons of Jupiter that we visited in our last space journey. Rock in the center and an envelope of water. It is unknown whether some of this water could be liquid under a crust of solid ice, but Titania is relatively small, much smaller than the Earth's moon. It may not have kept enough internal heat to have underground oceans, subsurface oceans, like Europa or Ganymede are suspected to have. At its surface, there appears to be a lot of canyons. This is not the kind of features that can be created by asteroid impacts. Canyons can appear due to plate tectonics, but Titania is too small for that, or because of erosion. But Titania doesn't really have an atmosphere with meteorological events that could provoke erosion. So a hypothesis is that long ago there was a liquid ocean on Titania under a layer of ice, maybe kept liquid thanks to the presence of ammonia. As we saw before, it is a powerful antifreeze when mixed with water, because it freezes 100 degrees Celsius below water alone. And then, as Titania became colder as it cooled down, the subsurface ocean would have frozen. This would have made its volume increase, and it would have created these canyons at the surface because it would have broken the hard ice crust. Overall, Titania is an icy desert. It does not produce much internal heat. There is no atmosphere to retain heat, and it doesn't receive much sunlight due to the distance to the sun. But there are still variations of temperature due to seasons, and they are extremely long due to a particularity of Uranus. Uranus has the particularity to present its pole to the Sun, not its equator, like other planets. This could be due to a major collision in the distant past that would have tilted the planet. And the moons orbit around the equator of the planet, and Titania always presents the same face to the planet. It is tidally locked to it. So what it means in terms of seasons is that when Uranus is on one side of the Sun, Titania presents one of its poles to the Sun, and then the other pole. But as Uranus needs 84 years to complete one orbit, this means seasons on Titania last 42 years. One side is lighted for 42 years, whereas the other side is in the dark, and then they switch for another period of 42 years. Now let's resume our journey and go to our second destination, even farther away from Earth. Uranus is about 20 astronomical units from the Sun. Now we need to travel 10 astronomical units more to reach the orbit of Neptune, which, as we're going to see, is a near twin of Uranus, with a few differences. Neptune is so far away that it is invisible from Earth to the unaided eye, and this is why it was the first planet discovered not by observation, but by mathematical prediction. This happened in the first half of the 19th century. Uranus had been found and was now observed by telescopes, and its orbit was mapped. But something was off. there were unexpected changes in the orbit of Uranus that were not really explainable by the existence of other planets and the laws of gravitation. So either there was something wrong with the calculations, or there was something else, yet another unknown planet that influenced the orbit of Uranus. The position of a possible eighth planet was deduced from the perturbation of Uranus' orbit, and this ghost planet was tracked in the night sky until 1846, when it was found. In the following decades, several moons were also found around Neptune, starting with, by far the largest one, Triton. We'll take a look at it a bit later. In terms of composition and structure and size, Uranus and Neptune are thought to be very similar. Envelope of hydrogen and helium, ices inside, that is to say water, ammonia, methane, to a lesser extent carbon dioxide. But in visible light, Neptune looks bluer. This is believed to be due to more methane in the upper layers of the atmosphere, and possibly another component that has not been fully identified. Another difference is that Neptune is a bit more massive than Uranus. It has 17 times the mass of Earth, versus 14.5 times for Uranus. And it sounds counterintuitive, but it is also physically a bit smaller. This is due to its mass. It implies a bit more compression of its atmosphere. And in balance, it is a bit more matter in a bit less space. Another difference is the distance to the Sun. The two planets are 10 astronomical units away from each other, and this is a huge distance, about the same as the distance from the Sun to Saturn. And this means even less sunlight. Neptune is internally a bit hotter because of its bigger mass, so the temperature at the center is estimated at 5,400 Kelvin versus 5,000 for Uranus. But still, its atmosphere is one of the coldest places in the solar system. The temperature approaches 50 Kelvin, that's below 200 degrees Celsius, and only 50 degrees above absolute zero. Since its discovery, Neptune has completed only one orbit around the Sun. It takes 165 years, twice the time Uranus needs. And yet another difference is the intensity of meteorological activity compared with Uranus. Neptune's atmosphere is all but peaceful. There are giant storms constantly, a complex system of clouds, and the most powerful winds of the entire solar system. They blow constantly at more than 1,000 miles per hour in the upper atmosphere. This is believed to be a consequence of the differential in temperature between the core and the mantle, which are hotter than for Uranus, and the atmosphere, which is colder in its upper parts. And as you know, winds are the product of gas masses moving from one place to another, due to a differential in pressure and temperature. And on Neptune, these differentials are bigger. And so the planet looks constantly agitated by giant storms that have been observed since we have higher definition images. For a time there was a big dark spot, comparable in nature to the great red spot of Jupiter, and it was a storm. It finally disappeared, but more perturbations are constantly appearing and disappearing at the surface. Beyond Neptune begins a region called the Kuiper Belt. a very large region of the outer solar system, with millions and millions of small asteroids. Pluto, the dwarf planet, is one of these bodies. The limits of the Kuiper belt have been set to between 30 astronomical units from the Sun, that is to say Neptune's orbit, and 55 astronomical units. And Neptune has a strong influence on this belt due to its gravitational pull. It has shaped its structure over time after hundreds of millions of years and millions of revolutions around the Sun. An example of that is the number of objects that are in orbital resonance with Neptune in the Kuiper belt. I explained the concept in the story about Jupiter's moons because 3 of them are in orbital resonance. To summarize, it is when 2 or more objects on different orbits become locked by their respective influence on each other, and their revolutions happen in a stable ratio. In the example of Jupiter's moons, every time Ganymede makes 1 orbit, Europa makes 2, and Io makes 4. So they are said to be in a 1-2-4 resonance. Neptune is in resonance with dozens of smaller bodies in the Kuiper belt, starting with Pluto. They are in a resonance of 2-3. That is to say, when Pluto makes 2 revolutions, Neptune makes 3. And there are also other ratios that have been found with other bodies: 3-4, 3-5, 2-5, 4-7. Over time, the Kuiper belt has become strongly influenced by Neptune, by its mass and orbit, in a way that is similar to the influence of Jupiter on the smaller asteroid belt, the one that is between the orbits of Mars and Jupiter. Neptune also has 40 known moons, most of them small, except one, Triton. Triton alone represents more than 99% of all objects orbiting Neptune. All the other moons together are not even 1%. So let's focus on Triton, because it has original elements, original aspects that make it different from most moons. The first one is that its orbit is retrograde. It orbits in the opposite sense to the rotation of Neptune. This is very rare for large moons in the solar system. Most of the time they are the opposite, prograde, meaning they follow the rotation of their planet. This is a strong clue that Triton did not form in the periphery of Neptune, but was captured later, possibly from the Kuiper belt, where it would have been considered a dwarf planet like Pluto if it was still in the belt. Triton is actually a bit larger than Pluto, and almost as large as the Earth's moon. So it is rather big, the 7th largest moon of the solar system. Its surface looks like it was renewed. This can be deducted from the density of impact craters. There are few, and this strongly suggests that if the moon can rejuvenate its surface, it is geologically active. That is to say that it has a differentiated structure with a core, a mantle, and a crust. That would be coherent with its size, and there seems to be 2 kinds of geological phenomena at the surface: cryovolcanism, that is to say, eruptions of warmer materials like water that surge and freeze at the surface, and also tectonic terrain that would release other materials from inside the moon, or that would let plates of crust move. This is how mountains and rifts can appear. How can a body of that size be captured, bearing in mind that distances are huge in the Kuiper belt? There are different possible mechanisms. In any case, it takes a very long time and maybe millions of orbits around the Sun. Parts of Triton's orbit may have crossed or passed near Neptune's orbit, and bit by bit, the influence of Neptune would have slowed Triton down, so much that Triton's speed could have passed below escape velocity, allowing its capture by gravitation. The slowdown could also have been the consequence of a collision between Triton and an ancient moon of Neptune, now disappeared. Or yet another option is that Triton formed a binary system with another body, like Pluto and its biggest moon, Charon. The influence of Neptune on this system would have caused the system to interact in such a way that Triton would have been pushed to the orbit of Neptune and its partner expelled from the Kuiper belt, or even possibly from the solar system. We don't know, but it seems the arrival of Triton had catastrophic effects on the ancient moons of Neptune. It perturbated their orbits. There could have been collisions, and small moons could have been dispersed through gravitational interactions. When the system stabilized, Triton represented more than 99% of the mass in orbit around Neptune, the remainder being faint rings and small irregular moons. At its surface, in this region of intense cold, Triton is covered with a layer of frozen nitrogen. There could be an envelope of water, accounting for 15% to a third of the moon's mass, and below that, a mantle and a core of rock and metal. Like for many moons we have visited in our stories, there could be liquid water, a subsurface ocean, that could theoretically harbor life, but this is speculative, and it is already hard to imagine an expedition to Europa or Ganymede, which are 5 astronomical units away from the Sun. Triton is 6 times farther, at 30 astronomical units, so any manned mission to explore it directly is science fiction at this point. It takes a lot of patience to send probes to these regions of the solar system. All space missions take time, but this is really far. You remember we talked about the probe Voyager 2, that was the first to take close pictures of Uranus and Neptune. It was launched by NASA in 1977. It reached Jupiter in 1979, then Saturn in 1981. It took 5 years more, despite an acceleration, to reach Uranus in 1986. And still continuing to accelerate, Neptune was reached in 1989, 12 years after launch. Voyager 2 is still active, by the way, and now on a mission to explore interstellar space, 44 years after departure. The distance it has traveled is absolutely mind-blowing. When it reached Neptune, 32 years ago, it was at 30 astronomical units from the Sun. Then it crossed the entire Kuiper belt, which ends at 55 astronomical units, and it exited the zone of influence of the solar system at 120 astronomical units. That was in 2018. Voyager 1, also conceived to reach interstellar space and launched almost at the same time, is also still operational and is now at more than 150 astronomical units from Earth. These two probes are by far the man-made objects that have traveled the farthest ever. I take you on a new space journey tonight. But contrary to other journeys we made to other planets, stars, or even galaxies, the objects of our attention tonight will be much smaller. I'll tell you about asteroids, comets, and the phenomenon of shooting stars, meteors, when small asteroids, meteoroids enter and burn through our atmosphere. We have a lot to discover. Our cruise will begin in the upper layers of our atmosphere, and then, following the trail of these bodies, we will travel through the solar system, through the asteroid belt, and even beyond the orbit of Neptune. I will also tell you of different phenomena like how comets form, why and how bodies burn through our atmosphere, what a comet's tail is made of, and I'll also tell you about Oumuamua, this strange space object that was detected a few years ago and probably comes from another system. Our cruise begins just a few miles above the surface of the Earth, above the clouds, a good place to observe shooting stars at night. And you know what they are, a glowing streak of light that travels for a short time in our atmosphere and can sometimes be observed from the surface at night when meteorological conditions allow it. But shooting stars or falling stars are colloquial terms for a meteor. So what are the differences between these various words? Meteor, meteorite, meteoroid, asteroid, comet. The differences are all about the size and the location, and also what they are made of. A meteor is synonymous with shooting stars. It is more a phenomenon than an object. The object that causes a meteor is a meteoroid, or an asteroid. The difference between a meteoroid and an asteroid is essentially the size, the mass. A meteoroid is smaller, typically the size of a pebble. There is no official precise range of mass for meteoroids, but think about anything from the size of a grain of sand to a basketball. Meteoroids are generally fragments of asteroids, which are bigger. Now, a meteorite is what remains of a meteoroid or asteroid once it has fallen on Earth, if it has not entirely fragmented and burnt. So, in summary, an asteroid can break into smaller meteoroids, and if they enter the Earth's atmosphere, generate a meteor as they burn. Finally, if something is left of this body after impact with the Earth's surface, it will be a meteorite. A comet is a different type of asteroid. It has a particular composition, we will see that later, and an orbit, a trajectory in space, that makes it periodically come close enough to the Sun for the interaction of solar radiation on the elements it is made of to generate a coma and a tail of gases and dust, which give the comet its well-known popular appearance. As we are now high in the atmosphere, let's take a look at meteors, or shooting stars. It is the same thing. It is not that common to observe shooting stars, and that could make us think that the meteoroids that enter the Earth's atmosphere are fairly rare. It is actually the opposite. It is estimated that about 25 million meteoroids enter our atmosphere each day. This is about 1 million each hour. Or another way to say it is that since you started listening to this talk, about 100,000 meteoroids have arrived. But don't panic, because almost none of them can reach the surface. They are generally no bigger than grains of sand, and they turn to dust long before they could hit the ground. Only bigger meteoroids visibly catch fire and become meteors. But still, the constant arrival of material that turns to dust and eventually falls to the surface represents a big volume, about 15,000 tons annually. This means that the Earth gains about 40 tons of material each day due to meteoroids. 40 tons that end up spread more or less evenly as dust on its surface. Why do these meteoroids burn and break apart? As you know, it is due to the density of the atmosphere in gases. They are heated to incandescence. In the upper atmosphere, the density is enough to heat them to incandescence. This is what creates a streak of light when the object is large enough. It burns and sheds glowing incandescent material in its wake. Shooting stars typically look much closer than they really are. They seem to be a few thousand feet high in the sky, but in reality they essentially happen in the mesosphere, which is 76 to 100 kilometers above our heads, 50 to 60 miles up. As you also know, it is the Earth's gravity that makes the meteoroids fall towards its surface. Sometimes they can be space debris that were in orbit around Earth, and they lost enough altitude to enter the atmosphere. But generally, meteors happen because of the Earth's motion. As it travels on its orbit around the Sun, it crosses streams of debris, for example, left by a comet, or that happen to cross its orbit, and this is what causes meteor showers, when suddenly plenty of big enough meteoroids enter the atmosphere together and become incandescent due to friction with air molecules. Friction, or in the case of slightly bigger meteoroids, something called ram pressure. So what is ram pressure? When a body moves through a fluid medium, like air, it compresses the medium in front of it, and this causes a drag force to be exerted on the body. In the case of an entry into the atmosphere, it leads to stronger heating of the air in front of it. It applies to meteoroids of a certain size, and even more to space capsules or space shuttles when they return to Earth. They were in the void, or quasi-void, and suddenly they enter a denser medium. There is air around them. So, as they move fast, the air in front of them is suddenly compressed. A shock wave happens, and this suddenly compressed air heats up because of the sudden compression. This hot air will flow around the object and in turn heat it up to hundreds of degrees. It is this phenomenon that heats up meteoroids and makes them burn, rather than friction, collisions with air molecules. But it depends on their size. If their size is big enough, from 3 or 4 inches or 10 centimeters in diameter and up, ram pressure is what causes the majority of the heating. When they are smaller than that, friction is the main cause, because they are too small to cause enough compression of air in front of them. A practical application of the understanding of ram pressure when objects enter the atmosphere is the design of space capsules or space shuttles. In the first years of space exploration, it was assumed that the best design for an object re-entering the atmosphere, returning to Earth after a journey to space, would be with a sharp, streamlined profile that would minimize friction and limit the rise in temperature. But a counterintuitive alternative was proposed, a large, blunt body concept. This is what you see in space capsules that return to Earth. They are shaped as cones, they're conical, and they present their base, which is wider when they enter the atmosphere. And this is because of ram pressure. It is taken into account that, given their size, the main contributor to heating as they fall towards the surface would be the compression of air in front of them. In other words, the transformation of their velocity, their kinetic energy, into heat, not friction with air. So the question is how to optimize the evacuation of this hot air around the capsule with minimal physical interaction. This is where the conical shape is a good one. The hot air that flows around the capsule does not heat that much the walls, only the base. Because the walls recede, they don't oppose much resistance to the air. To a lesser extent, the design of space shuttles is influenced by this. They have a large nose, not a pointed one. Of course, you still need a thermic shield made of material resistant to very high temperatures in the blunt base that will be in direct contact with compressed air. But this design turned out to be more efficient to facilitate re-entry into the atmosphere. Returning to meteoroids and asteroids that fall to Earth, as you also know, they are sometimes big enough to not shed all their matter during their crossing of the atmosphere. And so sometimes they impact the surface. They can even be big enough to create an impact crater. Let's take a look at their composition, their size, and in some extreme cases in Earth history, how they can impact, have an effect on the planet as a whole. Meteorites, the remains of a falling meteoroid, are not that common. Normally about half a dozen to a dozen a year are observed to fall and are recovered for analysis. There are certainly many more that go unnoticed or fall into oceans. But a few dozen meteorites a year is almost nothing when you compare it with the millions of meteoroids that enter the atmosphere every day. Out of these few meteorites, even less are big enough to create an impact crater. Most of the time they are no bigger than a pedal, and they create a small pit. But the possible crater and their size when they hit the surface is not only determined by their mass, a more important factor is what they are made of. Most of the time, impact craters on Earth are caused by metallic iron meteoroids. We will take a look at some of these craters in a minute. These are more resilient to the crossing of the atmosphere. Traditionally, 3 categories of meteorites have been distinguished. There are iron meteorites, which are one of them. They are largely composed of metal, especially iron and nickel. Then there are rocky or stony meteorites. These are made of silicate minerals, which means that at the atomic level they consist predominantly of silicon and oxygen. And there is a third category for composite meteorites called stony iron that contains a mix of metal and rock. So, as I said, most known impact craters were caused by the first category, iron meteorites, because rocky material is easily disrupted in the atmosphere, including asteroids or small comets with a mass of several tons. They will break in smaller pieces due to the heating and the shock wave, and each of these pieces will be reduced to dust, whereas iron meteoroids are more solid. They will still lose much of their mass before impact, but something may still exist. One hypothesis that has gained credibility in the past 10 years or so is that some of the complex organic compounds that are necessary to life on Earth could have arrived with meteoroids falling. They would not have included full living organisms, but big bricks of DNA and RNA that are fundamental to biological life as we know it. Why is this credible? First, because laboratory experiments under outer space conditions have shown that these compounds could form by chemical reactions on asteroids. Some very old meteorites, several billion years old, that were found on Earth have also been found to contain liquid water. This was not a surprise. It is believed that much of the water we have on Earth arrived via massive asteroid bombardments when the planet was still in formation. But more interestingly, they also contained prebiotic organic substances, that is to say, some of the ingredients, the bricks, that make biological life possible. So the idea that asteroids contributed to the emergence of life on Earth sounded like a long shot 2 or 3 decades ago, but it is not as unlikely as it may sound. These compounds can form in space, and they can also resist entry into the atmosphere. As we have seen, there is a degree of molecular destruction when the meteoroids crash and burn, but compounds may also be just spread during the fall or resisted inside a meteorite. There are thousands of meteorites in circulation in labs, museums, or private collections, and most of them are fairly small. The largest known one is the Hoba meteorite, and it fell in Namibia, Africa. It is believed sometime over the past 80,000 years. Its mass has been estimated to more than 60 tons, and it contains about 84% iron. It now has a bit of rust on its surface due to oxidation. The fall of such a big asteroid on Earth could have caused significant damage, theoretically, but maybe less than one could imagine in that particular case, because no big impact crater was found where it fell. An explanation could be the way it fell. These are just estimates, but due to its shape, it has been estimated that it slowed a lot during its fall. The entry speed into the atmosphere would have been typically in excess of 10 kilometers per second, that's 22,000 miles per hour. But at the time of impact, it would have slowed down to just about 320 meters per second, 720 miles per hour. That is to say, below sound speed. This was still probably a big, violent impact, but at this speed, and despite its mass, it would not have created a big excavation. And that also probably explains why such a big meteorite could stay in one piece. The most violent impacts in the planet's history, it is believed, saw the disintegration of the meteoroids or asteroids because they impacted at very high velocity and they disappeared. Their matter was scattered on a large perimeter and in the atmosphere. In recent history, a much bigger impact event is thought to be the Tunguska event, an explosion that is still somewhat mysterious, that happened in eastern Siberia in 1908. No impact crater was found, it is believed, because the meteoroid would have been stony and would have disintegrated at an altitude of 5 to 10 kilometers, 3 to 6 miles, up in the air. That would still have been enough to generate a massive shock wave, which flattened the forest on an area of 800 square miles, 80 million trees. In that case, the meteoroid would have been 50 to 60 meters in size, up to 200 feet. Because it happened only a bit more than a century ago, the Tunguska event is the largest recorded impact event in history. But much larger impacts happened in prehistoric times. The largest known impact crater on Earth is in South Africa. It is called the Vredeport crater, and it is estimated to be 2 billion years old. It is 100 miles wide, and it is believed the asteroid that hit must have been 10 to 15 kilometers, 6 to 9 miles in diameter. As you certainly know, it is estimated that an asteroid impact caused or at least contributed to the extinction of most dinosaurs millions of years ago at the end of the Cretaceous. This impact in South Africa is much older. 2 billion years ago, life on Earth would have been only ocean-bound, and organisms were small. But an impact of that magnitude probably had a catastrophic consequence on the whole planet, because of the shock wave initially, and then the tremendous amount of dust thrown up into the atmosphere, changing the climate for months to years. It is expected that an object bigger than 1 kilometer across, or 0.6 mile, could have a global impact, and the one that fell at Vredeport crater was at least 10 times that diameter. The second largest known impact crater is the Chicxulub crater in Mexico, on the Yucatan Peninsula. This one is much younger, 66 million years ago, and it is the prime suspect for the extinction of non-avian dinosaurs, that is to say, all dinosaurs minus birds, and also 75% of all species at the end of the Cretaceous period. At the time, the Yucatan Peninsula was under a shallow sea. It was not emerged like today. So now the crater is partially on land and partially underwater. But back then, the asteroid impacted the seabed. Contrary to 2 billion years ago, Earth at the end of the Cretaceous was teeming with terrestrial life. There were giant forests and all types of plants and animal species that were the ancestors of modern species. So the consequences on life in the case of that impact were probably much worse than the one that happened 2 billion years ago. First, because of the impact itself, that would have sent a splash of rock and debris into space, and upon their return to Earth, these flaming debris would have torched much of the planet. And then, because of a dust cloud that must have enveloped Earth for years, blocking sunlight, causing temperatures to drop and disrupting food chains. Now, this being said, should we worry about such a catastrophic event? Probably not. I mean, it is still possible, but statistically the probability that it happens during our lives or our children's lives is close to zero. There are more serious and pressing concerns to worry about. However destructive such an asteroid impact can be, it could also not really end life on Earth. Life is so diverse, it is everywhere, including in the depths of oceans where it does not need sunlight, that it could find a way to adapt and come back. And also, as the solar system ages, the quantity of large debris, of asteroids flying around on orbits that can cross ours, has diminished a lot. So all the very big impact craters are also very old. The youngest large impact crater on Earth, that is to say several miles in diameter, is in Tajikistan in Central Asia, and it is already 5 million years old. So now that we have looked at meteors and meteorites that fall on Earth, let's leave our atmosphere and head to where they come from, or to the places where asteroids can be found. The official definition of an asteroid is that it is a minor planet of the inner solar system. Minor planet because the one difference with planets is the size. Asteroids are smaller. And obviously there are similar bodies out of the solar system. Inner solar system means everything that is comprised between the Sun and the asteroid belt, a large region of the solar system that is located between Mars and Jupiter. But beyond the last planet of the system, Neptune, there is another larger belt, the Kuiper belt, that contains millions of bodies that could also be called asteroids. The only difference with asteroids from the asteroid belt is their location. But let's take a look at the millions and millions of bodies that float in the asteroid belt. Some fairly big, but the majority ranging from a few inches to a few feet at most. The asteroid belt is located 2 to 4 astronomical units from the Sun. one astronomical unit is the distance from the Sun to Earth. So it is 2 to 4 times farther from the Sun than we are. It is where the majority of independent bodies of that size in the solar system concentrate. Why there, instead of being scattered all around? The main hypothesis, based on models of formation of the solar system, is that these asteroids are shattered remains of planetesimals, bodies that appeared when the Sun was forming by accreting the matter, the dust that formed the disk in the early stages of the solar system. All planets of the system would be the products of this accretion. They absorbed all other bodies on and around their orbit by collisions and by attracting them due to gravitation. Actually, as we have seen earlier, this accretion process never ended completely. I told you how Earth keeps gaining thousands of tons of matter every year due to meteoroids entering the atmosphere. But now the phenomenon is marginal in comparison with what it once was, billions of years ago. So some of these bodies were satellised by planets, but the majority were swallowed. But not all planetesimals ended up being planets. Some were absorbed by bigger planetesimals, and others were ejected from the system, or at least from the outer solar system, by the gravitational influence of other planets, especially Jupiter. When Jupiter grew and neared its current mass, becoming by far the most massive planet of the system, its influence would have ejected over 99% of planetesimals in the belt, and no planet, no big enough body could form on this orbit between Mars and Jupiter. There were still collisions, but no body large enough to absorb the others ever formed. It is believed in this model that many objects in the belt entered in orbital resonance with Jupiter. If you are curious about orbital resonance, I tell you more about this phenomenon in the story about the moons of Jupiter. And this would have been what led to their ejection from the inner solar system. Another model also suggests that some of the asteroids that are now in the belt could have been captured in the outer asteroid belt beyond Neptune, the Kuiper belt, and dragged between Mars and Jupiter. So now there would be a mix of bodies, planetesimals that formed there but never became bigger than dwarf planets. For example, Ceres, the largest asteroid in the belt, which was big enough to become round and differentiate, that is to say, the heavier elements it was made of, metal, migrated to its core, and lighter elements like rock or water became wrapped around the core. It is believed Ceres formed in the asteroid belt, but not 100% sure. It could also have been one of these bodies attracted from the outer belt. Smaller asteroids would mostly be the remains of shattered planetesimals that did not collide with other ones to grow more, or stayed small, or were shattered by collisions. In any case, we should not picture the asteroid belt as one of these asteroid fields that we sometimes see in sci-fi movies, when spaceships have to slalom between floating rocks. This kind of environment doesn't exist in the asteroid belt. To find something similar, We will have to go inside the rings of Saturn, for example, where there is enough density of rocks and ices floating. We could cross the asteroid belt without even noticing it, because it is very empty. There are millions of asteroids, and about 1 million have been identified. They are much more common there than in any other part of the inner solar system, but they are scattered over such a large area that they can have millions of miles between them. Visually, the belt is not dense at all. About 1 to 2 million asteroids would be more than 1 kilometer large in diameter. That's 0.6 miles. And there would be millions more smaller than that. 200 asteroids are bigger than 100 kilometers. These ones have been named, and some of them have been explored by probes. Now, at the scale of the mass of the solar system, the asteroid belt is really not much. It is almost neglectable. If we were to put all the asteroids together, we would get only 3% of the mass of the Moon. And one body alone, Ceres, accounts for 40% of the belt's mass. We already explored Ceres in other stories, so we won't stop there tonight. But it is the only body of the belt large enough to be round. The next one, by mass, asteroids like Vesta or Pallas, are irregular because they are too small for their internal pressure to make their components melt, and they never took this round shape. The surfaces of Vesta or Pallas show that they collided in the past with other asteroids. They have craters. But nowadays, even though collisions can still happen in the belt, they have become rare events. Because of the large distances between asteroids, collisions have become unlikely, and most of the time, except if they take place with Ceres or Vesta, they will not lead to accretion. These bodies are relatively small. They don't have much gravitational pull. So instead they are more likely to shatter the asteroids into smaller ones. But all asteroids are not in the asteroid belt. There are other locations. First, there are asteroids that are called Trojans. They share their orbit with a larger planet or a moon, but they don't collide with it, because they have reached a point of equilibrium, of stability, that makes them orbit always at the same distance, ahead of or behind the larger body. Jupiter has many of these Trojans. More than 1 million, larger than 1 kilometer, are thought to exist on Jupiter's orbit. And unless a perturbation happens due to another body, they will not collide with Jupiter, because they always maintain the same distance. They are in two groups, one ahead and one behind of Jupiter. Mars has 9 identified Trojans, and Earth has 2. The largest one is 1.2 kilometers wide and was discovered in 2020. The other one was found in 2010. These are both recent discoveries, and this second one is 300 meters in diameter. They both are hundreds of times more distant than the Moon, but they could be less costly to reach in terms of energy, because they are on the same orbit as our planet by definition. They are small, but one day in the distant future, they could be a valuable source of rare elements that are technically present on Earth but very hard to access. For example, iridium, a very dense metallic element. There is iridium on Earth, but due to its density, it mostly sunk to the core of the planet shortly after its formation. These asteroids may have a similar composition to Earth, rock and metal, but since they are much smaller, it could be easier to access these elements, these rare elements on them. And out of the asteroid belt and trojans, there is also a smaller number of asteroids on orbits that pass close to planets. As of today, if we take Earth as an example, almost 30,000 near-Earth asteroids have been identified. These are the ones that are most observed for the possible hazard they represent. Their orbits are typically unstable because they are perturbated by the Earth's orbit. Most of the time, it will result in their ejection from the solar system or a collision with the Sun, a planet, or another body. Of course, it is extremely unlikely that a collision will happen every time they complete an orbit. But if you give it millions of years, millions of orbits, it will happen eventually. For that reason, these near-Earth asteroids survive in their orbit for just a few million years. There are still some, thousands of them, because they keep arriving. It is believed that they generally come from the asteroid belt. The orbital resonance with Jupiter makes them migrate towards the inner solar system, closer to the Sun, where they come nearer the terrestrial planets like Mars, Earth or Venus. A small number of near-Earth objects are also thought to be extinct comets that can no longer produce a tail because the elements that produced the tail have all been consumed. As you see, there is a variety of asteroids, and contrary to the orbits of planets that have remained fairly stable for billions of years, these asteroids are subject to various influences that can make them change position in and out of the solar system. These celestial bodies transit, they travel, and we now know that they can travel between star systems. So let's talk about Oumuamua, an object that attracted much attention in the past few years because of its shape and because of its origin. It is likely to be extrasolar. The shape is elongated like a cigar, and it measures between 100 and 1,000 meters, that's 300 to 3,000 feet. Oumuamua is a Hawaiian name because it was detected from an observatory in Hawaii. I told you earlier that objects, asteroids, may be expelled from the solar system. We mentioned it when we spoke about the influence of Jupiter. But it does not make them disappear, of course. If they leave our system, they will travel in space, and eventually they can reach another star system, even though space, included inside a galaxy like ours, is mostly void. Star systems are very distant from one another. Typically the distance has to be expressed in light years, but statistically, ejected objects will end up crossing the path of other systems. That can include planets. We know that some planets are not bound, no longer bound to a star, and travel alone in space. Oumuamua is not very big compared to common asteroids in our system. we saw earlier that more than 1 million of them in the asteroid belt could be larger than 3,000 feet, and Oumuamua barely enters this category. But what revealed its origin is that it did not travel on a sun-bound orbit. It entered the system on a trajectory and with enough velocity to not be captured, meaning that it would cross our system and then continue its journey. When it was first observed, it was only 0.2 astronomical units away from Earth. That's pretty close at the scale of the system. Only 85 times as far away as the Moon. And when it was spotted, it was already heading away from the Sun. Another thing that drew attention was that when it approached the Sun, it exhibited an acceleration that was not due to the gravitation of the Sun. This was weird. It could have suggested that it produced its own thrust, but not unexplainable by natural phenomena, because the Sun may have an influence on other bodies beyond its gravitation. It can provoke outgassing, we will see what it is when I tell you about comets, or it can push things away due to the pressure of its radiation. But of course, between the shape of Oumuamua, its extrasolar origin, and its trajectory and acceleration, it raised the question of a possible trace of alien technology. Why not an interstellar ship? That would be a strange ship. The surface looks red and similar to natural objects in the outer solar system. So it does look like a natural body, despite its unusual shape. A small number of astronomers suggested that Oumuamua could be a product of alien technology. They did not say it was, but just that the phenomenon was unusual enough and hard to explain enough to call for attention. The majority believes that it is a natural object, and there are several hypotheses about how it formed. It could be a remnant of a disintegrated exocomet, a comet outside of the solar system, or a piece of an exoplanet from beyond our solar system. But it is true that this is a particularly strange object that will probably continue to draw attention in the coming years because it is still inside the solar system. Now let's talk about a particular type of bodies that are close to asteroids, but with a few particularities: comets. As of today, there are more than 4,000 of them that are known in the solar system. And their most obvious difference with asteroids is that they can sometimes be seen from Earth to the naked eye, because they create a long, luminous tail in their wake. Why is that? And how do comets work in general? The center, the nucleus of a comet, is hardly distinguishable from an asteroid. It is a loose collection of agglomerated ice, dust, and rock. The term ice here does not only refer to water ice, like on Earth. In astronomy, ice is a term for compounds that are often found solid in space due to the low temperature, but that are volatile. They can be readily vaporized. It can be water, but astronomical ices also include carbon dioxide, nitrogen, ammonia, methane, sulfur dioxide, and others. So all of this is contained inside the nucleus of a comet. Some comets are small and measure a few 100 meters across. Others are giant and measure tens of kilometers or miles. Like everything in the solar system, comets follow an orbit. But this orbit is highly elliptical and eccentric. Instead of revolving around the Sun at almost always the same distance, like Earth, for example, Earth does not have a perfectly circular orbit. As you know, at some moments of the year, it comes slightly closer or slightly farther from the Sun. But the difference in distance is comparatively very small, whereas comets can be 10 or 100 times farther from the Sun when they reach their most eccentric point than they are at the least eccentric point. We will see later that the type of orbits they have and the frequency of their returns near the Sun depends a lot on where they come from. But the big specificity they have is that when they approach the Sun, following their orbit, solar radiation and the solar wind warms the ices they contain, and because they are volatile, they separate from the nucleus. They are released, and this is the phenomenon called outgassing. These gases, water vapor, carbon dioxide, methane, also take dust with them, and they generate a kind of atmosphere around the nucleus. This atmosphere is called a coma, and it reflects enough sunlight to be visible from afar. This coma is not bound by gravitation to the nucleus, because the nucleus is not massive enough for that. So it can visibly stretch behind the nucleus on long distances, up to 15 times the Earth's diameter. It would disappear quickly if it was not renewed by the continuing effect of the Sun's proximity. These are basically volatile elements ejected from the comet's nucleus. And actually the comet does disappear when the comet has passed near the Sun and starts to go away on its eccentric orbit. Once it is far enough for ices to stop outgassing, the comet goes away, it disappears, and the nucleus comes back to the appearance of a regular asteroid that will continue on its orbit and will stay without a comet for years or up to hundreds of years, depending on how long it takes to return near the Sun on the comet's particular orbit. But the most visible part of a comet that passes close enough to the Sun is not this coma, actually. It is the tail. The tail is a second section of gas and dust from the nucleus that is blown out from the coma by the Sun's light pressure and the solar wind. This stream of tiny particles that the Sun constantly emits. And the tail will typically be even longer and more visible than the coma. It can stretch beyond 1 astronomical unit, more than the Sun-Earth distance. This tail is typically what we picture comets with. As comets consume some of their matter to produce their coma and their tail every time they pass near the Sun, they have an expiration date. The nucleus will end up exhausted once it can no longer outgas, and it will keep revolving around the Sun until it changes orbit. But as a common asteroid, a dead comet, the solar system has existed for billions of years already, and yet there are still active comets. So how is that possible? they should have died long ago. This is possible because there is a giant reservoir of potential comets beyond the orbit of Neptune, in the Kuiper belt, and even more beyond it, in a spherical cloud of icy bodies that extends beyond the Kuiper belt, and that is called the Oort cloud. It is believed that these potential comet nuclei can be set in motion in the Kuiper belt by the influence of planets, and in the Oort cloud by gravitational perturbations at the scale of the galaxy, for example the passing of other stars. If their orbit is modified and brings them close enough to the Sun to start outgassing, they become comets. So depending on where they originate, there are short-period comets that need a few decades to complete an orbit, and long-period comets that need much more time. The reservoir of comet-like bodies in the Oort cloud is estimated to be 1 trillion, 1,000 billions. This is why, with only a few thousand active comets at any given time, we will never exhaust this stock of potential comets. The solar system will disappear long before. The way comets work has been studied and quite well understood for decades, but more recently, probes have visited them, and that was quite an achievement given their speed and their small size. A probe called Deep Impact, sent by NASA, blasted a crater on a comet called Tempel 1 and photographed it to study its interior. And another probe, Rosetta, sent by the European Space Agency, was the first to land on a comet and send information from there. All comets do not stay bound to the solar system. I told you earlier that there were exocomets that could travel between stars. This happens if the trajectory of a new comet does not allow it to form an orbit around which it will keep traveling. These are called hyperbolic comets. After one passage near the Sun, they are ejected from the system and may or may not reach another system one day, where they will deploy their tail again if they come close enough to another star. Some of the most famous and expected comets include Halley's Comet. It is named after Edmund Halley, the publisher and friend of Isaac Newton. Using Newton's work, he realized that a comet that had been sighted in 1531 and 1607 and reappeared in 1682 was in fact the same body, not three different bodies, and calculating its return, taking into account the perturbations the comet would sustain from the gravitation of the planets, he forecasted the comet would reappear in the sky in 1758. Indeed, it did reappear in December 1758. The comet has a period of 75-76 years. It varies a little bit each time due to the effect of the more massive planets of the system, like Jupiter or Saturn. The last visible passage of Halley's Comet was in 1986, and it is expected to return by mid-2061. This comet was also the first to be observed in detail by spacecraft during its 1986 visit to the inner solar system. A lot of hypotheses about how comets work were validated thanks to these observations, especially the prediction that the comet's nucleus would be composed of this mix of rock, ices, and dust that we discussed before, like a dirty snowball. This was the name given to the hypothesis that comets were made of such elements, and it was outgassing that liberated the coma and the tail. When this comet is not in the inner solar system, it returns to the Kuiper belt. It goes beyond the orbit of Neptune at a distance of 35 astronomical units, roughly the distance of Pluto to the Sun. It reaches its farthest point from the Sun. This point is called the aphelion, and then it starts coming back. Overall, it takes about 75 years to complete one orbit. Comets are classified as short period when their orbital period is under 200 years. So Halley is a short period comet. Above 200 years, there are long period comets. And a famous example of long period comet is Hale-Bopp, which became visible in the 1990s and was one of the brightest seen for decades. Hale-Bopp has an orbital period of 2,500 years, so needless to say we won't be alive to see it again. Its aphelion, the farthest point from the Sun, is at 370 astronomical units. That is 10 times farther than Halley's comet. It has a much longer orbit and comes from the Oort cloud. It stayed visible for 18 months in the 1990s, so we have plenty of photographs that show very well the coma and the tail. As of today, in 2022, Hale-Bopp has already crossed the orbit of Neptune again, and even Pluto, and it is traveling in the Kuiper belt. It will keep moving away from us for more than 1,000 years, and then begin its travel back after centuries and centuries spent in the silence and darkness of space, where the Sun is only a tiny point on the horizon. We are going to travel across the galaxy and beyond. Travel to explore space oddities, phenomena that defy our imagination or keep a part of mystery, like neutron stars or black holes, or phenomena that are speculative, hypothetical, like dark matter, and types of planets that could exist theoretically, even though they have never been observed and proven, and more existing or possible phenomena. For our first visit, we are going to leave the solar system and travel a few hundred light years, which is pretty close at the scale of the galaxy, to explore a fairly small but incredibly dense object, a neutron star, the closest one ever found. And I will also tell you about pulsars and magnetars. What is a neutron star? To understand it, we need to talk about the life cycle of stars. As you may know, it is believed, and there is strong evidence about that stars appear, live, shine, for generally billions of years, and then they die, they disappear, when they have exhausted the fuel they contained, when the fusion reactions between atoms that powered them is no longer sustainable. When this happens, the star does not slowly shrink and turns dark. It dies with glory, and the way it dies depends on its size, on its mass, and on its composition. A star about the size of the Sun, or a bit less, which is average in comparison with other types of stars, will tend to become a red giant, and what will remain of its core after that is called a white dwarf. But what does it mean? A red giant is what happens when the core of the star runs out of its main fuel, hydrogen, that for hundreds of millions of years it fused into helium. It is not like a switch that would suddenly be turned off. The phenomenon takes time. Hydrogen becomes rarer inside the core of the star, but the fusion reaction goes on, including in its upper layers. But the core is where hydrogen goes missing first, and when it happens, the core contracts because of gravity. This contraction makes it heat up. It becomes warmer than it already was. And in turn, this heats up the outer layers of the star. As a result, the star begins to grow, not in mass, but in volume. It occupies more space, because the outer layers inflate. And this is not a marginal change. The star becomes gigantic compared with its past size, dozens of times bigger. For example, in the case of the Sun, it is expected to grow so much that it will reach the Earth's orbit when it turns into a red giant. But this is not the end yet, because inside the core of the star that has contracted and heated up, temperature and pressure have become sufficient to start fusing not just hydrogen, but heavier elements, especially helium, the product of hydrogen fusion. So, at this stage, helium atoms fuse, merge, into oxygen and carbon atoms. And for some time, the star keeps living on its stock of helium, until helium also runs out. And at this point, the end is near. There is no fuel left to burn that could keep the star producing energy. If you would like more explanations about that, you will find them in the story about nuclear fusion that I will link in the description. The general rule is that fusion of light atoms is exothermic. It makes energy available to be released because the new atoms need less binding energy. The bigger atoms are, the more likely they are to need extra energy to fuse, and so the reaction becomes endothermic. It needs energy available to be consumed to take place. This is why the fusion of heavy atoms cannot be a good fuel for a star, because instead of releasing energy, it consumes some. So, as fusion reactions die down in the core of the star, where carbon and oxygen pile up, the core expands again and cools down whereas the outer layers of the star dissipate, and their matter forms what is called a planetary nebula, a cloud of matter floating in space. The core cools into what is called a white dwarf, a body where fusion reactions no longer take place. It is mainly made of carbon and oxygen, and it is much smaller than the original star. The Sun, for example, could end up having about the size of Earth, but a white dwarf is still very massive. Some of its matter has been shed and is now part of the planetary nebula. But a white dwarf produced by a star a bit more massive than the Sun could perfectly end up being as massive as the Sun is, while having the size of a planet. This very dense body is called a white dwarf because even though it no longer generates new energy with fusion, it is still intensely hot, and it keeps radiating, emitting energy. White dwarfs may still appear as very small stars, little shiny points with a faint light for billions of years. But eventually they should cool down and turn into black dwarfs, the dead core of a star that is now cold and no longer radiates light and heat. I said should because the transformation of a white dwarf into a black dwarf is estimated to take a very long time, actually more than the 13 billion years that is the estimated age of the universe. So at this point, even the very first stars would not have had time enough to turn into black dwarfs. And if these estimates are correct, black dwarfs are objects that should start to appear in the future, in billions of years, but there are none yet. So that was the outcome of the death of a star that belongs to the same category as the Sun. It turns into a red giant, loses some of its matter, that forms a planetary nebula, and the core remains as a white dwarf. But as you see, the sequence of events in the late stages of the star's life depends on physical reactions that happen inside it. And these reactions depend on the mass of the star, its quantity of matter. What if the star is much bigger than that, 10 or 20 times bigger, more massive than the Sun? A giant star. In this case, the core of the star is also much bigger, and this means that the gravity, the gravitational force, and the heat inside the core are going to be higher, so high that fusion reactions can go on after the disappearance of hydrogen and helium, because there is enough energy available. These giant stars go through the same process of exhausting their hydrogen reserves. Then they fuse helium atoms, and turn them into carbon and oxygen. But at this stage, their mass is enough to fuse carbon into heavier elements: neon, silicon, sulfur, iron. And only once these elements, especially iron, form the core of the star, it can burn no more. With the extinction of fusion reactions comes a collapse. As fusion reactions no longer push outward, the star's core suddenly collapses on itself due to gravity, and it becomes so tightly packed that even subatomic particles like protons and electrons merge. In other terms, the gravitational force is enough to overcome the resistance of atoms. As you know, there is a lot of void inside atoms, a lot of distance between the nucleus and the cloud of electrons around it. The sudden disappearance of this void makes the core shrink dramatically. A star's core the size of Earth can shrink to a ball with a radius of just a few miles. And in this core, subatomic particles have merged. As you know, a distinction is usually made between three different types of particles inside atoms. There are protons and electrons, which each have opposite electric charges, and neutrons, which have no net electric charge. In reality, protons and neutrons are themselves made of smaller particles, but we don't need to go into that for tonight. The mergers of protons and electrons form only neutrons, and the atomic organization of matter disappears. The core turns into a dense pile of neutrons, where, due to this sudden compression, temperature rises to inconceivable levels, billions of degrees. The outer layers of the star are suddenly pulled into it, which crushes it even further, and the sudden accumulation of energy cannot be contained. So the core explodes, and happens what is called a supernova, an explosion that sends a powerful shock wave in space and disseminates large amounts of matter, of material, into space, especially these heavier atoms like iron and others that have just been produced by fusion reactions, from gold to uranium. It is believed that all these elements that are present around us, and including inside our bodies in small quantities, must have appeared and been disseminated by a supernova of this kind billions of years ago, before the formation of the solar system. And when our system formed, it reused some of this matter that had been transformed in the last moment of an extinct star system that disappeared before the solar system began to form. So finally we are getting there. What remains of a giant star, above 8 to 10 times the Sun's mass, can form a neutron star, which is actually smaller than a white dwarf, but much denser. Inside a white dwarf, gravitation is not enough to break the resistance of atoms. So a white dwarf remains made essentially of carbon and oxygen. The elements remain distinguishable, whereas inside a neutron star, there are no longer distinguishable elements, just a mass of neutrons, because as we saw before, electrons and protons have merged. So typically a neutron star is 1,000 times smaller than a white dwarf, but with a similar mass and sometimes a bigger mass. Neutron stars are like an intermediary body between white dwarfs and black holes that we will talk about later. If the giant star is not 10 or 20 times more massive than the Sun, but 50 or 100 times or more, The collapse of its core may theoretically create an even denser black hole. It is believed that neutron stars can appear when stars that are at least 8 to 10 times more massive than the Sun and up to about 25 times the Sun's mass end their life cycle. Below 8 times, a white dwarf is more likely, and above 25 times, a black hole. But it is not that systematic, because the mass is not the only factor. The richness of the star in metal can be one too. We will visit a black hole later, but for the moment, let's talk about neutron stars and the different forms they can take. First, white dwarfs are probably much more common than neutron stars. It is estimated that 97% of stars are not big enough to form a neutron star, and only an even smaller fraction are supergiants that can leave a black hole when they die. This state of matter, where there are only neutrons, results from a kind of equilibrium. Pressure, gravitation, is strong enough to compress matter to the state of neutrons. But on the other hand, there are forces that prevent further collapse, forces that protect the integrity of neutrons. These forces are called neutron degeneracy pressure and repulsive nuclear forces. We don't need to go further into these forces. Let's just bear in mind that they resist, they counterbalance gravitation and stop the collapse. But this works up to a point. Theoretically, a neutron star can have up to twice the Sun's mass, above about 2 times. This is just an estimate, and it is still discussed between physicists, because different forces are at play, and their sum, their interaction is complex to estimate. But it gives an order of magnitude. So above 2 times, the collapse process could not be stabilized, and further collapse of the core of the body on itself would happen. Further compression would make a black hole appear. A black hole with still the same mass, but occupying an even smaller space, and in which even neutrons have disappeared. But we will come back to that. Still, even though they are not black holes, neutron stars have a density that is hard to imagine. The mass of a star like the Sun, contained inside a body that is just a few miles across. This means that a little bit of neutron star material contains an extraordinary quantity of matter. To take an example, the bodies of all humanity, all 7 or 8 billion people, compressed like that, could fit into a matchbox, and there would be some space left in the box, because precisely a matchbox of neutron star material would be estimated to weigh about 3 billion tons. Gravitation at the surface of a neutron star would be around 200 billion times what it is at Earth's surface. This is inconceivable. And another consequence of this enormous mass in a small space is a strong magnetic force, a powerful magnetic field that surrounds the body. I will also link another story for more explanation about what magnetism is, how it works, in the description. But these powerful magnetic fields are important because they are organized around two poles, like the Earth's magnetic field, but billions and billions of times more powerful. A magnetic axis exists between these two poles, and the magnetic fields may funnel jets of particles out along the two magnetic poles, so a beam of radiations can come out of the pole. And another characteristic of neutron stars is that they rotate very fast on their axis. They rotate fast because the much bigger star they were born from rotated. And when it disappeared, the core kept this rotation. But it is much smaller, so the rotation rate measured at the surface became much higher. In physics terms, there is a conservation of the angular momentum. But you can easily picture it, imagining a figure skater doing a spin. When they are spinning, their rotational speed can accelerate if they draw in their arms. It is not an acceleration due to an additional effort, it is because drawing in the arms decreases the inertia, the moment of inertia, and mechanically it makes them rotate faster. This is what happens, on a different scale, when the star's core collapses to become a neutron star. The radius suddenly diminishes, but as the angular moment remains constant, the rotation accelerates. So typically a neutron star rotates on its axis in a matter of seconds or even milliseconds, extremely fast. Now, when you combine these radiation beams coming out of the magnetic poles and the fast rotation, you get what is called a pulsar. Seen from afar, like from Earth, or more exactly observed from Earth with instruments, because pulsars are not visible to the naked eye, and instruments are necessary to detect their beams of radiation. So, seen from afar, a pulsar is like a lighthouse that would rotate very fast. Each time the beam points at the observer, a signal is perceptible, and this signal repeats very regularly. It follows the neutron star's rotation. Pulsar means pulsating radio source, and thanks to this signal that they repeat very regularly, thousands of them have been identified in our galaxy alone. This is only a fraction of existing pulsars, probably, given the number of dead stars in our galaxy. I told you earlier that the majority of stars are not massive enough to leave a neutron star behind. But there are billions and billions of stars in our galaxy, so that still leaves hundreds of millions that are big enough to turn to a neutron star and become a pulsar. A particular and less frequent type of neutron star is called a magnetar, because they have an extremely powerful magnetic field. They are not necessarily bigger than other neutron stars. As we saw, their mass cannot exceed 2 solar masses, otherwise they collapse further. But their magnetic field is particularly powerful, and they tend to rotate slower than pulsars, typically 1 every 2 to 10 seconds. Magnetars have been identified separately from pulsars because they are responsible for bursts of rays that were detected from different parts of our galaxy. and they became the best explanation for that phenomenon. As of 2021, 20 to 30 magnetars have been located in the Milky Way. Not many in comparison with the thousands of pulsars, but this is because magnetars have a short lifespan. Their magnetic field decays quickly in a few thousand years, and so they become less active and detectable. So there are probably millions of inactive or less active magnetars in the galaxy, and only the youngest have been spotted, the ones that produce spectacular bursts of rays. At this point, we have seen what happens to stars the size of the Sun, a bit less or up to 7-8 times the Sun's mass. What happens to giant stars, the ones that tend to turn to neutron stars, up to about 25 solar masses. But what about supergiant stars that are more than 25 times bigger than the Sun? In their case, the collapse of the core on itself does not end in a pile of neutrons. The neutrons themselves are crushed and cease to exist as such. They form a body whose gravity is so strong that nothing, including the fastest particles or rays in the universe, can escape it if they come close enough. Very dense objects, like neutron stars, may have a very strong gravity, but this is not enough to capture light, for example. To understand it, we need to talk about the concept of escape velocity. When we are on Earth and we throw something at the sky, it falls back, a little bit because there is friction with the air. This may slow the object down as it rises, but if it falls back, it is because the gravitational pull of the planet attracts it back to the ground. The more energy, the more velocity what we throw has, the higher it can go before falling down. A basketball thrown by hand will rise a few meters. The bullet from a gun can go higher. But this is still not enough to escape the planet's gravity. To escape it, you need to either provide more thrust as the object rises, for example a rocket. When a rocket traveling to space takes off, additional push is provided for several minutes as it burns its fuel reserves. And this is how it can free itself from the Earth's gravitation. Or you need to give the object enough push, enough initial speed, that the planet's gravity will not be sufficient to stop it from escaping. This is the concept of escape velocity, the minimum speed necessary to break free from the gravitation of an object with a mass. It depends directly on the object's mass and the distance of your starting point from the center of this mass. For example, the escape velocity from Earth's surface is about 25,000 miles per hour. That's 40,000 kilometers per hour. Man-made ships do not reach this speed, and rockets manage to escape despite lower speeds only because they have a continuous thrust during their ascension. Bodies or particles in space don't have that self-propulsion. They receive some kinetic energy. that they don't lose as long as they don't collide, but they don't accelerate by themselves. So, the more massive the body you try to escape is, the fastest you need to go. And this concept was understood long ago, in the 18th century, with the elaboration of the theory of gravitation. And soon, this theoretical development led to a theoretical question. What if an object was so massive, with such a strong gravitational pull, that its escape velocity was higher than the speed of light itself, the speed of light being the highest conceivable speed, at least based on our current understanding of physics? Then, in that case, nothing, not even light, could escape such a body. This is the concept of a black hole. A body so massive, which doesn't mean so large, matter is so compressed inside of it that a black hole does not need to occupy a lot of space, but a body so massive that once something has been captured by its gravitation, no escape is possible. Or, at least conceptually, no escape without self-propulsion. This is why they are called black holes. Black because not even light can escape them, and you can literally fall into them. But the term hole can be a bit misleading because they are very, very dense, the opposite of a void. For an astronomical black hole to form, a mass of at least 2.5 to 3 times the Sun's mass is necessary. Below that, the mass is not enough for the core of a star to keep collapsing on itself. But if 3 solar masses is the lower limit, you may wonder why there are stars that are dozens of times more massive than the Sun. And yet they don't turn to black holes. This is because as they burn their fuel during their life, other forces compensate for gravitation and prevent the star's core from shrinking. It is when these reactions die down that what is left of the star, the core, can finally collapse on itself, and if it is massive enough, turn into a black hole. Black holes are sometimes pictured as irresistible vortexes that will swallow anything. This is true if you come too close to them, but their gravitation, their impact on other bodies, is not more powerful than other objects of a similar mass. A black hole with 5 solar masses has the same gravitational pull as a star with 5 solar masses. And there are plenty of them. So black holes can have satellites. They can capture other bodies with their gravitation. But it doesn't mean they will end up swallowing them if these bodies are far enough and have their own speed. If this is the case, the captured body will keep its distance with the black hole. It will stay on an orbit around it. The limit, the point of no return of a black hole, is called the event horizon. Beyond that frontier, beyond that limit, there is no escape left. But as long as it is not passed, a high enough velocity will allow fast particles to escape, like light. This is why, visually, the event horizon would be like the limit, the boundary of the black hole. Everything beyond it is dark, because light cannot escape. I will leave the physics of what happens inside a black hole for another time. This topic is complicated and still discussed between physicists, in particular because it is believed that at the center of each black hole there is what is called a singularity, a point where gravitation becomes infinite, and there is no theory at this point that can model or describe this phenomenon. But if we keep an external look, a lot of discoveries of black holes have taken place in the past few decades, and two main groups are identified. There are stellar mass black holes, the ones that form when large star cores collapse under their own weight, and there are supermassive black holes, the ones that are believed to be at the center of galaxies and have much higher masses, billions of times the Sun's mass. The origin of supermassive black holes is poorly known, but what is likely is that black holes can grow. They can absorb more matter, capturing objects. They can merge, including supermassive black holes when galaxies collide. And as you may have seen, the first pictures of black holes were released. What we see on them is obviously a black spot, but it is contoured by light. And this sounds paradoxical. I just told you that black holes did not let light escape, by definition. So why would there be like a visible ring around them? What we actually see, and this is an illustration of Einstein's theory of relativity, is an effect of the black hole on its environment. The definition of gravitation, according to Einstein's theory, is that massive objects affect others because they curve, they warp the space-time, the fabric of the universe. The bigger the mass, the stronger the warping, the curvature. And this curvature does not only affect objects which also have a mass, as Newton's initial theory supposed. It affects everything, including light, which is without mass. The ring of light that we see on these pictures is not emitted by the black hole. It would come from the effect of the black hole on its surroundings, where space-time is warped, and this affects the path of visible light, allowing us to see something. There would be much to say about black holes, but we have more things to see in our cruise, and space oddities are not limited to what stars turn into when they die. We have seen that black holes could be extremely massive objects, and as such contain a big chunk of the matter that exists in the universe. Maybe the majority of it. Or do they? Let's talk about dark matter, a hypothetical form of matter whose existence has never been directly proven, but that could represent around 85% of the matter in the universe, if it exists. What is this, and why is this hypothesis seriously considered? To understand it, we need to go back to the 20th century, when astrophysics and observation of faraway galaxies made giant leaps forward. At the time, the theories of gravitation and Einstein's theory of relativity were already well known and accepted as valid by the scientific community. But a number of observations did not really fit them. In particular, the observation of galaxies and how they move in space, the observation of their motion. It was observed that galaxies could travel away from each other, and this was an important step in realizing that the universe was in constant expansion. Galaxies also are big masses that interact with each other via gravitation, even though they can be far apart. But the mapping of the universe, at least what we can see of it, soon revealed that something was off. Many galaxies did not behave as they should have, based on their estimated mass and the laws of gravitation. But the laws of gravitation cannot be thrown away easily. They work, and their predictions have permitted many discoveries, including planets that were guessed before they were observed. So if gravitation was not the problem here, it had to be the mass of these galaxies that was not correctly estimated, and sometimes widely so. Some galaxies should have been more than 10 times more massive than they seemed to be, to explain their influence, their interactions. This was the unexplained mystery that gave birth to the hypothesis of dark matter. Dark because it is undetectable as of today. Not only visually, but also because it seems to not interact with the electromagnetic field, which means it does not absorb, reflect, or emit any radiation. And so it could be of a different nature than the matter we know of. Its only shared property with familiar matter would be that it has a mass. This is why dark matter is speculative. It is deducted from our inability to explain observed phenomena. The motion of galaxies is not the only clue that points to its existence. There are other lines of evidence, such as the formation and evolution of galaxies, or the measurement of what is called the cosmic microwave background, a radiation that is a remnant from an early stage of the universe. That makes a lot of unexplained phenomena that could be explained by the existence of dark matter. The problem is that no one has ever observed it, assuming it exists. All about it is hypothetical. Its only interaction with known matter would be through gravity, but we have no idea of its possible nature. Are these gigantic but undetectable masses, or a few particles with enormous gravitational force, or something we have not managed to conceive? The primary candidate today would be a kind of unknown subatomic particle, unknown as of yet. The strength of this hypothesis is not just because the existence of dark matter would avoid having to throw away the gravitation theory, which would be very uncomfortable. It is also that its existence can be deducted from various independent approaches, as I said before. Solving the problem raised by one of these approaches with a different explanation than dark matter would be a thing, but solving all of them looks very difficult. And for that reason, even though it is unobserved, elusive, and at the same time would be expected to make the bulk of matter in the universe, this hypothesis is still the one favored by the scientific mainstream. That's an ongoing mystery, and it is humbling. if dark matter is real, it means that at this point we barely know about 15% of the matter in the universe, and the rest escapes our perception so far. But if it does not exist, it is maybe worse. It means that large parts of physics fall down, and we become unable to explain a lot of observations that have been repeated many times and look solid. Until now, in our cruise, we have been looking at large-scale objects or phenomena. But on a smaller scale, at the scale of planets, there could also be bodies that can theoretically exist and would challenge our knowledge of planets. Our knowledge of planets being primarily based on the observation of the solar system. We have two big types of planets in our system. There are rocky or telluric planets with a metallic core. It is believed because heavier elements tend to migrate to the core in their formation process, and around this metallic core they have a rocky envelope where the dominating elements are silicon, oxygen, hydrogen, and to a lesser extent plenty of other elements in smaller quantities. And then there are giants, planets with probably a metallic core too, but around it layers of gas. And these ones are divided into gas giants when they are mainly made of hydrogen and helium, like Jupiter and Saturn, and ice giants when they contain more astronomical ices like water or ammonia, like Uranus and Neptune. But the solar system is just one system among billions, and nothing says that other types of planets do not exist. Planets with a different structure or a different composition. This is all speculative, but theoretically possible. And now we are going to review different types of planets that may or may not exist somewhere in the universe, like coreless planets, carbon planets, planets covered by oceans, or orbiting around a black hole. The concept of a coreless planet is not a hollow planet. Hollow planets were imagined in different contexts, including in fiction along history. But given what we know about the universe, it looks impossible for a hollow planet with just a shell to form. There is no reason for a void to exist inside, at least not naturally. A coreless planet would be a rocky planet without a metallic core, a terrestrial planet that would just be a giant rocky mantle. The formation models take into account the type of material available when planets form around a star, and there is a lot of metal in this material, especially iron. As we saw before, when I told you about the appearance of new heavier atoms in large stars when they reach their last moments, iron is a frequent outcome of fusion reactions, and for that reason it is relatively abundant. So a rocky planet without a lot of metal and a metallic core is hard to conceive. If we look at the solar system, we even have an example of almost the opposite, with the case of Mercury, which has a big metallic core proportionally and a small rocky mantle. But the formation of a planet made primarily or mostly of rock material is not unthinkable. It would theoretically be possible in cooler regions of a system far from the star. A first mechanism would be when the planet accretes far from the star in a colder environment. Accretion means the progressive absorption of material on its orbit by gravity. And in that case, it would happen in an environment where metallic iron is bound into silicate material crystals. In other words, iron would be trapped into rock structures that will not melt and will not let it escape. In that case, the formation mechanism would not allow metal and rock to be separated and the planet to differentiate, that is to say, to have a core and a mantle with different compositions. Another possibility would be that the planet accrete from water-rich and iron-rich material, also slowly enough and far enough from the star for water and iron to react and form iron oxide, rust, before differentiation of a metal core has taken place. In that case, provided iron droplets are mixed enough with the other elements, iron could stay entirely trapped in the mantle and no core could form. Maybe we have already detected coreless exoplanets, and we don't know it, because apart from their internal structure, their sizes are expected to be similar to planets with a core. They would form far from the star, based on models, but this does not exclude the possibility of a migration within a system, so they could move to a closer orbit later. The opposite to a coreless planet would be an iron planet, a type of planet with a metal core and little to no mantle. Mercury is almost one, and that is proof enough that metal planets, or almost metal-only planets, are a possibility. The formation process here could be different. These planets are expected to form near the star, because this is where the concentration of iron-rich material would be found when a new star system appears. They could form naturally with mostly metal, but like it is hypothesized for Mercury, they could appear after collisions. A regular terrestrial planet would form, and later, large collisions with asteroids would strip it of its mantle that would be ejected into space and lost. So the iron planet, in that case, would be the remaining core of a rocky planet that has been exposed and has cooled down. A consequence of being a metal planet is that there could be no plate tectonics or volcanism, just different layers of metal with a colder, solid outer layer and a hotter core where metal is melted. Yet another type of theoretical planet with a different composition would be a carbon planet. Not a planet made only of carbon, but one where there would be more carbon than oxygen. What does it mean? rocky planets in the solar system, like Earth, Venus, Mars, formed in an environment where there was more oxygen than carbon, almost twice more. Their carbon to oxygen ratio is around 0.55. It means that in terms of mass, Earth, for example, has a bit more than 2 pounds or 2 kilograms of oxygen for 1 pound or kilogram of carbon. What we call rock are compounds made mainly of silicon and oxygen, silicates. This seems to be the norm, because oxygen is more abundant than carbon in the universe. Oxygen is the third most prevalent element, after hydrogen and helium, whereas carbon comes in fourth. But we also know that all star systems don't have the exact same carbon to oxygen ratio. Some are richer in carbon than ours. For example, exoplanets have been detected with a higher carbon-oxygen ratio, as high as 0.78. And so there could be planets which would look like Earth in terms of size and internal structure, but the domination of carbon over oxygen, or a parity, would mean chemistry and climate at their surface would be very different. The equivalent of geologic features on Earth may be present, but with different compositions. For example, instead of being composed of liquid water, the rivers might consist of oils. If the temperature is low enough, gases in the atmosphere may synthesize into hydrocarbons that could rain onto the surface. And the surface would be expected to look dark and reddish from hydrocarbon deposits. Yet another type of planet, not because of its composition, but the object it orbits, could be so-called planets with a P like black, planets that orbit a black hole. This is more than purely theoretical, it is likely to exist, even though none has been detected yet. Planets would be fundamentally similar to planets and could be of different kinds, and they could be located around supermassive black holes. It is a bit more difficult to imagine them around a black hole born from the collapse of a big star, because even though this supergiant star probably had planets, it went through a supernova that destroyed the system or expelled its planets. It is not completely impossible, though, because planets could be captured later, once the black hole exists. We know that there are rogue planets that escaped the system where they formed, and some of these rogue planets may even travel between galaxies. But a supermassive black hole at the center of a galaxy is a better candidate because it could capture many of these planets, and even more because there is an accretion disk around such black holes, a region with enough material in orbit to form new bodies, possibly thousands. There is a safe zone around such black holes, where satellites can exist, a zone where they are close enough to be captured by the black hole's gravitation, but far enough for an equilibrium to form between their speed and the black hole's pull, so they can adopt and stay on an orbit. These are different types of terrestrial planets that could be markedly different from the ones we know. But gas giants could also be different. The ones we have in the solar system are quite distant from the Sun, but we know that there are giant gas planets that orbit closer to their star. This is what is called a hot Jupiter. Hot because of the proximity to the star. And when this happens, they could become something called Chthonian planets. Gas giants that would have been stripped of their gas layers by the star, leaving only their solid core that would look a lot like a terrestrial planet. Or there could be helium planets. On Jupiter and Saturn, hydrogen is the main component, and helium is the secondary one. A helium planet would be one where helium dominates, and they might form in a variety of ways. The first possibility would be if hydrogen evaporates. If the planet orbits close to the star could drive off lighter gases more effectively, and hydrogen is lighter than helium. So, over time, hydrogen could be depleted and leave helium as the primary component of the planet. Another type of planetary object with a layer of helium, rather than a planet, could appear from a small white dwarf. You remember what white dwarfs are? We spoke about them at the beginning. They are the remnants of sun-sized stars, after they turn to red giants when they exhaust their hydrogen reserves. Now, in a binary system, a system with two stars, where both have passed their main sequence and died, turning into white dwarfs, one may have lost so much of its mass that it approaches planetary mass, and it orbits around the larger white dwarf. The planetary nebula left by the stars would be rich in helium, and this smaller white dwarf may be surrounded by layers of gas dominated by helium, making it look like a gas planet, even though technically it used to be a star before, which is why it would be called planetary object rather than planet. We are approaching the end of our cruise, and it is now time to return to Earth after this little exploration journey. As you see, space is still full of wonders, unsolved mysteries, and phenomena that wait to be discovered or understood. It took tens of thousands of years to mankind to understand the nature of the solar system, with a star and bodies orbiting around it. Then it took centuries to detect and name all the main planets in the solar system, and understand that the stars in the sky were countless other suns, parts of a galaxy. But it took only years to detect and name thousands of planets that do not belong to our system, exoplanets. Hello everyone. We're going to space again tonight for another cruise among the stars. And this time I'm taking you to exoplanets, the billions and billions of planets that exist in our galaxy alone and that astronomers started to discover rather recently. The identification of exoplanets is still a young discipline. So we're going to dream about these faraway worlds, and we will spend a cruise traveling to some of them: Proxima Centauri b, OTS 44, Kepler 438b. And to entertain you along the way, I will tell you about the different types of planets and how we think they form, the different types of stars, because stars are not all like the Sun, how planets that are so far away can be discovered, and another big question raised by evidence that so many planets exist in the universe. Could there be life on them? And what kind of life? This field of investigation that studies the possibility of extraterrestrial life is called astrobiology, and we'll talk about it too. It took only a few years since the 1990s to discover and name hundreds of exoplanets, planets that do not belong to our system. Knowledge in astronomy has advanced so much faster than our ability to travel in space, and these new planets are so far away from us that the hope of seeing human beings reach them one day is tenuous. But tonight, by the power of imagination, we're going to travel much faster than light and cross light years in seconds to reach our destinations. Of course, everything we will visualize tonight is hypothetical. It is based on observation, deduction, and the state of our scientific knowledge. It is likely that the way we understand other systems and exoplanets will keep evolving. But still, there has been so many discoveries, so much progress in this field in the past 30 years, that it has become a major aspect of modern astronomy. Our first stop in this journey will be at the nearest exoplanet that we know of, Proxima Centauri b, 4.2 light-years away from Earth. But how is it possible to detect planets that are so far away? The last big planet in the solar system, Neptune, was discovered in the 19th century. Then there was Pluto in 1930, which has been classified as a dwarf planet. But these are only a few hours light away from us. Proxima Centauri b is hundreds of times farther, and no conventional telescope can actually take a picture of it. So as we begin to accelerate, we are already leaving the solar system, and we will arrive at Proxima Centauri in a few minutes. Let's take a look at how exoplanets can be discovered. Any planet orbiting around a star is a very faint light source compared to its parent star. For example, in the solar system, the Sun is 1 billion times as bright as any of the planets that orbit around it. When you watch from several light years away, the light from planets is barely existent and gets completely washed out by the star they're attached to. So very few exoplanets have actually been observed directly, and astronomers resort to indirect methods to discover them. The first one is called transit photometry. What does it mean? Seen from Earth, other stars in our segment of the galaxy have a relatively stable brightness. It can increase or decrease with their distance to us because of all the planetary systems moving, orbiting the center of the galaxy at different speeds. But this is predictable. However, if there are planets orbiting these stars, these planets may regularly cross between the star and us, and this transit will hide a little bit of the star's light. Not much of it, and it depends on the size of the planet and its distance to the star. But with instruments that are precise enough, that little variation in brightness can be detected during the planet's transit in front of its star. Sometimes the star dims significantly. There are examples with big exoplanets that make the visual brightness drop almost 2%. Most of the time it is much less than that. For example, a planet the size of Earth transiting in front of a star the size of the Sun produces a dimming of only 0.01%. This is tiny, but still perceptible with the right instruments. This method is complicated because there are many variables. The star may have several planets. It requires to make assumptions about the characteristics of the planet's orbit. The dimming of light during transit is so small that errors, false positives, or transits that are not observed are probably frequent. And it also requires the planet's orbit to be aligned in the right plane from the astronomer's vantage point. From where we are, there are planets that will never transit just in the line of sight of their star. So it works, but only a minority of planets can be detected this way. And the larger their orbit, the less likely they are to be found. A second method that sounds very complicated, but the concept is not, is the use of radial velocity and Doppler spectroscopy. So what is this about? You know that planets are attached to stars by gravitation. This force keeps them on an orbit around the star, because the star is way more massive than them. But gravitation works both ways. The star has a major influence on the planet's orbits, but given that the planets also are massive objects, they have an influence much smaller on the star too. The bigger the planet and the closer it is, the more influence it has on its star. This means that the center of mass in a star system is not the exact center of the star. This center of mass is generally inside the star, but it's not the exact center of it because of the influence of planets. We generally say that planets orbit around the star, and this makes sense because the star in a system represents the bulk of matter, typically around 99% of it. But technically, planets and the star itself orbit around the center of mass, which happens to be inside the star if it's big enough, but a little bit uncentered. This means that the star also has a little orbit. It moves around a gravitational center. For example, in the solar system, Jupiter makes the Sun move by 13 meters per second. Earth also has a little influence on the Sun. It is much smaller than Jupiter due to Earth's smaller mass, but it influences the Sun by about 9 centimeters. That's a bit more than 3 inches per second. This is the concept of radial velocity. And these little interferences of the planets on their star can be detected. How? thanks to a phenomenon called the Doppler effect. Light has the properties of a wave, and when you receive a wave emitted by a moving object, waves arrive a little bit distorted. Let's take an example of the Doppler effect with sound waves that we experience every day, actually. Maybe you have noticed that when an ambulance with a siren passes near you in the street, the sound of the siren changes quite a lot. When the ambulance is advancing towards you, the sound is higher pitched. Then it passes just near you, and the sound becomes lower pitched as it moves away. The same happens when you are near a railroad. The sound of the train changes a lot, depending on whether the train comes towards you or moves away. This is not due to a variation in the sound from the siren or the train, and someone on board the ambulance would not perceive a different kind of sound. It is because the sound waves are emitted by an object that is in motion relative to you. Try to imagine the waves as an undulating line. The waves from the siren are coming towards you, but so is the vehicle, and this tends to compress the line. It fluctuates faster. In other words, the frequency increases, and this makes the sound seem higher pitched. Now when the vehicle moves away, the waves are now distended, the frequency decreases, and they sound deeper. This modulation of waves due to motion is the Doppler effect. Now sound waves are useless in space, because sound propagates through matter, through air in this example, but in the void of space, sound waves couldn't travel. But we have light instead. That's the basis of Doppler spectroscopy, detecting and measuring how the motion of a star is affected by the planets thanks to the variations in light waves. In practice, this is very complex. It requires extremely precise instruments and calculations, but velocity variations down to 3 meters per second from stars that are several light years away, or even dozens or hundreds of light years away, can be detected with modern spectrometers. A spectrometer is an instrument that measures and separates the spectrum of light, and in astronomy, spectrometers can even analyze the chemical composition of faraway stars and planets, thanks to the signature of the elements they are made of. We'll come back to that later. There are such high-precision systems searching for exoplanets thanks to Doppler spectroscopy in Hawaii and in Chile. They are responsible for the discovery of dozens of planets. Apart from the two methods we have discussed, transit photometry and Doppler spectroscopy, there are more methods to discover exoplanets. A visual one, but at this stage it works only for very large planets, like the size of Jupiter, with short orbits, is to detect how the light reflected by planets varies. Planets go through phases, like the Moon. They reflect more or less light through a cycle, depending on their orbit and how they are positioned. Telescopes cannot distinguish them from their stars, but they can measure how the same cycle of variations in brightness repeats itself, and deduce the existence of planets this way. Yet another method is called pulsar timing. It is limited to planets that orbit a pulsar, a type of dead star. We'll talk about the types of star a little later during the cruise. Pulsars are very dense bodies that rotate and emit radio waves with extreme regularity. So it makes it possible to track their motion, possibly because of planets, with extreme precision. Pulsar timing can reveal planets with less than a tenth the mass of Earth, and it can even detect mutual gravitational perturbations between the various members of a planetary system, revealing several planets and how they interact at the same time. There are not many planetary systems with a pulsar at their center. They have to be very old systems with an exhausted star that has already collapsed on itself. As you see, these indirect methods are a bit complicated, and they have a margin of error, but they work, and they have allowed the discovery of thousands of planets. As of February 2020, there are more than 4,000 exoplanets that have been confirmed in more than 3,000 different systems. But we are now approaching our first stop, Proxima Centauri b. We are now 4.2 light-years away from Earth, 25,000 billions of miles away. Alpha Centauri is a star system, like the Solar System, and the closest to us in the galaxy. But it looks quite different. There is not a single star, but 3. 2 are bigger and look like smaller versions of the Sun, and one that is smaller, called a red dwarf. In 2016, the discovery of Proxima Centauri b, a rocky planet orbiting the red dwarf star, was unveiled, and interestingly, this planet is in the so-called habitable zone of the star, not too close, not too far, like Earth is in the habitable zone of the Solar System. Another thing in common between this exoplanet and Earth is the size. Proxima Centauri b may be a bit bigger, at 1.3 times the Earth's mass, but the kind of gravity at its surface is probably acceptable for most terrestrial life forms, including humans. But it doesn't mean this planet is another Earth that is likely to be habitable. We don't know exactly what it is made of. It could be rocky like Earth, or it could have an icy composition like Neptune with a thick layer of hydrogen on its surface. The star Proxima Centauri is the closest from the Sun, but it is not visible to the naked eye from Earth, contrary to stars that are much further away, because red dwarfs do not emit as much light as Sun-like stars. And one thing that doesn't make the possibility of life as we know it easier on Proxima Centauri b is that the star is a flare star. Occasionally, it undergoes dramatic increases in brightness and emissions of all sorts. When these stellar storms happen, it is estimated that the surface of the planet is intensely irradiated to levels of UV rays that would easily kill the most resistant microorganisms on Earth. Proxima Centauri b is hit by intense stellar wind, too, that could probably carry away any atmosphere, unless the planet has a powerful magnetic field like Earth that would shield it from stellar wind. What is stellar wind? You know that stars emit light and heat and other radiations, but they also release matter that is ejected from them. It can be gases or particles, free electrons, nuclei of atoms. The Sun does it too, but we are protected from the stream of particles it ejects by the Earth's magnetic field that deviates solar wind. In the case of Proxima Centauri b, it is unsure whether or not there is a magnetic field, and stellar wind is up to 2,000 times more powerful than on Earth, meaning that an atmosphere made of gas is not very likely. And in this case, life forms would have to exist underground only. If not, they would have to be life forms we have a hard time imagining. And yet it is not completely impossible, because the planet is in the habitable zone. What is this concept of habitable zone? It's quite simple. Biologists have observed that life forms that we know of on our planet need liquid water to appear and survive. It doesn't mean life is impossible without it, but Earth-like life, based on the chemistry of carbon, oxygen, hydrogen, probably needs liquid water. Now, the liquid state for water requires quite specific conditions of temperature and pressure. Out of these, water is either solid or gas, and Earth-like life, especially surface life, would be impossible. When a planet is too close from a star, the heat is too much, and stellar wind is likely to prevent a thick enough atmosphere from existing. With high temperatures and a very thin atmosphere, which means low pressure, liquid water cannot exist at the surface. But if a planet is too far from the star, it doesn't receive enough energy from it, and water turns to eternal ice. Of course, even outside the habitable zone around the star, life could theoretically appear in underground oceans, for example, but surface life, probably not. Now, it's not because a planet is in the habitable zone that it is likely to harbor life. There are many more conditions of composition, temperature, pressure, and maybe a series of coincidences that make life possible. In the solar system, Venus and Mars also are in the habitable zone, but no sign of life has been detected there. So Proxima Centauri b is in the habitable zone. Its size is relatively similar to Earth, a bit bigger, but its habitability remains very uncertain because of stellar radiation, the brutal variations in the energy its star sends, and we don't know whether or not the planet is shielded from this. But there is a slim chance that liquid water exists if the planet constantly presents the same face to its star, like the Moon does to the Earth. When a body orbits around another one, and at the same time revolves slowly on its axis, so that it always presents the same side, it is said that it is tidally locked. The Moon is tidally locked to Earth. If this is the case for Proxima Centauri b to its star, there must be a hotter side which receives the radiations, and a colder, dark side opposite to the star. But in between, there could be a thin border region where the transition between extremes happens, or if Alpha Centauri has a magnetic field and is rocky, an atmosphere made possible by the magnetic field, maybe a regulation of its temperature by an atmosphere, then the sunny phase could have liquid water. There are many conditions necessary, and a high probability that the planet is just a dead rock, or maybe not even a rock, but we cannot exclude the possibility of life only 4.2 light years away from Earth. But let's now escape Alpha Centauri b and resume our journey. We are now going to accelerate even more than last time, because our next destination is OTS 44, 550 light years away, a planet that is so big that it could border on a star. It has more than 10 times the mass of Jupiter, and it is located in the constellation Chameleon. As we resume our journey, and because this planet is going to be very different, let's take a look at the various types of planets and stars that we know of in the universe, or that could theoretically exist. What is a planet, actually? The most commonly accepted definition is that a planet is an astronomical body orbiting a star that is massive enough to be surrounded by its own gravity, and which has cleared its neighboring region of other bodies by absorbing them or turning them into satellites. But it's not massive enough for thermonuclear fusion to happen. So according to this definition, planets are defined mainly by their size. There is a lower and an upper limit to what constitutes a planet. This definition disqualifies a few bodies that are big enough to be surrounded by their gravity, like Pluto, for example, but not big enough to have absorbed planetesimal protoplanets around them. But this definition of what a planet is remains a bit controversial, because it excludes objects of planetary mass based on what or where they orbit. There are satellites in the solar system that are bigger than planets, but they are not considered planets because they orbit another planet before orbiting the Sun. If the criteria of cleaning space was lifted, then Pluto could be classified as a planet again, but so would be various bodies from the asteroid belt, like Ceres or Pallas. These are just conventions anyway, but whatever its definition, the term planet also hides a variety of bodies that can be completely different in their sizes and composition. You have probably heard of various terms like rocky planet, gas giant, super Earth, hot Jupiter. These terms are a bit confusing because they refer to various ways of classifying planets, various approaches. A first classification can be made based on their composition, what planets are made of. In the solar system, there are rocky planets. They have a hard surface, and they are mainly made of metal and rock. They also have an atmosphere made of gas, but the separation between the atmosphere and the surface is very clear. There are also planets called gas giants, like Jupiter or Saturn. They are bigger and they don't have a well-defined surface because they are a giant ball of gas, mainly hydrogen and helium, and they can also be very dense. Actually, their cores are denser than rocky planets in the solar system because of their size that compresses the core. But rocks are marginal in these planets, and they lack a hard, solid surface. Their density just increases progressively as you travel from the periphery to the core. There are other giant planets like Uranus and Neptune called ice giants. The structure looks the same as gas giants, but their composition is different. Instead of hydrogen and helium, they're made of heavier substances, methane, ammonia, water. I told you about it in previous stories already, but in astronomy, ice is not always water ice. It can also be other compounds, water, carbon dioxide, hydrocarbons. Ices in an ice giant do not form a solid icy ball like an ice planet. They float, so there is no solid surface neither. But nothing says all kinds of planets are represented in the solar system. There are other types of planets or theoretical types of planets that have not been discovered yet but could exist. For example, gas dwarf planets or mini Neptunes. These are planets with a rocky core and also a thick envelope of gas or volatile ices, like a crossover between Earth and Jupiter. Planets are called gas dwarfs when their size, their total size, their radius, is up to 3.9 times that of Earth. Above this limit, they become giants. It is theoretical, but another kind of large gas planet could be made mainly of helium instead of hydrogen plus helium if a small star loses enough mass to be downgraded to a planet. These ones would be expected to resemble gas giants, but they would differ from them by their composition and their formation history. Another theoretical type of planets could be ice planets. There are bodies in the solar system with a solid icy surface, like the moons Enceladus orbiting Saturn, or Europa orbiting Jupiter, or Triton near Neptune. An ice planet would be a bigger version of these, big enough and independent enough to fall into the definition of a planet. None was found neither, but there could be iron planets too. Rocky planets generally have a metallic core. When they form, heavier elements like iron tend to migrate towards the core, and lighter elements like silicate rocks stay closer to the surface. But a planet that would form from mainly iron, or that would lose its rocky mantle due to giant impacts, could become an iron planet. The closest planet to this model in the solar system is Mercury, the first planet from the Sun. In proportion, it contains a lot of iron. All these existing or theoretical planets are not random inventions. Their proven or possible existence is a result of the planet formation process when a new planetary system appears. You know that according to the current state of theories about planetary system formation, or single star systems at least, it all begins with a large disk of matter, gas, dust, that progressively accretes due to gravitation. And most of the matter ends up creating the star, something to the magnitude of 99% of matter available. Planets form with what is left of it, on different orbits around the star. The remaining matter forms rocks that collide for millions of years. They absorb each other and they give birth to protoplanets that clean up their orbit or satellize smaller bodies. If we take the example of iron planets, they are expected to form near a star, because presumably this is where the protoplanetary disk consists of a lot of iron-rich material. Why iron and not another metal? It is because iron is a rather abundant element in the universe, the sixth most abundant. By mass, the one element you are most likely to find in the universe, and by far, is hydrogen, the simplest kind of atom. It is followed by helium. When hydrogen nuclei merge in stars during thermonuclear fusion, it produces helium. So it is another abundant element that stars keep producing all the time. In third place, there is oxygen, followed by carbon and neon. We rarely hear about neon because it is quite rare on Earth. There are traces of it in the atmosphere, where it is a gas, and there is even less in the Earth's crust. There is little neon on rocky planets because it is highly volatile and it forms no compounds that could fix it to solids like oxygen does. So it tends to escape from planets in the early stages of their formation. It doesn't stay trapped in the condensing clouds of gas and dust that form solid planets like Earth. But it is a more significant component of larger gas planets and stars. And in sixth position comes iron, far above any other metal. So this is a typology of planets by composition. But there are other ways of categorizing planets, for example by mass. The term super-Earth has been coined to name a type of exoplanet that is more massive than Earth, but still less than the giants of the solar system. Theoretically, a rocky super-Earth could be habitable, but gravity could be much higher than we are used to. Another concept based on mass is super-Jupiter, a planet that is more massive than Jupiter. Various of them have been discovered, including OTS 44, we are on our way to visit. And yet another way to categorize planets is by their orbit. This is where the concept of hot Jupiter or hot Neptune appears. These would be gas giants or ice giants, orbiting much closer to their star than they do in the solar system. And they're called hot because the proximity of their sun would mean high temperatures in their more superficial layers. As I told you before, the main difference between planet and star is based on mass. Stars are big enough to ignite thermonuclear fusion and become big energy producers under the form of heat, light, and other radiations. It also means there are bodies that are just under or above this limit, very big planets or very small stars. OTS 44 that we are now reaching is one such body. It was discovered 20 years ago in 1998, and it is not a planet attached to a star, but rather a free-floating object that has 11 times the mass of Jupiter, but only 1.1% of the mass of the Sun. We don't exactly know what it looks like, but it is believed it has a disk of particles of rock and dust, about 10 times the mass of Earth. This disk could be in the process of accretion that would create a mini planetary system with a very small star at the center and one or several planets orbiting around it. It seems OTS 44 is just at the limit of planet and star. And this kind of object is called a brown dwarf. A brown dwarf is not massive enough to fuse ordinary hydrogen in its core, but it can fuse deuterium. Deuterium is an isotope of hydrogen. What is it about? Elements are defined by the structure of atoms. Common hydrogen, for example, has two particles, one proton in its nucleus and one electron. Any atom with these two particles is hydrogen. But the nuclei of atoms may also contain neutrons, another type of particle, and the number of neutrons can vary. These different versions of the same atom are called isotopes. When an hydrogen atom also has one neutron in its nucleus, it is still hydrogen, but its properties are slightly different, beginning with the mass that is a bit higher, and this particular isotope is called deuterium. Maybe you've heard of something called heavy water. This has to do with deuterium. A molecule of water is made of two atoms of hydrogen and one of oxygen. Most of the time, hydrogen has no neutron. Regular water on Earth is made of that type of hydrogen. But if the hydrogen atoms that combine with oxygen are the deuterium isotope, with an additional neutron each, the water it creates has different properties. It is a bit more massive, hence the name heavy water. It freezes at a higher temperature, close to 4 degrees Celsius instead of 0. And one of the applications of heavy water is in the nuclear industry. In many nuclear reactors, water is used as the moderator, that is to say, the substance that slows down neutrons to facilitate their capture by fissile material, so that nuclear fuel will become unstable and fission. An advantage of heavy water over regular or light water is that heavy water has a lower propensity to capture neutrons. It's logical because deuterium already has a neutron, so it facilitates reactivity inside the reactor. The nuclear fuel may be less enriched in fissile material. So returning to brown dwarfs, these are bodies that are massive enough to fuse deuterium, because this requires less extreme conditions than ordinary hydrogen. Deuterium fusion gives helium-3. A deuterium nucleus combines with a second proton, so it is no longer hydrogen, it is now helium, but an isotope of helium with the neutron from deuterium. That's why it's called helium-3, because of the particle in its nucleus, 2 protons and 1 neutron. Brown dwarfs emit a bit of light, nothing compared with larger stars, and this is why they are called brown. they are hard to detect by visual observation because of their low brightness. But in fact, to the human eye, they would probably appear magenta or orange-red rather than brown. Even more than with planets, there is a diversity of stars based on their mass or the stage they're at in their life cycle, which determines their kind of luminosity, their size, and their radiations. Currently, stars are generally classified under a system called Morgan-Keenan, with a letter and a digit, indicating their temperature and their luminosity. As stars appear, burn for millions or billions of years through the main stages of their lives, and then die, their classification evolves. So let's take a look at some types of stars or stages in their existence, as we already started with brown dwarfs that are at the lower limit of what a star is. You remember when we visited Alpha Centauri, we talked about the red dwarf around which Alpha Centauri b orbits. Red dwarfs are bigger than brown dwarfs, and they are true stars because they do fuse ordinary hydrogen. But their limited mass makes the fusion reaction relatively slow. So they are small-sized stars. Their surface is colder than others, and it is also believed that they can live much longer than bigger stars. Above this category, in mass, are stars like the Sun, which are sometimes called yellow dwarfs, but their precise classification is G-type main sequence stars. Their typology is based on their luminosity and radiation, but we can just retain the idea that they are rather similar to the Sun. These stars typically exist for around 10 billion years, way less than red dwarfs, because they burn their reserves faster. At the end of their life, when their hydrogen reserves in the core become exhausted, they grow dramatically in size and become so-called red giants. It happens because after billions of years of existence, their core has become rich in helium, the main product of hydrogen fusion. So they begin to consume hydrogen from their more superficial layers, which expands them dramatically. And at the same time, the helium core tends to contract, which liberates gravitational energy. As a result of these two factors, the star may expand up to 1,000 times its previous size. And when this happens to the Sun in several billion years, it should expand enough to absorb Mercury, then Venus, then Earth, and even Mars. At the same time, the surface temperature decreases, and this is why they are called red giants. Their luminosity tends to decrease. After this phase, it is believed that a red giant collapses on itself, abandoning a lot of its matter that keeps floating in space. These clouds of gas and dust are nebulas that may later participate in the formation of a new system. In the last stages of its life, now that hydrogen to fuse has become scarce in its core, a star of that kind begins to fuse heavier elements, beginning with helium. This is how new elements can be created, from the most common ones like carbon or iron, to the biggest, most massive atoms. but the remains of the star keep agonizing for a very long time, several billion years more, as a smaller body the size of a planet called a white dwarf. Bigger stars than the Sun also exist. They tend to have a shorter lifespan because they burn their fuel faster. When they approach the end of their life and begin burning helium, these massive stars become very bright and are called blue giants. Blue giants are fairly rare because they don't exist for a long time. Still, it can be millions of years, but this is not that much on an astronomical scale. Later, they go through the same expansion process as Sun-like stars and become red supergiants. You have probably heard of supernovas. A supernova is a phenomenon that may happen when a large star reaches the end of its life, either because it has turned into a white dwarf that explodes, or because a star that still has nuclear reaction implodes, collapses suddenly on itself, and when this happens, the collapse of its core dislocates its external layers. At the scale of a galaxy, supernovas are relatively rare, but there are so many galaxies in the universe that it is estimated a supernova takes place somewhere every 2 to 3 seconds in the universe. But in the Milky Way alone, there would be 1 to 3 supernovas by century only. A supernova is such a powerful phenomenon. It releases so much energy in a few milliseconds that the dying star can suddenly have become more bright than an entire galaxy. And they are important events in the universe too, because they disseminate the elements synthesized by the star during its life, and they create shock waves in space. It is believed that these shock waves are responsible for the formation of new systems. They will transmit motion to a nebula and facilitate the concentration of clouds of floating matter. This matter can then start to spin and accrete due to gravitation and form a new planetary disk with a star at the center. White dwarfs, these dead bodies of stars, are very dense, and if the star was big enough, they may shrink even more and turn into neutron stars. Neutron stars are dark, small, but extremely dense balls of matter, in which the forces at play are so strong that atoms shrink. Electrons and protons combine to form neutrons, and the neutron star is made of atom nuclei. The next stage, if the star was even bigger, may be the transformation into a black hole. Earlier I mentioned pulsars that emit a very stable signal. It is believed that pulsars are heavy white dwarfs or neutron stars, so the remnants of a large dead star that rotates fast on itself. So let's return to exoplanets now that we have seen OTS 44, because we have one last stop to make before returning to Earth. We're going to visit one of the most Earth-like exoplanets identified, Kepler 438b. It was discovered using the transit method and confirmed in 2015. You remember, the transit method is the measurement of how the crossing of a planet in front of its star dims the light. Its star is called Kepler 438, and it is a red dwarf located 640 light-years away from Earth. Kepler 438b checks a lot of boxes in the comparison with Earth. It is in the habitable zone of its system, this region at the periphery of the star that is not too hot nor too cold. It is likely to be rocky. It has the same size as Earth almost. Its radius is only 12% bigger, and its equilibrium temperature, that is to say, the theoretical temperature it could have given the stellar radiation it receives, would be around 3 degrees Celsius, 37 Fahrenheit. The main concern, like we saw earlier with Alpha Centauri b, is that it may receive large amounts of radiations from its parent star that produces regular bursts of radiations. We saw earlier that liquid water was seen as a likely necessary condition for the appearance of Earth-like life. But the search for an environment that could harbor life is just one aspect of a larger field of study called astrobiology, the study of life in the universe, how it may appear, travel through space eventually, what forms, what organisms can be called life, what life forms from other worlds may look like. This is a vast field of study, but one that is a bit paradoxical too, because it studies something we have no trace of at this point. Given that there is no organism to actually investigate, to study, astrobiology focuses on the origins and evolution of life, the kinds of biospheres that could support it, whether extraterrestrial life exists, and how it could be detected. So it touches on many different fields: biology, biochemistry, astronomy, geology, physics, and it concerns itself mainly with hypotheses that would be coherent with existing scientific theories. I told you earlier that the search for life focused on carbon-based chemistry. This may sound a bit random or restrictive, as if we lacked imagination. But maybe not so much when we start defining what a living organism may be. It needs to interact with its environment, to find energy somewhere, to build itself. And carbon is a very particular element compared with others, because its capacity to be part of many different molecules is unmatched by any other element. It is rather abundant too, the fourth most abundant element in the universe after hydrogen, helium, and oxygen. And the energy required for it to make bonds with other elements to form molecules is just at the right level. The molecules formed are stable, but at the same time they can react when put into contact with other elements. And that's an unique property, and probably the reason why all forms of life we know of on Earth use carbon. To understand how carbon chemistry is crucial, think about the cycle of eating, digesting, and breathing that keeps human beings alive. A large part of what we eat is carbon. It is a key component of not only carbohydrates, but also lipids, proteins, fibers, vitamins. when we digest these nutrients, we take bricks from them to maintain or build our organisms, and we also get energy from the breaking of carbon-based molecules. And a part of the carbon is ejected through breathing. We take in oxygen, and we take out oxygen and carbon dioxide. All of these transfers of matter and energy are only possible because of the particular properties of carbon. And the thing is, no other element seems to be able to replace it. As far as we know, matter in the universe is not different on Earth 1 light year away or 1,000 light years away from our home. The constraints are the same. And assuming life requires complex chains of molecules that can be broken and rearranged to transfer matter and energy, we see no other element than carbon that could be at the center of it. This is why the search for extraterrestrial life focuses so much on the chemistry of carbon and the conditions needed for it to become the basic brick of life forms. It is not a random option, and it actually looks like a well-informed guess to narrow the search for extraterrestrial life. Carbon and liquid water, which is another ingredient required for carbon-based chemistry to fulfill its potential. Another way to narrow the search when it comes to exoplanets is the type of stars. Sun-like stars are preferred because the larger stars tend to have a shorter lifespan that gives life less time to appear before they die. And smaller stars, like the small red dwarfs, may not send out enough energy. But on the other hand, red dwarfs may not be such a bad environment because they exist for hundreds of billions of years, which gives a lot of time to life. And a thick atmosphere that would heat a planet through greenhouse effect could allow the temperature to be sufficient, even with not such a powerful star. There is a hypothesis called panspermia, according to which life could exist throughout the universe, and that it could travel and be distributed by asteroids or space dusts. It is possible that the chemistry leading to life, with complex molecules, may have appeared quite quickly in the history of the universe, maybe after a few million years only. And we think the universe is 13.8 billion years old. The basic blocks of life may have formed spontaneously in nebulas or in the first planetary systems. They were made of elements that are relatively abundant. So these building blocks of life may have been distributed to planets as they formed, waiting just for a favorable environment to combine further. It is impossible to make rules, because Earth is the only example we have. But it is true that life on Earth appeared relatively quick in its earliest forms when Earth cooled down and had liquid water. Earth has supported life for billions of years already. Another aspect of panspermia is the possibility that microorganisms can survive the effects of space, the void, the intense cold or heat, the radiations. There are extremophile organisms on Earth, that is to say, organisms able to survive in conditions that would kill most others, like hundreds of degrees or staying frozen for years. Maybe these organisms could be ejected with other debris when a planet collides with an asteroid and stay dormant for years, or even centuries, until they randomly land on another planet where they would become active again and colonize a new environment. These are just hypotheses that sort of fit with scientific theories. They are not absurd, but there is no hard evidence that this ever took place. So is there life on Kepler 438b? We don't know, and it is so far away at 640 light years that it's hard to imagine human beings ever going there to check. It sounds absurdly far. But the idea of flying to Mars would have sounded equally absurd 3 centuries ago, and we are now maybe just a few years from it. So maybe our children will find a way that we cannot even start to think of at the moment to travel faster than light and reach these faraway worlds. We are returning to space tonight, but this journey is going to be our biggest ever. We are not just going to visit a particular planet or a part of the solar system. No. By the power of imagination, we're going to accelerate to several thousand times the speed of light. We will escape the solar system in a matter of seconds and travel to other galaxies. Along the way, I will tell you about our galaxy, the Milky Way. We will discuss other galaxies too, like our destination, Andromeda, and I will explain the mind-blowing distances within and between galaxies, their population of billions and billions of star systems, how the existence of galaxies was discovered, and how they are observed. We will also discuss mysteries, like the possibility of life on these hundreds of billions of planets they contain, or the possible existence of an invisible dark matter in the universe, and also how fast it is possible to travel in space. The Andromeda Galaxy, our destination, is extraordinarily far, and yet you probably already saw it. On a moonless night and from areas with limited light pollution, it is so big that it can be visible to the naked eye from our planet, and it appears in the same area of the sky as the constellation of Andromeda, hence the name given to the galaxy, even though it is way, way beyond the stars that form the constellation of Andromeda. Before we reach this galaxy, we're going to accelerate beyond imagination, even beyond what the laws of physics, as we know them, probably allow. We will come back to that later. But first, let's take a look at where our planet is in our galaxy. We are used to think about the position of Earth relative to other bodies in the solar system. The Sun at the center of it, and then the other planets and bodies that orbit the Sun. But the Sun is just one star among hundreds of billions that also orbit around another center, the center of the Milky Way, the understanding that we are part of a much larger disk of stars is recent, only a century ago. The Milky Way is shaped like a gigantic, flat disk. When bodies orbit around the center, they tend to align on the same plane. This is an effect of gravitational forces that keep them together. They tend to align on a plane, but star systems or galaxies are not perfectly flat. The Milky Way's disk is 1,000 light years thick and is estimated to be 100,000 light years wide in diameter. So it is about 100 times wider than it is thick, like the proportions of a CD-ROM. Sometimes in pictures, galaxies are represented with an oval shape, but this is because they are represented seen from the side with an inclination. If an observer looked at the Milky Way at the vertical of its center, the galaxy would look circular. All galaxies are not alike. On our way to Andromeda, we will soon reach a dwarf galaxy that may be in the process of being torn apart by the Milky Way. Some galaxies have only tens of millions of stars. Others have hundreds of billions. And their shapes vary too. Among large galaxies, there are mainly three shapes that have been observed. The most frequent ones, like our own, are spiral galaxies. Their stars are organized on a disk, but they concentrate on arms originating from the center. And most spiral galaxies have a central concentration of stars known as the bulge. This is why the center appears more luminous. At the periphery, these spiral galaxies have a much fainter halo of stars. The arms appear more luminous because they contain a higher concentration of stars, often younger stars that shine brighter. It is believed that these stars are born from nebulas, which are giant clouds of gas and dust. Sometimes parts of nebulas collapse on themselves after a shock wave hits them, and the gravitational forces lead to the accretion of this matter into a new star and eventually planets around it. The Milky Way contains various nebulas. They are the matrix of star systems. And when a star dies, after billions of years, because its fuel is exhausted, it may disintegrate and give back the matter it was made of to a nebula. The majority of spiral galaxies also have a bar-like structure that extends from the bulge. The Milky Way has one. Its spiral arms begin at the ends of the bar. Not all galaxies are spiral-shaped. Another type is elliptical galaxies. These ones have an ellipsoidal shape, which is like a sphere that has been slightly flattened. Seen from afar, they look like a smooth and nearly featureless halo of light, with more luminosity in the center, where more stars are concentrated. It was believed when these elliptical galaxies were discovered that they were younger and they could later evolve into spiral galaxies, but we now know that this is not the case. In fact, the stars they contain are, in average, much older than the stars found in spiral galaxies. And finally, there is a last type, irregular galaxies, which are the ones with no distinct regular shape. These ones are chaotic in appearance. They have no bulge in the center, so they are like clouds of stars. Some irregular galaxies probably once were spiral or elliptical, and they were deformed by an external shock or gravitational force. Generally, these irregular galaxies are much smaller, about 1/10 of spiral galaxies, and this small size makes them more prone to crash and eventually be absorbed by larger galaxies. This typology of galaxies was started by an American astronomer called Edwin Hubble, the same Hubble whose name was given to the Hubble telescope. He is one of the most important astronomers of all time because he extended our understanding of the cosmos way beyond the limits of his time. He was active in the first half of the 20th century. His main findings include the discovery that clouds of dust or gas that were visible from the Earth and were thought to be nebulas were in fact galaxies beyond the Milky Way, and that the Milky Way was just one galaxy among many others. So he could start to map visible objects in the sky of the Earth and differentiate what was part of our galaxy and what was at extragalactic distance. Together with the works of other astronomers, he also contributed to discover that galaxies that were more distant from Earth tended to recede quicker. This is important because this is a clue that the universe is expanding, and it became one of the elements that backed the Big Bang theory and made it go mainstream. Since its elaboration, the Big Bang theory has been backed by various proofs of that kind that it accurately described the history of the universe. So, where are we inside our spiral-shaped galaxy? The answer is midway between the center and the side. The radius of the Milky Way is 50,000 light-years, and we are approximately 25,000 light-years away from the center and 25,000 light-years away from the edge. To exit the galaxy, we could either travel along the disk, and at light speed it would take 25,000 years, or for a shorter exit, we could travel following the perpendicular to the galaxy's plane, and that would be faster, but would still require several centuries at light speed. This gives an idea of the size of our galaxy. We are disproportionately small and slow to even imagine reaching the edges of the Milky Way, let alone travel to another galaxy. Andromeda is 2.5 million years away from us. This means that what we see when we look at the sky and see Andromeda are rays of light that the galaxy emitted 2.5 million years ago. If it was to disappear entirely, we would be informed of it 2.5 million of our years after the fact. The fastest spaceships ever built travel at a small portion of light speed, way less than 1% of it. But even if we could reach light speed or close, traveling to other systems in our own galaxy would remain a very long journey. The diameter of the Milky Way, you remember, is estimated at least 100,000 light years, and there are generally several light years between star systems. So reaching another galaxy would remain very implausible. But if we suppose technical limitations can be overcome, is it possible to move faster than light? Our understanding of physics implies that very probably not, at least not for human beings made of matter as we know it. According to the theory of relativity, when a body with a mass, a measurable quantity of matter, accelerates close to light speed, its mass precipitously increases and becomes infinite, and so does the energy required to move it. So this is impossible. The light, photons, that can travel at light speed have no mass, and this is how they can travel so fast without seeing their mass tending towards the infinite. The increase in mass when matter accelerates and comes close to light speed has been verified in particle accelerators. In a particle accelerator, particles like electrons are propelled to observe their properties when they accelerate or when they collide. In the 1960s, scientists observed that at some point when the electrons accelerated, they needed to provide them with more and more energy to make them keep accelerating. And even though electrons came close to light speed, they could never quite reach it, because they got heavier and heavier, and it is obviously impossible to provide them with the infinite quantity of energy that could move their infinite mass. Our bodies and everything we may build are made of the same matter that can be tested in particle accelerators, and they are subject to the same laws, the same limitations. So it looks impossible, or at least implausible, that a human being will ever travel at light speed. For now, this is really not a problem, even for the fastest man-made vehicles, because they are way slower than light speed. For example, one of the fastest flying objects ever built is a space probe called New Horizons. This probe reached the limits of the solar system a few years ago. It reached a speed of 16 kilometers per second, about 10 miles per second. 16 kilometers per second is already a speed that defies our imagination. For example, it puts Los Angeles at less than 5 minutes from New York City, and a complete journey around Earth would take only 40 minutes. But this is still very slow in comparison with light speed. Light doesn't need 40 minutes to travel around the Earth. It needs just a bit more than a tenth of a second. It travels almost 20,000 times faster than the New Horizon probe. But even assuming we could build vehicles that are thousands of times faster, and we could come close to light speed, interstellar travel would remain very difficult, very long, and intergalactic travel still out of reach. Now, if traveling in straight line is impossible, maybe another option would be to use shortcuts. We figure out that the universe is a three-dimensional space because this is the perception that our senses and our minds allow. But we know, since Einstein's theory of relativity, that this perception is just one aspect, one way of seeing the universe, and probably a very incomplete, partial one. A few scientists and many sci-fi authors have considered the possibility that shortcuts in the structure of our universe, shortcuts in space-time, could be found or even created to almost instantly travel to another point in the universe, in what would be some sort of teleportation. Theoretically, the theory of relativity allows the existence of structures called wormholes that would link disparate points in space-time, like tunnels with two ends that would connect different points in space, different universes, or different points in time. But this is completely hypothetical, and no wormhole has ever been identified. However, science fiction quickly embraced the concept decades ago because it was a way to explain or justify very long distance travels in a short time and give stories a varnish of scientific credibility, which is why the concept of wormhole has become quite famous. Even though the existence of wormholes is far from certain, maybe one day a wormhole could be identified. After all, black holes also were a very hypothetical, theoretical kind of object for a long time before they were finally observed. Wormholes would be pre-existing structures, but maybe this type of tunnel could also be created and controlled by actively distorting space-time, which would allow a spacecraft to create its own shortcut to another point in the universe. This is also highly speculative, and there is no chance to see that kind of craft anytime soon, because we have no idea how to do that, or how to power such a spacecraft. At this point we have no grip and no clue about how to actively modify space-time, if that's possible. But once again, science fiction is ahead, and that sort of modification of space-time to allow a ship to travel to other points in space or to another dimension is already familiar in fiction. Sometimes it includes a very cliché scene where someone folds a sheet of paper to show that any 2 points apparently distinct on a plane can be reunited and the distance between them reduced to 0. This method of teleportation amounts to creating a man-made wormhole. But let's return to our journey for now. We are still not at cruise speed, but we already travel in imagination at hundreds of times light speed. We have left the solar system behind, and we are now in an interstellar void on our way to the closest star system to Earth, Alpha Centauri. Alpha Centauri already gives us a glimpse of the diversity of stars and systems in our galaxy. At only 4 light years from Earth, it is not a single star system with planets orbiting around their star like the solar system. It has 3 stars. 2 of them are rather similar to the Sun, and they orbit together around a common center, forming a binary star. From the Earth and to the naked eye, they look like one single star that appears in the constellation of Centaurus, hence the name of the system. But they are not alone. There is a third, less visible star that is almost invisible from Earth, Alpha Centauri c, or Proxima Centauri. This star is called a red dwarf. Red dwarfs are smaller and cooler than Sun-like stars, which makes them harder to spot because they don't emit as much light. Red dwarfs are very abundant. It is estimated that they represent more than half the stars in the Milky Way, and they can also potentially exist for way longer than other types of stars, because when they burn their fuel, atoms of hydrogen merging together to create helium in the core of the star. The resulting helium is evacuated from the core by a convection movement. This means that the fusion reaction can last a long, long time. Red dwarfs are estimated to be able to burn for thousands of billions of years, as opposed to mere billions of years for more shiny stars. This lifespan represents much, much more than the age of the universe, estimated at about 14 billion years. So all red dwarfs are still very young, and none of them can exist at an advanced stage of evolution. Proxima Centauri orbits around the 2 other bigger stars. The system remains little known, but planets have been discovered in it, including one called Proxima Centauri b that orbits around the red dwarf. This planet is the closest exoplanet to Earth that has been discovered until now. Exoplanet just means planet outside the solar system. This one, Proxima Centauri b, is in the so-called habitable region around its star. Habitable region means that, in theory, given the distance to the star, the planet could have conditions of temperature or radiations that could possibly be compatible with the existence of organic life on it. Now that we have reached Proxima Centauri, we're going to accelerate even further and travel thousands of light years in mere minutes to reach the edge of the Milky Way. As we start to see it from the outside, we may notice that the entire galaxy is spinning around its center. We will see later, when we arrive at Andromeda, what lays in the center of a galaxy. It may all look very slow because of the distances, but all star systems orbit around the center at high velocities. For example, the Sun and the Earth travel at 230 kilometers per second relative to the center of the Milky Way. This is less than a thousandth of light speed, but much faster than the speed of Earth relative to the Sun. The Sun's orbit around the center of the Milky Way is so large that it takes more than 200 million years to complete a revolution. This period of 225 to 250 million years is called the galactic year or cosmic year, and it represents entire eras for our planet. Even dinosaurs, if we accept birds, did not exist for long enough to complete a galactic year. Humanity has been around for only a small fraction of a cosmic year. I told you earlier that Andromeda was the closest galaxy to the Milky Way. But this is actually disputed. It is the closest large spiral galaxy, but there are many other smaller galaxies in the proximity of the Milky Way. One of them is the Canis-Major dwarf galaxy, or Canis-Major overdensity, because its status as a galaxy is unclear. This would be an irregular galaxy located in the same part of the sky as the constellation Canis-Major seen from Earth. This dwarf galaxy would contain about 1 billion stars, which is not much compared with the Milky Way that has at least 400 billion stars. This galaxy, or overdensity, would be in the process of being torn apart and absorbed by the Milky Way. Maybe Canis-Major came too close to the Milky Way. In any case, it appears to be losing stars to the gravitational pull of our galaxy, and it forms a trail of stars around the Milky Way, but it is unclear whether it is or was a distinct galaxy or just a part of the Milky Way's halo of stars. In any case, an existing theory is that galaxies may grow in size over time by absorbing smaller neighbors. Now let's leave the Milky Way behind and accelerate again to reach Andromeda in a matter of minutes rather than millions of years. We are now in the intergalactic void, which is not very different in nature from the void between bodies inside a galaxy, except it is even more gigantic. It is as close as you can get to absolute vacuum. But there is not nothing at all. In average, estimates point to probably 1 atom of hydrogen per cubic meter. But in some regions of intergalactic space, there are more things. There are clouds of gas ripped away as galaxies interact or sometimes collide. It is difficult to study the intergalactic medium because visually it sends us close to nothing. Only light-emitting or light-reflecting objects, like stars, can be seen from Earth. Optical light is not very useful, but it is possible to study how light from galaxies that are further away travels through this medium and make hypotheses based on the information. For example, we know there are clouds of gas because some of the light gets absorbed as it travels through intergalactic space. But there is more than gas. The Hubble telescope has observed stars that are not part of a galaxy and exist between galaxies. They may have once belonged to a galaxy, but they were separated from it. These stars are called stellar outcasts or intergalactic stars, and they are not that rare, even though they represent a very small percentage of existing stars. Several hundreds of them, of these free stars, have been detected already in space between galaxies. Instead of orbiting around a galaxy center, these stars have been found orbiting around a cluster of galaxies. Because galaxies are not the biggest unit in the universe, they tend to be located in groups where they are closer to one another in clusters. Like the gas clouds I told you about before, these stars were probably ripped off the galaxy where they formed and belonged to by the interaction or the collision between galaxies. We don't know how many could be out there, but all the intergalactic stars detected were giants. There may be considerably more that are harder to identify, and these stars may have taken with them their satellites, their planets, that accompany them in their lonely travel in space. If we look ahead now, we can now see the spiral of Andromeda growing bigger every minute, with its arms spinning around the center. The observation of Andromeda and other galaxies is what has led to one of the most fascinating mysteries and hypotheses in astrophysics: the supposed existence of dark matter. What is this about? It all started in the 1930s. By then, the laws of gravitation that we think determine the movement of all bodies in the universe when they have a mass, and how these bodies interact were already well understood. But a number of abnormalities were detected, in particular galaxies that seemed to travel faster than they should have, or not exactly in the right direction. This ghost force that seemed to drive the galaxies in the cosmos remained mysterious, and there were not enough observations made with the limited technical means of the time, so that this apparent abnormality was left unexplained for decades. But one hypothesis was elaborated by an astronomer called Fritz Zwicky to explain the speed of galaxies. And to explain this, he attributed them more mass than was thought, a mass that would be invisible. And doing this, he managed to explain their motion, and he called this additional matter dark matter, because it was invisible. But then there was no immediate follow-up to his work on this. Until the 1970s, and in particular until the works of another astronomer, Vera Rubin. She observed the movement of the stars spinning around the center of their galaxies, and noted that stars that were far from the galactic center were moving way faster than they should. What the laws of gravitation tell us is that the speed of a body orbiting another object depends on the mass of the central object and the distance between them. This is why in the solar system, for example, planets that are closer to the Sun travel faster than planets that are far away. Their speeds range from 44 kilometers per second for Mercury, the closest planet to the Sun, to 5 kilometers per second for Neptune. Earth is in between, moving at 30 kilometers per second. Now, if we apply the same logic to a galaxy, the stars that are closer to the galactic center should also travel way faster than stars that are far from it, close to the ends of the galaxy's arms. Except they don't. Stars that are 10 times further away from the galactic center, in a galaxy like Andromeda, for example, travel as fast as stars that are way closer to the center. This is unexplainable by gravitation, except if there is actually more matter than thought. And in fact, she worked on the hypothesis that a cloud of invisible matter existed around the galaxies, which would explain how they move relative to one another, and also inside the motion and the speed of the stars that belong to them. But the problem is, a lot of this invisible or dark matter is necessary to explain the movement of stars. For example, in the Milky Way, it would have to be close to 90% of the total mass of the galaxy. In other words, 90% of the matter contained in our own galaxy would be invisible and unknown. This is not easy to believe. And since Vera Rubin's hypothesis, one of the questions that keep astrophysicists busy is, what is this mysterious dark matter? There are 3 possible explanations here. The first explanation would be that dark matter is mainly objects that are known to us, but hard to detect, because they emit very little light to us, like black holes or gas clouds or red dwarfs. We know these bodies exist, and some have been detected, but even assuming there would be many more, the sum of their masses remains far from sufficient to explain the effect of dark matter. Too much mass is missing. The second explanation would be that there are particles out there that we don't know of and have never observed because they would not interact with light. What could be these mysterious particles? We don't know, despite attempts to detect or even fabricate them in particle accelerators. Nothing has been found until now. The third and last explanation, but it is unsettling, would be that the equations of gravitation are incorrect, and that a new theory of gravitation, or something entirely new to replace it, has to be elaborated. Various observations that are puzzling have been made. For example, a galaxy called Dragonfly 44 would have to be made of 99% of dark matter to explain its trajectory. Other galaxies would be almost entirely devoid of dark matter, meaning that the distribution of this matter would be extremely uneven, depending on the galaxies. But at this stage, astrophysicists have had to conclude that either close to 80% of matter in the universe is unknown and has not been observed yet, or that the laws of gravitation are not accurate and need to be revisited entirely. Maybe in the future an explanation to this mystery will emerge, but in the meantime it reminds us of how little we know about the universe still. We are now in the immediate vicinity of Andromeda, which looks a lot like the Milky Way because it has a spiral shape, but it is larger. Its diameter is twice the diameter of our galaxy. However, the mass of Andromeda would be rather similar at about 1,000 billion times, 1 trillion times the mass of our Sun. Like the Milky Way, Andromeda has its own system of satellite galaxies. I mentioned Canis Major for the Milky Way earlier, even though it is disputed as a galaxy. But the Milky Way has more than 15 dwarf galaxies that are proven to be part of the same system, and Andromeda would have a similar number. Given their trajectories, the Milky Way and Andromeda are expected to collide in roughly 4.5 billion years, and their merger would form a giant elliptical galaxy. Andromeda would have formed 10 billion years ago. That would be 3 to 4 billion years after the Big Bang, and the galaxy would be the product of the collision of smaller galaxies. In its first billion years, Andromeda was probably very active with a high rate of stars formation. But over the past 2 billion years, it is thought that the formation of new stars throughout this galaxy has almost stopped, and the youngest stars in the galaxy would all come from the captures and mergers with its satellite galaxies. These captures leave what is called stellar streams, and these streams are the remains of dwarf galaxies that have been torn apart and stretched along their orbit. Now that we can see the Milky Way from afar, we could see these stellar streams that may not be aligned with the galaxy's plane. Like our galaxy, Andromeda has hundreds of billions of star systems and hundreds of billions of planets too. It is really in the 20th century that we have realized that the universe was much, much bigger than thought before, or at least that it contained more objects than thought, because until the appearance of the Big Bang theory, the universe was estimated to be infinite and eternal, which was a guess based on the very limited information physicists had available. Another breakthrough in the 20th century was the understanding of organic life and the physical and chemical processes that led to its appearance. Even though everything is far from explained, and science only answers the how of things, not why they ultimately happen, this is a metaphysical question. However, it looks well possible that the same physical conditions that have led to the appearance of life on Earth, or other conditions maybe, could also exist in other parts of the universe. The laws of chemistry are the same on other bodies in space, and the molecules that can combine to create organic life are relatively abundant in the universe. So even though the probability that it happens on a particular planet or satellite is very low, when you multiply that low probability by hundreds of billions for the number of planets in a galaxy, and then again by billions more for the number of galaxies, you can quickly conclude that the existence of life in other parts of the universe is a near certainty. Maybe it could even exist or have existed close to us in the solar system, on the moons of Jupiter, or even on Mars in the past. We also know that the universe was already 10 billion years old when the first traces of life, the first unicellular organisms, appeared on Earth, and other planets formed billions of years before Earth. But if life can appear in multiple parts of the universe and evolve like it did for us into conscious beings that could travel away from their planet of origin or send information like radio waves, how is it that nothing has been detected yet and that they haven't found us? The apparent contradiction between the absence of signs of extraterrestrial civilizations and the high probability that they exist and may be more ancient than ours is called the Fermi paradox, after a physicist called Enrico Fermi, who participated in a famous conversation about this. Arguably, it takes a long time to travel in the entire Milky Way, maybe millions of years at subluminic velocity. But millions of years is not much when the age of most stars and planets in the galaxy is several billion years. We should have found or detected probes, or at least signs of intelligent life that can travel faster, like radio waves. This question was raised by Fermi in this conversation in the 1950s, but even before him, it appeared in a manuscript by Russian scientist Konstantin Tsiolkovsky in the 1930s, under the same terms. How is it possible that the near certainty of the existence of intelligent life is nowhere to be found? Tsiolkovsky proposed one of numerous explanations to this apparent paradox, what is called the zoo hypothesis. This hypothesis speculates that extraterrestrial life intentionally refrains from contacting Earth and humans, either because they are not interested, what could we know about their motivations anyway, or because they want to allow for natural evolution, avoiding contamination. But they could be observing us like visitors observe animals at a zoo. Another possible explanation, called the rare Earth hypothesis, is that the set of circumstances that lead to the appearance of life and then the evolution of biological complexity are very rare or even unique to Earth. This hypothesis argues that there are so many conditions required to Earth-like life that this phenomenon is indeed almost unique. It takes a planet in a habitable zone of a star system, a guardian against collisions by asteroids, in the case of the solar system, Jupiter, a large moon, a magnetosphere to be shielded from solar radiations, an atmosphere, oceans, and yet another filter is the transition from unicellular life to more complex organisms, which on Earth took hundreds of millions of years, and may be a very unlikely event. If we follow the rare Earth hypothesis, the absence of signs of life is logical. It is because there is not. Or maybe life is not so uncommon, but intelligent species are exceptional. Life on Earth has existed for about 4 billion years, but what we call intelligent life has been around for only 3 million years. Of course, we define intelligence based on our own genus, Homo, because this is what we know. But arguably, human beings have been able to send radio waves and spacecrafts to space. No other species that we know of ever did that before during almost 4 billion years. So it tells us that even after the appearance of life, it may take billions of years before intelligence appears. In the case of Earth, 4 billion years is long enough in comparison with the universe, which is 14 billion years old. Maybe the appearance of an outward-looking species like ours is something really extraordinary, and life is maybe abundant in the universe, but intelligent life able to exit its planet of origin is something truly exceptional, and that would explain why no trace of extraterrestrial intelligence can be found. Yet another hypothesis, because there are many, is the water world hypothesis. It presumes that planets where life appears have a much smaller landmass than the Earth, or no landmass at all. For forms of life that will develop in water, it is not possible to use fire or develop hands, and even though intelligence is possible, this would limit their capacity to communicate and even more send objects to space. Other explanations are gloomier. One is that it would be in the nature of intelligent life to destroy itself long before it can establish contact through wars or maybe disasters provoked by technology. Or maybe the existence of periodic extinction on all planets due to natural events prevents intelligent life to travel or establish contact. They go extinct before they have time to do so. If we accept that other intelligent civilizations exist, maybe they are just too far apart in space or in time. If only a few such civilizations appear in a particular galaxy, they may just not have had enough time to meet yet. Following the same logic, the beginning of radio emissions by human beings on Earth is very recent. The first radio wave emission, was in 1895. And even though radio waves propagate fast, they have only traversed a very small fraction of the Milky Way yet, reaching only a few hundred star systems at this point, when there are hundreds of billions. Another group of explanations is that the signs are there, but we miss them. We are not listening properly. For example, extraterrestrials may transmit signals that have a very high or a very low data rate, or they may employ frequencies we consider unconventional, which would make their transmissions undistinguishable from background noise. Maybe another form of evolution for intelligent life, if it doesn't destroy itself, is that more advanced beings may divest themselves of physical form and transfer themselves to virtual environments that become their universe. They are no longer interested in exploring the physical universe we live in, and space exploration becomes meaningless to them. Or, finally, it is possible that the perception that life is meant to expand and colonize is just a cultural feature of our species, born from our minds and experience of life. Other civilizations may just have no interest in this and prefer to stay on their native world without even thinking about leaving it or exploring the rest of the universe. These are just some of the speculations that have been brought forward to explain the Fermi paradox, and there are more. After all, some people also believe or suspect that aliens are already here. But let's take another look at Andromeda, especially its center. Like for the Milky Way, it has a bulge, a concentration of stars that look more luminous. Since the 1990s, the Hubble telescope has sent better and better images of this galactic nucleus. It contains millions of stars and a massive black hole at the very center. It is believed that galaxies, at least spiral and elliptical galaxies, have such a supermassive black hole at their center. And this is the densest part of every galaxy. Black holes are extraordinarily dense objects that pull other objects due to their gravitational force. I'll put a link to an entire video I made about black holes a few years ago if you're interested. One day, in more than 4 billion years, when Andromeda collides with our galaxy, the two nucleus may merge, or one will be torn apart. We don't exactly know how things will unfold. Let's embark on another space cruise. But this time, we are not going to a particular planet, a star, or a galaxy. We are visiting representations of the cosmos, theories, and we are looking for something that may or may not actually exist, the center of our universe. On our way, I'll tell you about historical representations of the cosmos, about modern scientific theories, especially the Big Bang theory, the apparent expansion of the universe, the notions of time or space. We are about to take off for our biggest cruise ever, because this time we will not just go to other planets and galaxies by the power of imagination. We will travel billions of years into the past to explore the nature, the size, and the history of our universe, or at least what the current state of science can tell us about it, because as usual, this kind of explorations always requires a great deal of humility. The only solid truth here is that we know little and have to make hypotheses or ask questions with the maybe limited tools of observation and understanding at our disposal. Anyway, let's get started. So, where are we heading to find the center of the universe? Our ancestors believed that it was Earth, or the Sun, or much later the center of our galaxy. But we know today that these hypotheses don't really work in a scientific way. The first answer to this question, if we follow the Big Bang theory, is that we don't need to travel anywhere to reach the center. It's here. Not because Earth is at the center of everything, but because any point is as good as any other. There is no center to the universe we live in. What does it mean? You probably know the concept of the Big Bang theory. At some point in the past, billions of years ago, the entire universe was concentrated in a single point, and suddenly, like an explosion, this point expanded at speeds and levels of energy that defy imagination. This is not a bad metaphor, but it leads to a common misconception about the Big Bang that pictures it as an explosion in the void, as if the void of space pre-existed the Big Bang. If that was the case, the universe would have a center. In an explosion, the central point is the hottest point, from which matter and heat are projected in every direction. But this is not what the Big Bang theory says. The explosion did not take place in space. It was an explosion of space. What we call the void of space is part of the universe and enclosed into it. It is not something external. So rather than an explosion, an analogy that works better here would be one with a balloon that is being inflated. It expands in every direction. But imagine that the universe is not the ball formed by the balloon. It is its surface. Just the surface. Now if we consider this spherical surface and ask ourselves where is the center, we could say that it can be any point. All points can be the center because relative to them, all other points are moving away as the balloon inflates. Or, put simply, if I give you a football or a basketball, you cannot point to one particular point on this surface that would be its center. We will talk in more details about the Big Bang theory, what it says and how it became the prevailing model describing the appearance and expansion of the universe. But before that, there is also a wealth of historical representations and other more modern theories to talk about. So let's take things from the start. Until the 20th century, the questions of the age of the universe, its size, or its limits were not that much studied by scientists. This question was more considered to be in the field of metaphysics, literally what is above physics, and cannot be grasped or described with scientific laws. A lot of different traditions and religions around the world provided answers about how the world had been created and when, or more exactly the Earth, whether it was seen as a world among others, a ball or a disk. What the ancient called the world was Earth, and the idea that the sun and the stars revolved around it was not really questioned. But this physical horizon started to be put into question with the progress of astronomical observations and the realization that Earth was an object in space, among others, that could actually be way bigger. Over time, new models put the Sun at the center of the universe, like that of Copernicus in the 16th century, and they made Earth a planet among others in the solar system. Then the existence of our galaxy was progressively revealed, and in the 19th century, the Milky Way was often believed to be the universe itself, until it appeared that our galaxy was just one among others. So over several centuries, the size of the universe as we perceive it has increased dramatically, and our place in it as human beings living on planet Earth has been reconsidered in a way that is quite humbling. But another assumption in the 19th century was that the void in which the galaxy was floating was limitless and ageless. It was eternal. This was not a theory or something people argued much about, just a hypothesis that answered questions about the frontiers of the universe. In a sense, this assumption was comfortable, because if the universe was eternal, then there were no questions to ask about its formation, its history, or its age. And if it was limitless, then this eliminated the question of what could be beyond its limits. But this had not always been the case. So how did men picture the cosmos, the universe, and our place in it along history? In many different ways. All civilizations forged their myth of creation, in which different gods were the artisans, or sometimes the products themselves, of the world's creation. I told you about some of these myths in recent stories about Greek, Norse, or Egyptian mythology. But maybe the Greeks were a bit different in their approach, because they introduced something else. The idea that natural phenomena were not just things to be observed or attributed automatically to the gods, but also things that could be understood and used for a better comprehension of the world. The Greeks didn't define the scientific method as we define the concept today, but they certainly elaborated its premises. Other cultures around the world also had an elaborate knowledge of astronomy, for example, like in Mesoamerica or in China. But they didn't go in the direction of observing the planets, the sun and the stars as physical objects that could be measured and speculated upon to better understand the harmony of the world as a whole. Doesn't mean the Greeks figured out everything, far from that. To them the world had to be geocentric, that is to say with Earth at the center and all other objects in the sky moving around it. This was a rather obvious observation to our ancestors. They saw celestial bodies move above their heads and come back year after year to the same positions. They had no reason to imagine that Earth itself was just one of them. And So the Greek world adopted the concept of Earth at the center of an universe, with celestial objects placed on another larger sphere that rotated around our world. This is how Plato, the philosopher, described the universe in the 4th century BC. The Greeks had found through deduction that the world was round, even though this was not intuitive or visible. This shows the power of their deductive approach to nature. They were ready to adopt a vision that was not immediately obvious to their senses, because it was logical. And the same logic made them question this description of the universe with a single celestial sphere carrying the planets and the stars around our world. They observed that something didn't work with the motion of the planets. They sometimes appeared to move backwards in the opposite direction to the stars and the constellations the stars formed. We know why today. Earth is in motion too in the solar system, so above our head other planets of the solar system can seem to go backwards on their orbit, not because they do, but because our vantage point is also moving, which can create this observation. In astronomy, this is called retrograde motion, the apparent change in the movement of a planet through the sky because of its relative position to Earth and how both planets are moving around the Sun at the same time. There was no way that all celestial bodies could be attached to this single external sphere then, and they came up with another explanation, also based on observation and deduction. Since the stars and the planets were not synchronized, it had to mean that there were not one, but several celestial spheres carrying objects in the sky. Up to 33 different spheres of larger and larger diameter rotating around us. Interestingly, the axiom that we were the center of the universe was not much questioned. It was taken as such an obvious thing that most of the Greeks didn't think about the possibility that Earth itself was moving. Most of the Greeks, because there were exceptions. For example, Aristarchus of Samos, an astronomer from the 3rd century BC, who had a remarkable intuition. He placed the Sun at the center of the universe and made Earth a planet among others. But his vision didn't stick and was mostly ignored, even though it was in a way more pertinent scientifically than the geocentric universe and its spheres turning around Earth. But however flawed this concept of multiple celestial spheres rotating around our planet was, there were also interesting and promising ideas in this depiction of the world. By considering that every planet was carried by a different sphere, the concept of orbits in space appeared. And overall, this depiction of the motion of the planets, the stars, the Sun, and the Moon above our heads was quite satisfactory at the time. So in the West, it remained the dominant scholarly description of the universe, not just for the period of ancient Greece, but for many more centuries, almost 2,000 years, until the end of the Middle Ages. More significance and elements were added over time to this multi-spherical system to give it more spiritual meaning and connect it with natural sciences. Aristotle, for example, divided the universe into two parts. Everything up to the sphere that carried the moon belonged to the changing and imperfect world where life, decay, and death existed. This world, our world, was made of the four elements: water, air, fire, and earth. Beyond the lunar sphere was the world of the high spheres, with the planets, the sun, and the stars, where everything was perfect and eternal. The Christian tradition also added elements to this worldview, especially a friar of the 13th century called Thomas Aquinas. He added yet another sphere beyond the last one where God would have resided, and from where he could embrace the entire creation. Angels lived in the solar and planetary spheres. The degree of divinity decreased as one moved down, closer to Earth. The purgatory, a notion that had been introduced in the Christian tradition during the Middle Ages, and also our world, were part of the sublunar sphere. You see that there is still the influence of Aristotle in this worldview. And below our feet, even lower, underground, was where he placed hell, the land of evil, where bad souls ended after their terrestrial life. Men were placed in between the heavens, the high spheres of the divinity, and hell underground. Almost 2,000 years with a stable description of the universe, and one that had been embraced and completed by theologians for centuries. This carried a lot of weight, and it is important to understand the reluctance to reject it, not from just the Catholic Church, but also many scholars of the 16th century, when new theories were put forward. Because these new descriptions of the universe could not just be scientific speculation. They shook centuries of tradition and the credibility of all these generations that had embraced this Greek and then Roman and then Christian system. The first and probably the most important intellectual revolution of the modern era when it comes to the description of the cosmos happened in 1543, when a Polish mathematician and astronomer called Nicolaus Copernicus published his description of the cosmos as a new system that put the Sun at the center of the universe instead of Earth. And he explained the movement of multiple planets around the Sun in a way that was very convincing, embarrassingly so, for the community of astronomers who knew about the movement of planets. The fact of replacing Earth with the Sun had big consequences: intellectual, cultural, emotional, spiritual even, because it also meant that humans were no longer at the center of the universe, and maybe not even at the center of creation. This heliocentric hypothesis, with the Sun in the middle, was actually not entirely new. As we have seen before, it was formulated in ancient Greece. But at the time it hadn't been successful enough to make a cultural or conceptual impact. In Copernicus' system, the theory of spheres was not rejected, neither. He just supposed that Earth was on one of these spheres, and the universe was much larger than thought before, because to him, the last sphere, the one that carried the stars, stood still, it didn't move, and it was the motion of Earth that now explained the apparent movement of the stars in the sky. But to make it work, to make it fit with observation, he had to place the last sphere much farther than thought before, beyond the limits of the solar system. So at once, humans were ejected from the center of the universe, and the universe became much larger than ever imagined. That was controversial, but it took decades until the early 17th century for the various churches, Catholic and Protestant alike, to attack these new astronomical theories, especially at the time of Galileo, another well-known and major astronomer. But attacks were not just on theological or spiritual grounds. Scientifically, Copernicus' system seemed to work well, but it had a few holes. One that served as a starting point to a Danish astronomer, Tycho Brahe, was the observation of comets and the supernova. He saw in 1572, we are 29 years after the publication of Copernicus' system, he saw what looked like a new star in the sky, so shiny that it remained visible for a month, including during the day. He couldn't know it, but this was certainly a supernova in the constellation of Cassiopeius, the death of a dying star that liberated the energy of billions of suns in a few days. And this happened millions of years before the observation, the time for the light to reach Earth. But to him, if a new star could appear and disappear like this, it meant that the sphere of stars was not as immutable and perfect than thought since Aristotle, and even in Copernicus' theory. The sphere of stars could change. Another thing that caught his attention in 1577, 5 years later, was the appearance of a great comet, visible from Earth, and its trajectory could be observed. The trajectory formed an ellipse that seemed to cross several spheres, and these spheres were seen as material. They had to be solid to carry the various celestial bodies like the planets, otherwise the planets would have fallen. At the time, the concept of gravitation and the idea that bodies could float in space was not yet a thing. But if the spheres were solid, then how could a comet cross several spheres on its trajectory? Something was off. And even more in the early 17th century, when new instruments to observe the sky revealed that not only the moon seemed to have a geography, but other planets had satellites. This was when Galileo observed for the first time the 4 main satellites of Jupiter. In about 70 years since the publication of Copernicus' work, the old representation of the universe had crumbled, and new theories were popping up to explain the new observations made. On this path, the works of Galileo, then Kepler, Newton, very importantly for gravitation, that finally resolved the problem of these spheres that could definitely not be material. All of this made modern astronomy emerge, a science that was now primarily based on ever more precise observation. And when it comes to the field of cosmology, it had huge implications. Cosmology, the studies of the description, the origin, and evolution of the universe became a branch of astronomy or astrophysics. As a science, it was separated from tradition, religion, or myth. And it took decades, but this is another consequence of the intellectual revolution initiated by Copernicus' work. But due to its object, cosmology also has connections to other disciplines, to philosophy, to other branches of physics, like particle physics. And as we are going to see, the Big Bang theory is an attempt at bringing together astronomy, the observation and study of the various bodies in space, and particle physics. So after this little historical overview, we are now back to modern times and the march to the formulation of the dominant theory that describes the history of the cosmos. I told you that new instruments of observation, new telescopes, had appeared at the time of Galileo in the early 17th century and allowed these observations. Technical progress didn't stop to our days, and in the 18th and 19th centuries, ever more bodies were identified in space, farther and farther from us, which also invalidated the heliocentric model. I already told you about the discovery of galaxies and how, in our perception, the universe became bigger and bigger along the past 2 centuries. That was in the story about galaxies. The link will be in the description. So I'm not going to repeat all this. But what interests us here is how theories about the cosmos evolved with these discoveries. As I told you at the beginning, by the end of the 19th century, the old theory of spheres was long gone, and even though this was not proven, a common assumption now across the scientific community was that the universe was limitless and eternal. It had always been there, would always be, and it was also static. In the first decades of the 20th century, it began to be understood that these distant nebulas that were supposed to be maybe island universes or clouds of gas were in fact other galaxies like ours. The central figure to the discovery of the multiplicity of galaxies was Hubble, the American astronomer. And something odd was noticed. These galaxies, especially the most far away from ours, seemed to be receding in space. They moved away from us. This was impossible in a static universe. And so a hypothesis was formulated in 1927 by a Belgian physicist, Georges Lemaitre. If objects were receding in space in every direction from our vantage point, it had to mean that the universe was expanding. In 1931, he went even further and suggested that if this expansion was projected back in time, then the further in the past, the smaller the universe was. And there even had to be a time in the past when all the mass of the universe was concentrated into a tiny single point. In the 1930s, Einstein's theories about time, space, energy and matter were already very well known, and the concept that they were linked was admitted. Here again, link in the description about Einstein's theory of relativity. So it meant that there had been a time when suddenly the fabric of time and space came into existence, when this tiny universe began to expand. This contradicted the steady-state universe conception that was preferred at the time, and initially the idea that the universe could have a history was rejected by many. Arguments against it included the fact that receding objects could have other explanations, so that was an unnecessary hypothesis. I'll tell you more on these alternative theories later. And also that the beginning of time was re-injecting metaphysics or religious concepts into cosmology. Georges Lemaître was also a Catholic priest, which probably enhanced the perception that the Big Bang theory was an attempt at bringing together modern astronomy and the Christian belief in the divine creation of the universe. So in the 1930s and after, other theories that are now called non-standard because they have been rejected by the vast majority of experts and cannot pass peer reviews, were formulated. But in cosmology, non-standard doesn't mean necessarily false. A standard theory is a widely accepted one because it is backed theoretically and empirically by observations that fit with the model's predictions. New theories are non-standard until they are validated, but sometimes invalidated old theories do not disappear entirely. They keep a small core of supporters despite contradictory observations or flaws that made the scientific community reject them. When Copernicus published his main heliocentric theory, it could have been called non-standard in the sense that it went against the consensus. Then it became standard, but it didn't make it true either. No one puts the sun at the center of the universe anymore, and you remember that Copernicus didn't reject the theory of spheres, which was abandoned later. Einstein's theories also were non-standard when they appeared. So this whole movement with theories that emerge as an explanation, a new angle, should be seen as parts of a process. Now scientists and the general public also are human beings. The creators of a theory can be emotionally attached to it. There can also be appeal in holding non-consensual positions and getting a form of reward from it, from a sense of self-worth to the opportunity to join a community. So theories do not always die entirely, even when the scientific community as a whole moves away from them and ignores them because they are not backed by evidence or have been invalidated by new observations. Theories have to compete and prove their worth for their place in the sun. The theory of an initial Big Bang, when and where everything was concentrated in a single point, a singularity, began to gain more supporters in the 1930s and 40s. But the scientific community remained very split. On the other side were supporters of a steady-state universe. A new steady-state universe was formulated to explain how the universe can be steady despite objects receding. In other words, to explain how the density of the universe can remain the same when galaxies are farther and farther apart. This theory posited that new matter was generated, that there was a matter creation field that inserted matter into the universe to maintain a constant density. Why not? It is certainly not harder to imagine than the concentration of the entire universe into a single point. For 15 years, the two theories coexisted, but the Big Bang theory won thanks to the observation that its predictions worked. In particular, the concentration of the entire universe at the start would have implied that at the early stages of the universe, when the atoms began to form, there was a transition phase that should have left a trace, a cosmic microwave background, like a kind of white noise that would exist everywhere in the universe. It is not noise, of course, it is a faint radiation. This remnant or relic radiation was detected and measured in 1965, and it was a major game changer for the Big Bang theory, because it corresponded to its predictions, and this microwave background had no other known explanation. From this moment on, the alternative theories were progressively abandoned, and the Big Bang became the dominant, the standard approach to the description of the universe's history and its expansion. It fits with observations, it made accurate predictions, but it doesn't mean that the theory explains everything when it comes to matter in the universe. In the current state of cosmology, there is no theory of everything that would explain every single observation. Here again, there is more about this you can listen to with topics like dark matter in the story about galaxies. There are still alternative models to the Big Bang theory, or complementary models being worked on, that are based on new hypotheses for a steady-state universe. For example, one that supposes that the universe could go through successive phases of contraction and expansion, and we would be in an expansion phase, explaining Hubble's observation of the galaxies receding. But these are no longer mainstream, and the Big Bang is the standard theory since the 1960s and 70s. Many attempts at imagining and describing a different cosmology have been made in the past 100 years. More than a dozen looked serious enough to deserve conversation. The holy grail for a cosmological theory is to explain all observations made. That includes faraway galaxies receding, the laws of physics that seem to work well, like the existence of gravitation and relativity, the different forces that are observed with matter, from very small scales to very large ones. Hypotheses have been made to explain or challenge observations. One such hypothesis, for example, is called the tired light. What does it mean? I told you earlier that one major observation that participated in the understanding that the universe was most probably expanding was Hubble's observation that galaxies are moving away from the Earth at speeds proportional to their distance. The farther they are, the faster they move away. You remember the image with the inflating balloon at the beginning. If we are a point on the surface of this balloon and it is being inflated, other points on the surface will move away from us in every direction, and the farther they are, the faster they move away. But it is not that simple when it comes to measuring the velocity of galaxies. that are millions of light years away from us, how do you know how fast they travel when they are just tiny points that are invisible to the eye and can only be detected by telescopes? Hubble's solution to measure their velocity was their redshift. The redshift is an increase in the wavelength of light that we receive from them. It is called redshift because of the color red, which is at one extreme of the visible light spectrum for us. The concept is that a galaxy is moving away from us and sending us light in the other direction. The movement of the galaxy relative to us alters the wavelength of light, and this is how we can measure its velocity from where we are. But redshift works as a measuring tool of their velocity only if the change in wavelength comes from this growing distance between the galaxy and us. And this is where the tired light hypothesis was made. What if the distance was not changing in fact, but light was losing a little bit of its energy when it travels a very long distance? That could explain the slight increase in the wavelength, the decrease in the frequency. Tired light was abandoned as an hypothesis because it didn't seem to work for several reasons. No loss of energy for light was ever observed or explained, and also, if this theory was right, more distant galaxies would indeed be redder, but their surface brightness seen from Earth would also be stable, and it has been observed that the brightness evolved over time, which is not consistent with tired light, and actually backs the expansion of the universe theory. And then cosmic microwave background was detected, a huge argument in favor of the Big Bang theory, which sent the possibility of tired light into retirement. But as a question, it was a good intuition that deserved to be examined. An example of alternative cosmology that appeared in the 1960s and is now rejected by the scientific community but also was stimulating is called plasma cosmology. It has disappeared from labs and universities since the 1990s as a way of describing the universe, and we will see why. And now essentially survives in pop culture under the term electric universe. Electric universe proponents have in common their rejection of pretty much all the pillars of modern astrophysics, from relativity to a lot of observations that do not fit into their systems. It's a bit like a fancier version of flat earthers. Fancier because they use plenty of complicated words. But if you have even a basic knowledge of physics and watch an electric universe video on YouTube or elsewhere, you will quickly realize that this is just mumbo-jumbo. It is like when the crew talks about physics and engineering in Star Trek. The words are there, it sounds like science, but it is just entertainment. The whole thing makes no sense because nothing is defined properly and there is barely any logical connection between propositions. But let's leave this aside, because initially plasma cosmology was an ambitious attempt at challenging cosmology in the 1960s, adopting a different angle. You know what plasma is in physics. It is a state of matter, a fourth state after the ones we are constantly surrounded with, solid, liquid and gas. A gas is typically made of molecules or individual atoms. A plasma is like a gas, but a gas of ions, that is to say atoms or molecules in pieces. They have had one electron stripped and free electrons surround them in the plasma. It takes additional energy to turn a gas into plasma. It has to be heated or subjected to a strong electromagnetic field. A property of plasma is that it is electrically conductive. It is full of free charged particles floating, so it can transport electric currents efficiently. So what did the concept of plasma cosmology mean, and why was there some pertinence to it? Because one of the question marks or problems of the modern standard model of particle physics and the theory of relativity is that they theoretically predict a similar quantity of matter and antimatter in the universe. In their language, a similar quantity of baryonic matter and antibaryonic matter, which is the same as matter and antimatter. The Big Bang should have produced a similar quantity of matter and antimatter too. But that is in theory, because in the observable universe, where is all this antimatter that, put in contact with matter, should mutually cancel themselves? It has never been found, and this is a bit embarrassing for all these models. The problem is called the matter-antimatter asymmetry, or baryon asymmetry. This question has never been solved, including today, and it was already on the table in the 1960s. One big advantage of plasma cosmology is that it provided a possible answer that would help support particle physics. Matter and antimatter would indeed be present in equal quantity in the universe, but they would be isolated in bubbles, gigantic pockets that would be separated by electromagnetic frontiers. This way they would remain separated, isolated, and avoid mutual cancellation. To get there, the proponents of plasma cosmology extrapolated to much bigger scales the properties of plasma that were being studied intensively since the 1920s. Now this theory could also integrate some of the observations made about the expansion of the universe. We would live with our galaxy and many others inside a pocket of matter, bounded with electromagnetic fields, but over time, similar pockets would tend to merge, like bubbles in water tend to come together to form a single, bigger bubble. That could be an explanation for the apparent expansion of the universe. In this approach, what we would see would just be the expansion of our bubble of matter. As you imagine, that would be a quite big change of paradigm in cosmology. The importance of gravitation at the scale of the universe would be strongly reduced. The age of the universe estimated by the Big Bang theory would no longer make sense, and standard theories about the formation of planets, solar systems, and galaxies would have it wrong, because they did not take into account the major role played by electromagnetic forces, according to the proponents of this theory. So this was an absolutely stimulating angle to look at cosmology, but quite quickly it appeared that this approach created more problems than it solved. First, it was based on many hypotheses that cannot be demonstrated or tested. Where are these separations between bubbles of matter and antimatter? They have not been observed directly, and indirectly neither. There are no known traces, light, radiations, signals of their existence. The assumption that plasma can carry electromagnetic forces on extremely large scales is also contradicted by experimentation. And there is also everything that works in particle physics and relativity. If these are wrong, why all the successful predictions they made? Because it cannot be a coincidence. Plasma cosmology doesn't provide an explanation to cosmic background microwave, neither. So as the 70s, 80s and early 90s passed, it appeared more and more as an intellectual construction with little to support it. The argument that existing models are not fully satisfactory, which is true, none of the standard theories about matter and astrophysics in general explain everything on all scales. The lacks or the flaws of existing theories is no proof that any alternative is right, of course. This is why plasma cosmology and all its various ulterior iterations about the electric universe became fringe theories. They have actually never made a single cosmological prediction that could be verified, and they essentially exist as a discourse when standard theories have concrete applications that work every day. Particle physics is used in experiments all the time, or relativity serves to synchronize satellites in orbit around Earth, for example. At this point, you certainly understand why the Big Bang theory dominates today. Scientifically speaking, it defeated other possible cosmological theories, despite all its limitations. And the biggest limitation for the general public is that the Big Bang is a description of what probably happened, but it tells nothing about the why, what there could be before it, even though this question doesn't really make sense, because in the Big Bang theory's logic, time also appeared with the Big Bang, so it is absurd to wonder what there was before, if time didn't even exist. And the question of how it ends remains open between a never-ending expansion or, at some point, a contraction that would lead to a big crunch. So what happened in the early stages of the universe, according to the theory? It estimates that our universe appeared 13.8 billion years ago. For comparison, the age of Earth would be about 4.5 billion years. So our planet existed for about a third of the time the universe existed, based on these estimates. The first instance of the universe have been modelized, based on what we know of particles, energy, and how they should theoretically behave. But obviously there is no possible direct observation, and it is all very speculative. The universe would have appeared with a singularity, a name given to this original point because we don't have the models to describe it. Following the theory of relativity, it would have been a point of infinite density and temperature. In instants, far less than a second, the universe went through a quick inflation, a moment of still extremely high energy density and temperature, but now cooling down, and a phase of exponential growth, so fast and powerful that the universe could have expanded faster than light at the time. In these first moments, the laws of physics as we know them would have started to work, which is a necessary assumption to modelize this phase, otherwise we would have nothing to work with. Still, during the first second of its existence, the universe would have cooled down enough for the first particles to form. First quarks and gluons that combined to make protons and neutrons. And so the first bricks, the first components of atoms were born. But not the atoms yet. The universe was still too densely energetic for that. The first stages would have lasted seconds, but it took hundreds of thousands of years for nuclei of atoms and electrons to combine to form atoms. These atoms were hydrogen for the most part, the simplest and lightest kind of atom. You remember the cosmic microwave background that we mentioned repeatedly as evidence of the Big Bang. This is when it would have appeared. These newly born atoms were able to emit radiation, which since then continues through space, unimpeded. This is how the cosmic microwave background appeared. After thousands of years, the universe was still very young. Matter was initially distributed evenly, but over time, slightly denser regions would have appeared. These denser regions attracted more matter because of gravitation. They grew denser and formed gas clouds that with more and more concentration formed stars, galaxies, and all physical astronomical structures observable today. So we have seen a lot of things since our departure when we wondered whether we could go to the center of the universe. It turns out there is probably no such place, or at least this is what the current state of cosmology points to. But instead we have found a lot of information about how men have imagined, described, or measured this universe and their place in it, long before the birth of modern science. And maybe in 10 or 100 generations, our current understanding will look also very naive and lacking to our followers on Earth. But for now, we have reached the end of tonight's story. So you can now let go and fall asleep, or pick another one. Sleep well. Sweet dreams. Au revoir.